Yeah. So sometimes ago, I think maybe last year or so, your dean called me for a meeting. I mean, selection committee meeting.
Yeah.
But then I asked the subject. The subject was some number theory and other mathematics. But then I just requested him to relieve me from that.
Yeah, there was actually no candidate of statistics actually.
Yeah, statistics is fine. Yeah.
Then of course they contacted. They still wanted one statistics expert. So they then asked Professor Ashish Sengupta. So he joined.
Oh, anyway, he is nearby.
So there was one candidate who had his B stat, etc. So he has been selected also. But although his PhD is in algebra, but he is B stat, etc. And also he was teaching statistics.
I see. Okay.
Actually, we need people for statistics. We have very few statistics guys here. So, and our all the students study statistics. So last semester my class has 1400 students. All the undergraduate students, postgraduate students, PhD students, everybody wants to study statistics. So there is too much load on me. So we need actually some good applications of statistics.
Okay, so that the good is the problem.
Good is the problem.
you need good.
Yeah, especially in our system, they have a lot of things. I mean, first of all, I mean, you should be throughout first division. Then they should have some very good number of publications. I mean, good quality publications.
Yeah, quality publications.
Something called Q1, Q2 nowadays, no?
Yeah.
That impact factor should be quite good. All those things are there. So because of that, actually, we get very few.
Yeah. Good morning, Professor Reddy.
Good morning, Balakrishna. Yeah. Earlier by 9 o'clock, I came over here. I thought the schedule will start by 9 o'clock.
Sir, Professor Reddy, Professor Srinivas Rao is greeting you.
Oh, Srinivas Rao.
Yeah, no, I don't know whether Rao, K. Srinivas.
Oh,
so, please unmute your mic and just.
No, I have already. Okay, where Srinivas, no?
Yeah.
Good morning, sir. Srinivas.
Yeah, I think his mic is muted.
Professor Srinivas, you are muted actually.
ISRO.
Good morning, sir. Good morning, Balakrishna.
ICSDS, right? Not from Andhra University.
Good morning. Yes. Good morning.
Good morning, sir. Srinivas, how are you, sir?
Fine, sir.
Yeah.
The program is going on wonderfully well. We enjoyed all the sessions. And
So,
Jayasri Madam also has been very kind. Balakrishna sir is well known to us. And actually, that's my parent department.
Which one? Usmania?
Yes, sir. I started with 4 kilobytes of computing power. It was occupying the entire second floor of your Usmania University electronics navigation department. If I tell you 5 megabyte hard disk, we needed about 6 people to carry it with strong iron crowbars. You will not believe it. We started with Fortran 2, but people kept the activity alive. I am eternally grateful to Usmania University because even though I was a student, people gave me all the privileges. Thanks to the enlightened outlook in our department, I could go to DMRL, I could go to ECIL, I could go to RR Labs and other places. Selected packages were available at different places. And of course, in ISRO and elsewhere also, I have seen some of the most powerful computers, far beyond what most people can see, even abroad. And we have put it to good use. I am really grateful to the department. In particular, I should thank SS, Professor Srinivas, who used to come, pick us up in the scooter, even when we're tired. No, you go see a morning show, come back. And once you relax in the theater, you are ready to receive what I'm going to tell you. He used to come in the scooter twice to pick us up and make sure that it is taught. That's how he drew us to the university. Otherwise, I would have pursued many other careers also. But he molded us because he knew what is the impact of what was being done.
Okay.
Then he introduced us to Professor Pandit.
Yeah,
then came Professor C.R. Rao. Sorry, I've taken too much of your time, but I thought I should know the power of the department.
Yeah, there are big stalwarts there like Professor Sudhakar Rao, Professor Ramakrishnaiah.
Yes, sir. Then MSRM. God, he was a gifted teacher on design of experiments. We can never forget him. Then the ladies also, we had really, what is that? Enlightened ladies. Yeah, I mean, we had this madam. Yeah. Then the other madam, unfortunately, she met with an accident, but then she recovered wonderfully well. Subhadra Devi madam.
Subhadra Devi.
Then Uday Sri madam, and then of course Kishta Reddy sir was there, who actually taught us.
For sometimes Professor Iyengar was also there.
Yes, sir. We used to go to Professor Iyengar, not directly, but he was with the Department of Economics, not statistics. And
Jayashree madam. Professor Jayashree.
Sorry.
Please unmute your. Did you contact Professor Anup Bose recently? He's not seen in the list. I mean, in the.
I think the organizers contacting the people regularly. And update also. They update.
Professor Deshpande he is supposed to chair the session.
Yeah, that you have to verify.
I spoke to Professor J.V. Deshpande sir yesterday night, and sir is going to join us.
So whether there is any confusion with regard to the link, or you please ask them.
Okay, sir.
Sometimes they may join the other link, because several links were sent. So.
Sir, yes, probably they use the yesterday's link. That also possible.
Do you have a contact number of Professor Bose? I can talk to Professor Deshpande. I don't know phone number of Professor Bose.
Or otherwise, some network issues may be there. Otherwise, they will not join by the time.
Yeah, but both of them have not joined. Means there may be some communication gap also.
Yeah. I have to verify. In fact, anyway, Professor, the organizers part, they have to. Is it possible for them to contact them?
Yeah, I will contact Professor Deshpande. Madam, you try to contact Professor Bose.
That's fine.
Actually, there are 4 links given in the same mail, but the first link is Hall D. So sometimes they may click on that actually.
No,
that is what I mentioned.
Actually, the second link is Hall A. So by mistake, if they click the Hall D, then they may be in different place.
Good morning, sir. This is Balakrishna from Cochin.
Sir, I contacted Professor Arup Bose Sir has joined in Hall D, but now sir is joining.
Yeah, in fact, both Professor JVD and they are in Hall D and they are talking each other.
Yeah. That, okay.
So they got some time to speak to each other. That's good.
Yeah. Professor Bose has joined. So.
Professor Bose, you are muted. Yeah.
Yes, I have joined, and I've also told Professor Deshpande that it's in Hall A. So there was a confusion.
Yeah.
Really sorry about that.
He'll join now. He'll join. That's fine. Yeah. Still it's okay.
Good morning, Arubo sir.
Good morning, Professor Jayashree.
Good morning, sir. Very happy to see you all in the morning, sir.
Yeah, why not? Good morning, Professor Rao. Yes. Hi, Somesh. Yes. Morning, Professor Malik.
Good morning. Good morning.
Yes. Morning, Professor Balakrishna.
Good morning, sir. Good morning.
Professor Srinivas.
Good morning, Professor.
Good morning.
Yes, good morning. Good morning, Professor Sumesh Kumar. Good morning,
Yes.
Bose. Yeah, good morning. Good morning.
Good morning to all, Professor.
Yeah, good morning to all. Yeah.
Namaskar, brother Malik.
Namaskar.
I think the Namaskar has a better attraction than good morning.
Yeah.
Okay. We can do it once more. Yes.
Yes. In COVID-19 situation, it is much better.
Yeah.
Exactly.
Yeah, even I think Prince Charles or someone we saw,
Right,
he was doing.
right. Yes,
That's
like this.
That's right. Balakrishna sir, you are from Cochin?
Yeah, I'm from Cochin, yes.
Yeah.
I studied in Cochin, sir, Girinagar Central School. Long back, 60s and
No,
70s.
which subject?
I was in school at that time.
Oh, okay. Central school, maybe, yeah.
But many people from Cochin University used to be in our neighborhood. Some of them even taught me, particularly oceanographic department.
Oh, yeah, that is in Maran campus, yes.
Yes, sir. Yes, sir. You know Malayalam, sir?
Oh, yeah, very well.
Okay. I do still keep looking at the movies. I used to write Malayalam also. Okay.
Yeah, good. Yeah, because in the email, I think the first link was given for Hall D. That must have created some confusion. Yeah.
Yes.
Yeah.
Yes.
Sir, shall I call sir once again? JV Deshpande, sir.
Yeah, you may call, please. Tell him that is the second link in the email.
Yes, sir.
Second link in the latest email.
Sir is joining, it seems.
Yeah.
Yes, spoken. Double it.
I think that order change in the email created some confusion.
Yeah, generally the tendency is to click the first link. So
yeah.
But all the links, but all
that
the
is what,
links,
yeah, that is what we were told yesterday during the common session. Any link will lead to the main link. That's, but I think that did not work today.
Oh, that is not working today. Yesterday it has, no, it happened like that.
Madam, did you talk to him recently? Yes, madam.
Yes, sir. One of our person contacted sir, and sir said it seems that he will be joining. I will also call sir once.
No, don't call very frequently. So.
Yes, sir. Sir might get confused.
Jayashree madam. Professor Jayashree.
Madam is talking to sir again, Deshpande sir. So Jayashree madam is talking to Deshpande sir.
Jayashree madam, can you hear me?
Jayant 921.
So ma'am is talking to Deshpande sir on mobile.
Yeah, Deshpande sir is connecting to A.
I think if he gives his consent, I think we could start the session. Already 9:43. Sir, shall we start the session? You can join in between.
Yeah, I think it may be better to start.
Yeah, so I just talked to him and took his permission to start. So he may join in between. Shall we do that, Professor Bose? I think you are muted, sir, Professor Arubus.
Yeah, okay.
Yeah,
we can start.
So I think let me just start the program and he will join in between.
Okay.
So,
Okay, sir.
So very good morning and welcome to the first session of the day, that is plenary talk by Professor Arup Bose. Professor Arup Bose is a professor at Indian Statistical Institute, Kolkata. And I leave the remaining details to Professor Deshpande to say afterwards. So now I request Professor Bose to start his talk.
Okay. Let me share my screen. It is
Sure, yes, sir.
Always a pleasure and an honor to be a speaker at ISPS. And I thank all of you who are instrumental in allowing me to talk here. My screen sharing is disabled. That's what it says. Host disabled participant screen sharing. So somebody has to give me permission.
Yeah. Please permit Professor Bose to share his slides.
Yes,
Yeah? Sure.
now you can, sir.
Yeah, okay.
So just try once.
Okay. Can you see my screen now?
Yes, sir.
Very good.
Yeah, it is visible. Yeah.
Okay. So if you recall, I gave a talk in the previous ISPS conference that was in September, where I had given some introduction. And so I will try to build on that. I wanted to add something lot more, but I could not because I got bogged down with several other commitments. Anyway, so there'll be something new in this talk compared to the previous one, and there'll be something old also. So where do articles on random matrices appeared? I had mentioned this earlier also. So there is a journal completely devoted to random matrices theory and applications from 2012. So it's celebrating its 10th anniversary. Articles on high dimensional random matrices, which is where I work, also appear in computer science, life science, physical science, mathematical science, engineering science, etc. I mean, of course, matrices are everywhere, but random matrices, including the high dimensional ones, have been finding applications in so many other areas. There's a huge explosion of articles on random matrices. So what is a random matrix? A matrix, all whose entries are random variables. Or you can think of a collection of matrices from where you pick according to some probability law. Irrespective of what, you can think of that matrix as having entries which are random variables. And of course, classical statistics is full of examples of such random matrices. For example, you can think of the contingency table, R by S contingency table, or the data matrix, or the random design matrix, the sample covariance matrix, or the Wishart matrix when you assume that the entries are Gaussian. Started way back in 1928. That was one of the earliest non-trivial examples of random matrices. I put that in bolds because this is something that I'll discuss a little bit in this talk. And then there is this Wigner matrix, which came up in nuclear physics in 1955. The Topli's matrix with IID entries, or the Hankel matrix with IID entries, they are very well studied in operator theory. And then the IID matrix, where all the entries are assumed to be independent and identically distributed. And there are beta matrices, which are very important in particle physics. So they are sort of a generalization of the sample covariance matrix in terms of the joint distribution of the eigenvalues. And then I'll talk quite a bit about the autocovariance matrices in high dimensional time series. So as we all know, the unadjusted P by P sample covariance matrix is S, which is XX star by N. So this vector, so there are N observations. So you can think of X as P by N matrix, and each column is the data on the p-dimensional vector, and you look at XX transpose, and then you have to average scale it by N. So this is of course a key matrix in multivariate analysis. And we also know that when the entries are Gaussian, then S is called a Wishart matrix, and the joint density of the eigenvalues can be calculated explicitly, and they are of course used in statistical inference, for example, principal component and other multivariate methods. When P is fixed and N is large, the set limit theorem arguments can be used to study the large sample properties of S. So remember that X is P by N, so that P is the dimension of the vectors of the. So if P is fixed, namely the dimension of the vectors is fixed, then of course as N goes to infinity, you are in the repeated sampling situation, and one can prove that the joint distribution of the eigenvalues is asymptotically normal. So this is what is used for inference purposes. But when P is also large, the standard tests will break down. So this hotel square and other things, and they will not have enough power. And the behavior of the matrix is very different in these cases. And I'm going to mention how the behavior changes. So next matrix that I want to say is the autocovariance matrix. So suppose x1, x2, xn is a mean zero stationary stochastic process. And then the autocovariance sequence is defined as gamma h, which is expected value of xt plus h. Remember, x is real value. So you look at the lag difference. So xt and xt plus h, you take the covariance of that. I have assumed that the mean is zero. So there is no centering needed. And then one can consider the dispersion matrix of x1, x2, xn, as you can realize that the covariance between any xi and xj will depend on the lag, on the difference I minus j. And hence the dispersion matrix sigma n will look like the following that I have displayed here. So all the diagonal values will be same, namely gamma 0, and then the first diagonal will be gamma 1, and so on. So these kinds of matrices which are constant along specific diagonals, they are known as Topli's matrices. One can then think about the sample autocovariance matrix. So this was in the population because you have put expectations everywhere. So you can think of the corresponding estimates. So of course the hth order autocovariance will be estimated by the sample average of the lag products. So xt plus h, j equal to 1 to n minus h, and then you average it. And you divide by n minus 1 so that you stay positive semi-definite. If you divide by the number of terms that you have, namely n minus 1, then the corresponding autocovariance, sample autocovariance matrix may not remain positive 7 days later. So then we get this sample autocovariance matrix gamma and X, which is you put the estimated values in the original matrix. So then that becomes the sample autocovariance matrix. Of course, this is a symmetric random matrix because it depends on the observations XTs. Now, in this talk, I'm going to focus more on the high dimensional case, namely where the dimension P becomes large, and the mathematical formulation is that P goes to infinity together with N also going to infinity. And then you can have some assumptions on the relative rates at which P and N go to infinity.
Sorry to disturb you, sir.
Yes.
Good morning, Deshpande, sir.
Okay, he's here.
Welcome you,
Right.
sir, into the session.
Yeah, I am here, and I'm sorry that there was some problem initially. Please, Dr. Bose, please continue.
No problem. Okay.
Please continue, sir. Sorry
Okay.
for this inconvenience, sir.
Okay,
Thank
no
you,
problem.
sir.
No problem.
Thank you, sir.
No problem. So high dimensional matrices come up naturally in high dimensional models. So I assume that XTs are p-dimensional observations, and there are n many observations. So the sample size is n, and the dimension of the observations is p. And both p and n are assumed to be large. And then the sample covariance matrix is high dimensional because it's a p by p matrix. And as I mentioned, that the usual formulation is that both p and converge to infinity, and there might be some assumptions about the relative rates at which p and n go to infinity. And as I had mentioned earlier, that usual procedures do not perform well in high dimensions. Namely, if p becomes large, then either your standard procedures are not going to work. So from that point of view, understanding the properties of high dimensional random matrices is important, specifically the sample covariance matrix also. To understand the reasons for failure of the standard procedures and to devise new methods for statistical analysis. So let me move to the main matrix that I'm going to discuss here, which is the autocovariance matrix sequence. Now, earlier I had mentioned the one-dimensional observation. So x1, x2, xn was a real valued time series, and we talked about this autocovariance matrix and its corresponding sample version gamma and x. Now I'm assuming that the xt's are p-dimensional vector valued time series. So earlier we had the real valued time series, and so we had a sequence of autocovariances. Now for every I, we get a p by p matrix gamma I, because if I take xt, which is a vector, and then I take its transport at lag I, and then you multiply, then you get a p by p matrix. So and you take the expectation, that is the ith order autocovariance matrix. And each of these autocovariance matrices, of course, of dimension p. And as you change n, you're a host of different autocovariance matrices. The sample autocovariance matrix of order I is the corresponding sample version. Namely, so you take xt and you take the lag value at t minus I, and you take a transpose. So xt prime for every t is a matrix, and you take an average of those matrices to get your gamma hat I. Now also note that unlike the gamma hat 0 that I had mentioned earlier, all these matrices are non-symmetric matrices because they do not appear in the xt and the xt prime values do not appear in a symmetric way in the construction of the matrix. And it is known to people who work in large dimensional random matrices that non-symmetric random matrices are notoriously hard to analyze. And one way out is to resort to some kind of symmetrization. For example, you can take a matrix A and you take this transpose and add them to make it a symmetric matrix, or you look at its singular value, namely you look at A star and consider its eigenvalues and so on. So this is just a way out, and of course there's a loss of information if you do that. But non-symmetric matrices are very, very difficult to find their properties, especially in this random matrix context. There are very few results known. I'll mention one or two as I go. So then for these matrices, which are high dimensional matrices, what should we study? Of course, matrices are linear transformation, and its features are captured by its eigenvalues. So we could study the eigenvalues in some way. We'll give a brief glimpse only into the behavior of the bulk of eigenvalues of sample covariance and sample autocovariance matrices, and I'll very briefly mention some applications. Of course, there are other aspects that people have worked on, and as I mentioned, that's a huge literature, and there are many important developments in this area. So, for example, one could look at the joint behavior of random matrices. You might have more than one sequence of matrices. For example, as we have different autocovariance matrices of different orders, so we can think about how they behave jointly, and that gives rise to a concept known as the free independence. And or one can look at the behavior of the extreme eigenvalues. Again, some results are known for very specific matrices, and almost nothing is known for the autocovariance matrices as far as the extreme eigenvalues is concerned. I think there is some noise here, so please mute yourself as I speak.
Yes, I request all others to mute the mic so that the speaker will not.
Thank you. Yeah, because others cannot hear otherwise. Yeah. Okay. So one can think about the behavior of the extreme eigenvalues. That's a very difficult area. And there are very few results known, say, for example, the Wigner matrix or the IID matrix. And so you can get very new types of limit distributions. And some of them are not even known in any explicit forms. One could also study the behavior of the gaps between eigenvalues, and that is linked to what are known as determinantal point processes. And of course, once you do the studies, then you use this knowledge of these aspects to develop statistical procedures to analyze high-dimensional data. And as I mentioned, even the basic results on extreme eigenvalues, there are not too many. So one needs more tools and techniques to develop this area and put them into applications. I'll be more interested in what is known as the bulk of the spectral of the eigenvalues. So this is how it is defined. So suppose I have a p by p random matrix with eigenvalues lambda1 to lambda p. Then the empirical distribution of Rp is the probability distribution that puts probability 1 over p at each of these eigenvalues. So this is very similar to the empirical distribution function. You take these values instead of the observations, you take the eigenvalues, and you think of them as having equal probability to come in your sample. So this probability distribution varies from sample to sample. So it is, of course, a random probability distribution, just like the usual empirical distribution function is. And it's a cumulative form. I will just define it because in one couple of slides, I'm going to use this definition. So if all the eigenvalues are real, then you can take the cumulative version of this probability, and that is usually called the empirical cumulative distribution function. We can also consider the histogram of these eigenvalues, and the limit results that I'm going to mention, you can view them as results on the histogram of these the eigenvalues. And so once you have this empirical spectral distribution, then you can talk about its limit. So just like we have any sequence of distribution functions, we understand what we mean by the limit of that sequence of distributions. The only difference here is that the sequence of distributions that are under consideration, they're all random probability distributions. So that is known as the idea of LSD. If as p goes to infinity, this empirical spectral distribution converges weakly. And for our purposes, these are random distributions. So we must be specific about in what sense. So for our purposes, almost surely to a probability distribution, then the limit is called the limiting spectral distribution. Loosely speaking, if the histogram stabilizes as p goes to infinity, then the limit curve defines the limiting spectral distribution, if you don't want to be very formal in your mathematically precise. This is called convergence in the bulk, since any finite number of individual eigenvalues do not matter in the limit. So you're putting all the eigenvalues in one box, and you're trying to see what happens overall instead of looking at the maximum or the minimum or the other eigenvalues. Okay, so here is what happens. For example, if you can simulate this very easily yourself. So this is what happens for the sample covariance matrix. So I have taken this X matrix, which is the IID matrix, is a p by n matrix, and I've looked at XX star. And so that is the sample covariance matrix, and you scale it by n. And as you can realize here, the distribution depends on the ratio of p by n. So the first graph, p by n is 0.25, and this next one, p by n is half. And so the nature of the curve changes as p by n changes. And of course, if p by n is bigger than 1, then realize what happens. Then the dimension p is, so x was p by n, so the dimension p is bigger than n, and of course the S matrix will have a maximum rank of n, so there will be a lot of zero eigenvalues because S is p by p, and so a mass will appear when p by n bigger than 1, which I have not given in this simulations. So this is very easy to simulate, and you can check it. All right. So having done that, let's go back to the autocovariance matrix that I had introduced. So recall that xt was a real valued mean zero stationary process, and gamma h is the autocovariance, and the sample autocovariance was the sample version of the dispersion matrix of x1, x2, xn. As we had realized, it has a Stokes structure, but the entries are dependent. And it's very interesting to see what will happen to this matrix. This is now an n by n matrix because I have n observations. So I have gamma hat 0 and then gamma hat 1 and so on. So this is an n by n matrix. I have very few observations in the corners of the matrix, but as n goes to infinity, all of these diagonals are going to contribute in some way or the other, and it's not clear what is going to happen to the empirical distribution function as I increase my dimension n. But on the other hand, we know that the sequence xt is a mean zero stationary time series. So under suitable assumptions, it also has a spectral density, and it is quite imaginable that the spectral density will come up in the limiting spectral distribution. So this is what happens. I'm not going to give you a precise theorem. It's a little complicated. The limiting spectral distribution of this autocovariance matrix exists, and the properties of the limiting spectral distribution are not known in closed form, unfortunately. And the limiting spectral distribution is connected to the spectral density of the process, and the distribution is unbounded. But what is also very interesting is that you cannot recover the density from this limiting spectral distribution. In other words, two different spectral densities can give you the same limit. Okay. So this was my first limit result that I wanted to mention. But remember, this was when the dimension p is equal to 1. What I'm doing is I'm looking at the autocovariance matrix and looking at its sample estimate, and then trying to study its properties. Okay, now let's move to the high dimensional case. So in the high dimensional case, I'll need to introduce some assumptions. So I assume that xt, which is a p-dimensional vector time series, p is going to go to infinity eventually. I assume that that's a linear time series, and we know that all these moving average ARMA models, etc., they're all linear time series. So so I take this linear time series. So here the psi j's are matrices. These are called the coefficient matrices. So like, for example, in the usual autoregressive case, so these are parameters. So psi j's can be thought of as parameters, and the epsilons are vectors. So they are all p-dimensional vectors. I'll assume that the epsilon t's are IID with mean 0 and variance covariance matrix IP. Now you can have a non-identity variance covariance matrix. The results will remain, but they'll start getting more complicated to state. And we assume that p and n both are going to infinity, and you can think of n as being a function of p, such that p by n goes to y, which is between 0 and infinity. And y equal to 0 is left out of this talk. I'll maybe make a brief mention at the end about what happens when y is equal to 0. So that is the case where the dimension p is relatively small compared to n, but both are going to infinity, remember. And the other case, of course, will be that when the dimension p is too large with respect to n. So, and these are sort of complementary to each other, because the non-zero eigenvalues of x star and x star x, they are the same always. So the specific case in equation 1, where all the shi's are 0 except for the first one, namely the psi 0, I will call that the MA0 process. So the autocovariance matrix sequence, as we had defined, the p by p sample autocovariance matrix of order I of xt equals gamma hat I, which is equal to 1 by n xt plus 1 xt plus I transpose. Remember that each xt is a vector, so each xt plus I transpose is a matrix of order p. So gamma I hat is a matrix of order p. Also note that as I had mentioned earlier, if I is equal to 0, then this matrix is symmetric, which is the really the essentially the sample variance of the xt's. And the autocovariance is when I is not equal to 0, all of these matrices are not symmetric. And for the most part, we shall resort to additive and multiplicative symmetrization, such as gamma I star, etc. So in general, I can take these matrices gamma I, finitely many of them, and take any kinds of combinations of these matrices so that I can get a polynomial of these matrices. And usually that polynomial will be assumed to be symmetric. So here is my second limit result. Again, I'm not going to give you any mathematics here. Those who are interested can go and check the references that I will mention at the end of the talk. So this was done by one of my students, Monica, and myself. There are a series of papers, and I'm going to give you in a nutshell what happened in these articles. The limiting spectral distribution of any symmetrized matrix polynomial of the sample autocovariance matrices exists, but it is not possible to write the limiting spectral distributions explicitly. These LSDs can be described in terms of what are known as free variables in a non-commutative probability space. So that's a very technical result, and one has to have a lot of machinery to understand really these limits. But free variables are roughly like independent random variables. But realize that for the matrix there is no commutativity. So the usual notions of independence do not apply for matrices. So there is a notion of independence in the non-commutative objects like matrices, and this freeness is the notion of the corresponding notion of independence for non-commutative objects. So that's a very, very technical thing, but unfortunately without that you cannot really, just like in many statistics limit distributions, you can express the limit in terms of further independent random variables. For example, the Kramer-Von Mises statistics, the limit is a sum of independent random variables with some weights. So here also the limits can be expressed in terms of within quotes independent random variables, which are called free variables. So when p by n goes to 0, then something different happens. You cannot look at the gamma I hats itself. You need a different centering and different scaling. And with that, one can still look at the polynomials, the symmetric polynomials, and prove the same kinds of results. So that's slightly more harder than the p by n going to y, which is not 0 case. The limits can be used, of course, for statistical inference, and I'll spend a couple of slides on just giving a very brief glimpse of how they can be used. And as I had mentioned, very limited results are known for the non-symmetrized autocovariance matrices. That's a very wide open area to find, very challenging to find the limiting spectral distribution of any symmetric, non-symmetric autocovariance matrix. Okay, so because there are no general results for non-symmetric matrices, let me give you one simulation at least, and maybe mention a couple of results that are known. So the empirical spectral distribution of gamma 1 hat for MA0 case. So what have I done here? So I have taken epsilon t to be p by 1 IID random variables. You can take any distribution that you like. The limit distributions are all going to be independent of the underlying probability distribution, just like in the center limit theorem. So the limit distribution does not depend on what parent distribution you choose. So this is gamma 1 hat, which is 1 by n summation epsilon t minus 1 star. Of course, as you can realize, this is a non-symmetric matrix. And if you simulate with n equal to 500, and the errors to be maybe, as I mentioned, whether you can take normal or Bernoulli or whatever, they are all standardized entries. So you get these two pictures here. The one of them is for p equal to 250, and the other is for p equal to 500, and n is 500 in both cases. So the p by n ratio y is half in the first case, and p by n is equal to 1 in the second case. So it's clear that the limit, if at all, is going to depend on this y, and it's also clear that there is some kind of limit there. So the points are very systematically symmetrically distributed around it. Note also that this is a bivariate plot, because the eigenvalues of this matrix are going to be complex numbers, because the matrix is non-symmetric. So here is the result for this matrix gamma 1 hat, but only in this special case where the epsilon t's are where the xt's are white noise, namely that I'm not looking at the general moving average process. I'm looking at this specific case where all the other coefficients are 0. So suppose we have a complex valued time series with a non-trivial real and complex part, and suppose p by n goes to suppose p and n both go to infinity, such that p by n goes to y, which is non-zero. Then the LSD of gamma 1 hat 0 for this process exists in the complex plane, and is, as we have seen in the picture, it is rotationally invariant. The proof of this is highly non-trivial, and some description of the limiting spectral distribution is available. One can write down a reasonable formula for the limiting distribution, and the limiting distribution will have a density, except for the case where p by n is bigger than 1, where you have a point mass at 0. But other than that, and so you can look at this reference if you are interested. And the same LSD holds for any gamma I for the moving average of order 0. The limiting spectral distribution of gamma 1 hat for the moving average order of order 1 has been developed in Bose and Hachem. And it's not like, for order of 0, you have a paper, and for order 1, you have another paper, and so on. The point is that these problems are extremely hard. And as soon as you change the nature of the matrix a little bit, then it becomes a completely different problem. I hope at someday enough progress will be made where you can have a general theorem. But until then, these are the two results that are currently available. And finally, the final result on asymptotic normality of the trace. Remember that I had said that for any matrix polynomial, you can find the limiting spectral, you can show that the limiting spectral distribution exists. And the way those results are proved is by looking at these matrices and calculating their trace and try to study the behavior of the trace of these matrices. And so while doing that, one can also show that if you take any matrix polynomial, if you take a trace of that, then asymptotically, after proper centering and scaling, asymptotically, all of these traces will have asymptotic normal distribution. Of course, what normal distribution will depend on what polynomial you take and what are these coefficient matrices, Shijs. So these ideas can also be used to show that trace of any polynomial after centering and scaling of the sample autocovariance matrices is asymptotically normal. Okay, so as I mentioned, as I promised, I'll give a very quick glimpse of applications. First of all, for graphical inference, you can do, for example, you can do white noise testing, or you can test other hypotheses. So let me show that with some plots. So if I had my process is moving average of order 0, and if I look at gamma hat 0, then of course I have the Marchenko-Pastur law. This we have already seen, and this is the cumulative version of that plot that I had shown you earlier. And if I start with the moving average process of order 0, and I look at this this matrix here, namely the singular values of gamma u star, and no matter what you take, the order of your autocovariance, you're going to get the same plot. So this curve that you see here are actually 4 different plots, 4 different curves, and they are really coming one on top of the other. So in other words, the spectral distribution in this case, for each of these gamma hat u star, for every u they are going to be same. So this is happening because you have a moving average of order 0. Now I'll take 2 more minutes. I'm almost done. I'll finish more or less in time. Okay, so this is what happens when you have a moving average of order 0. Now let us see what happens when you have a moving average of order 1. So in this case, I again look at this same matrices, namely this gamma hat u star. But now you can see that 3 of these processes, namely gamma 2, gamma 3, gamma 4, u equal to 2, 3, 4, they will be different, and they are all they are all different in the sense that they are different from u equal to 1, but they are all going to be the same with respect to each other. So in other words, you can very quickly pick up the order of your model by looking at these plots. So because the order is 1, you see only 1 curve shifting out, and if the order is 2, you will see the first 2 curves shifting out, and so on. Okay, so that you can see here. So if I have a model of order 2, then the first 2 curves will shift out, and the other 2, namely the u equal to 3 and 4, they will be superimposed. They will remain the same for each other, and they'll be different from the first. Okay, similar patterns if you use other combinations. So you can choose your own matrix combinations. You get the same kinds of patterns or same kind of deviations, and they will pick up the order of the model very easily. Applications too. This is very commonly used in high dimensional time series in many different areas. spectral distributions might be harder to get results on that, but traces are easier to tackle. So people have looked at very specific matrices and very specific trace, and they have done the testing with respect to those traces. But what our result will tell you that no matter what polynomial you choose of this autocovariance matrices, the trace is always asymptotically normal, and you can find out reasonable formulas for the asymptotic variances. They of course depend on the matrices, unknown parameters, and so on. So significant testing of suitable simple versus simple hypothesis involving the coefficient matrices can be done by using the asymptotic normality of traces of these polynomials. All right. So with that, I sort of end. I have two more slides. In one, I'm giving you the journal references, and in the other, so if I pause for 20 seconds for you to have a quick look if you want to make a note, or I can make the slides available to all of you. If you request, I can send it to you. So this is the paper that I was mentioning that does the gamma 1 case for moving average of order 1, and this is still not published. And the works with Monica, these are all appeared in Annals and IJPM and Random Matrix RMTA. So these deal with all kinds of polynomials and the traces of these polynomials. And if you're interested to get into this area, right now there are a lot of books available, and one of them was written by myself and Monica, which deals with the main topic of this talk today, namely the covariance and the autocovariance matrices. Okay, thank you very much.
Well, thank you, Professor Bose.
Thank you
for
you are Professor Deshpande, you are muted. Yes.
We have got a gist of the area, and apparently one can have some reason for testing the null trace of these matrices. Could you please elaborate on that?
Yeah, it's right now it is only for white noise testing, and some people have used it for other kinds of testing also. So you have two competing models, and and usually finding out the limiting spectral distributions are hard as soon as you go to the non-null case. But what usually people do is take the autocovariance of order 1 or 2 or something similar, something simple, and then look at their trace.
Yeah,
and so the behavior of the trace under the null and the alternate will be different, but both of them will be asymptotically normal. So that's the way out that people have been taking.
Okay, so even the non-null distribution would be
for the
normal,
trace. For the trace, it will be normal. For the trace,
with changes in the parameter value.
Yes, with changes in the parameter values.
Yeah. So, are there any other questions from the audience? Please open your microphone and ask.
I just want to make.
I'd like to compliment both sir for this. Like, my background is statistics, all right, but from image processing point of view, where I've spent all my life, you have got testing with respect to eigenvalues, which you have mentioned well. But what happens is the rotation comes from the eigenvectors.
Yes.
So is there any mechanism by virtue of which you would advise us to test our rotation matrices? For example, in Nader viewing, a tolerance of plus or minus 2.74 degrees is acceptable. But when that tilt angle changes, the game changes again. So can you advise with respect to vector testing?
Yes.
Another point also I would like to compliment you is you're working on random circulant matrices. In digital image restoration, we use it extensively, but we use a little more complicated version called block circulant matrices. Here again, because of the vehicle-induced motion, a lot of random noise steps in. So now I leave the floor to you to advise me, sir.
Okay, so first of all, I have not worked on the random vector problems. They are much harder than the eigenvalue problems. But there are some articles on random vectors, which I am not an expert to comment on those. But there are works by both statisticians, probabilists, and also people who are from the engineering sciences, especially computer science. So there are some works, but I'm not too aware of those things.
Appreciate.
Yeah, very difficult problems. And
I appreciate it.
For the block circulants, there are some results on the block circulants, but again, I don't have the results right now with me. Yes, the
Andrews and Hunt is a great book, sir. You can refer to it because you already have spent so much time there. I'm sure you'll get phenomenal lead.
Okay,
I really enjoyed programming it there.
Okay, thank you very much.
Okay, any other question?
No, I just want to make a comment. Professor Arobo's talk is an excellent talk. And I should also mention, probably he didn't mention in his slide, he is also an editor for the Random Matrices Journal. And, it shows his contributions. And I just want to comment, yesterday I gave this talk on big data and high dimensional data. And I told at that time that high dimensional data need new techniques to analysis. Old techniques do not apply anymore when P is much larger than N and so on. So this is an example where new techniques are being developed for high dimensional data analysis. So this is just a comment for all of our statistical friends who are attending these lectures. So this is what I mentioned yesterday. For high dimensional data, classical methods do not help. And of course, big data, they don't help at all. And this is an example where new techniques and matrices and random matrices are very useful. And I congratulate Professor Arup Bose for an excellent talk and his great contributions to this area. Thank you.
Thank you very much, Professor Prakash Rao. Any other comment or question to the speaker? Well, if not, let me take this opportunity of thanking Professor Arup Bose for the very thought-provoking and knowledgeable talk that he just gave. I'm sure it will lead a lot of people to the latest work in this area, particularly if you read his books. I'm sorry that I was late in joining the meeting. I don't know what went wrong because, in fact, before the meeting started, I and Arup Bose were chatting exactly on the same channel for half an hour. And then when the time for the meeting to start came, we just couldn't do that anymore. And I wonder what happened. But anyway, all that ends well is good. So we are very happy to have him here. And I thank the organizers of the conference. I thank the organizers of the conference for bringing such distinguished researchers like Professor Prakash Rao and Professor Arup Bose together on this platform so that the younger people can hear their multifarious contributions and important contributions. Thank you very much.
Thank you, Professor. Thank you, Professor Deshpande.
Thank you very much, sir. We are grateful to Professor Deshpande, sir, and also thankful to Professor Arup Bose, sir, for your kind acceptance and enlightening the participants with thought-provoking. Thank you very much from the ISDS and also from the Department of Statistics Organizing Committee. Thank you very much for your kind acceptance, the Professor J.V. Deshpande and Professor Arup Bose. Thank you very much. Now I request all the participants to join the concerned links, session hall A or B or C or D, whichever that you are interested to join, and as per the schedule that is specified. So we will continue in the session halls of A, B, and C and D parallelly. Thank you, sir. Thank you. One and all.
Thank you. Bye. Bye, Arup.
A very good morning to all the delegates and participants present. I am B. Haripriya. It is an honor to introduce Professor S.C. Malik, sir.
Yes, I request you, madam, no need of introduction. Several times we have given the introduction. So thank you very much for this. Without making much time, I have the opportunity to invite Professor Sumesh Kumar. Should I invite?
Yeah, I'm here actually. I'm here, Professor.
Oh, yeah,
Malik.
yes, Professor Sumesh Kumar. Very good morning.
Yeah, good morning.
Okay, so today we are going to start the second lecture in session hall A. In this session, we have the very eminent speaker, Professor Sumesh Kumar. I have a few words about him, although he does not require any much introduction, but it is my prime duty to introduce him with the audience and participants. So Professor Sumesh Kumar, basically a researcher, good researcher in the area of estimation theory. He started his career from University of Jammu and served thereafter served many times or many years, and presently is also working in IIT Kharagpur. He has published so many research papers, and some of these research papers have been published by him in the journals of good repute, like Communication Statistics and some other good journal, Probability and Letters, and some other journals. He is a visitor of various countries also. He has been invited to deliver talks at various levels, international and national levels. And he is a good researcher, no doubt in it. So without taking much time, I request and I also welcome Professor Sumesh Kumar to deliver the talk. I requested to deliver the talk on the topic inference procedures for exponential models with a common minimum guarantee time. So I request Professor Sumesh Kumar to deliver the talk, please.
Thank you, Professor Malik, for giving a very nice introduction about me. And I thank the organizers of this conference, especially the administrative body of Indian Society for Probability and Statistics, as well as Osmania University Department of Statistics, that they have chosen me for this prestigious Hanagal, D.D. Hanagal endowment lecture. Professor Hanagal is an established name in the area of reliability theory, survival analysis, fidelity models, and he has published around 120 papers. So it is appropriate that I speak on a topic which is related to his work, because he has several papers on stress strength reliability. So in the exponential model, I will actually talk about the stress strength model. And so there is a new stress strength index that has been introduced a few years back. And we have done estimation of the parameters and the testing for such an index. So let me share my screen now. I hope I have been given permission for sharing the screen. Let me just see. Yeah. So is my screen visible to all the participants?
It is visible, sir. Yes, we have. No problem.
Okay. So let me start the introduction to the problem. Okay. So as I mentioned that I'm going to talk about a new stress strength type index or a stress strength type measure for exponential populations with common location. So minimum guarantee time actually refers to location parameter in the exponential distribution. The lambda parameter refers to the hazard rate, and if you put 1 by sigma kind of thing, then it is sigma refers to the mean of the distribution, or the you can say scale parameter of the distribution. I'm going to talk about the stress strength type measure for such distributions. And so the initial expressions for the stress strength type measures originated in non-parametric procedures. Actually, if you all remember, all the people who are working in statistics know about the Wilcoxon rank sum statistics and the Munn-Whitney U statistic, which they introduced in 1940s. And their main objective of their study was to compare the probability distributions, that is the medians of two random variables x and y, which are results of two experiments. And non-parametric methods, of course, are applicable in variety of situations as they are distribution free. However, when the information about exact probability models is available, one can construct more efficient procedures. This rank-based procedures of this Mann-Whitney and Wilcoxon, they led statisticians to consider expressions of the type probability x less than y. And then it was realized that this quantity has applications in a variety of industrial problems. So it was related then to the stress strength measure or stress strength reliability measure. So of course, we all know that there are appliances which survive due to their strength. So appliances receive a certain level of stress, but if a stress level becomes high, then the strength is unable to sustain, and the appliances or the equipment, it actually breaks down. So what is stress? Stress is defined to produce failure of a component or the device of a material, whereas the strength is defined as the ability of a component or a device or a material to accomplish its required function satisfactorily without failure when subjected to the external stress. So strength is a failure resisting variable and stress is a failure inducing variable. So we have the essential examples here. For example, if we consider miles to failure distribution of a component in a vehicle. So suppose we say warranty is 1 year or 18,000 miles, whichever is earlier. Then the goal is to estimate the reliability of the component within the warranty period. That means the system should not fail or the vehicle should not develop problems within the warranty period. We can consider the Y as the strength of a rocket chamber and X stands for the maximal chamber pressure. So if the solid propellant is ignited, then this chamber pressure is generated. So probability X less than Y is the probability, or you can say X less than Y denotes the event that the engine will be fired successfully. So probability of X less than Y is of interest. So of course, Gutman et al. And there are examples of such situations. Similarly, we consider the earthquake resistant buildings or structures. So when the earthquake is there, the tremors are there. That is the stress creating variable. And so therefore the structure should be such that it should resist that. We can look at the articles by Esteva et al. So you can look at in all the branches of mechanical engineering, electrical engineering, electronics engineering, in all the branches you have the applications of the stress strength reliability. Some relevant literature I will mention, although literature on the stress strength reliability is very vast. In fact, there is a book also by Johnson, Katz, and Balakrishnan, etc. But I will be looking at certain thing which is relevant to our index. So in 2001, Brunner and Puri, they have introduced in the non-parametric setup. So they considered something called a relative treatment effect. So if you have distribution functions, say for D groups, F1, F2, Fd, then they define a relative treatment measure called integral of GDFI. Of course, this integral is in the generalized sense. In the Lebesgue-Stieltjes sense we are considering. So we call it PI. Here G is the unweighted mean of the distribution function F1, F2, Fd. So this can be considered to be an extension of the usual stress strength reliability. And Brunner and Puri, they obtained many asymptotic results. So this is a completely in the non-parametric setup. For two-parameter exponential distribution with known scale parameters, Paul et al. They considered the estimation of probability y greater than x and its power k, and they derived the distribution of the UMV of xi, and they also considered the test of hypothesis for such a thing. Krishnamurthy et al. In 2007, they have considered the stress strength model in case of two-parameter exponential distributions when both parameters are unknown. And they actually used a generalized variable approach to draw inferences for the parameters and the reliability function. Gao and Alvo in 2008, they considered non-parametric comparison procedures for one-way and two-way layout. And so in general, if you have xijn following fijx, and they considered a weighted average, unweighted average of all these CDFs Fij. So that is 1 by ij double summation Fij. And they consider H star dFij, the integral of this. So that is considered as the unweighted relative effect. So similar thing for one way also they have done. Arilmaj in 2010, he considered a little bit difference in the stress strength. In place of considering simply probability x less than y, he considered some sort of multiples or the differences of this. That means something like probability y minus x greater than something, not greater than 0 exactly. That is dependent upon certain kernel function, and similarly in the ratio also. So he considered that the two states based on the difference in the stress and strength value, and then of course he obtained exact expressions as well as bounds and approximations for the system reliability. So this basically can be considered as a multi-state reliability function, and he derived for the exponential model the maximum likelihood estimator and the UMBUE. He extended this multi-state stress strength reliability system to n components, that is k out of n system also. He investigated various properties of the reliability function, and again for the exponential distributions he considered the estimation of the parameters. Then Huang et al. Considered independent gamma variables with known shape parameters, and they derived the uniformly minimum variance unbiased estimators and compared its performance with the MLE using simulations. And then Krishnamurthy et al. In 2015, they have considered likelihood ratio tests for comparing several independent gamma distributions with respect to shape parameters, scale parameters, and with respect to the means. Then Jana et al. In 2016, they have considered estimation of the stress strength reliability of a multi-state component or of a multi-state system where the states depend on the ratio of the stress and strength variables through a kernel function. And they use the Bayesian approach, assuming the stress and strength as exponentially distributed with common location parameter but different scale parameters. That is the model which we are going to present today. They have considered the multi-state model, and they considered estimation as well as the confidence interval procedures. Then Quinn et al. Considered only the scale model for the multi-state stress strength reliability, and once again they have considered the base estimation and also the UMBUE, MLE, and other things. In the non-parametric setup, Brenner et al. Considered ranked-based procedures, and they considered inference on the relative treatment effect, that is PI, that is integral G dFi, where G is the unweighted mean of the distribution functions F1, F2, Fd corresponding to the D groups. So if we represent it in the form of a probability, then it can be represented as probability of Z less than Xi1 plus half times probability Z is equal to Xi1. So Z is actually a hypothetical variable with a distribution which is following G. So note that we have samples from the D groups, Xi1, Xi2, and so on, Xi from the ith group. But a new distribution is constructed, which is actually the unweighted average of F1, F2, Fd, and based on that, a hypothetical variable Z is considered. So this Z can be considered as that the mean, you can say, how much your individual components or individual systems are having strength more than the average stress kind of thing. So, or you can say average strength. So which one are better than the average and which are worse than the average. So this measure PI for P1, P2, PD, this will give the actual emphasis that which systems are stronger, which systems are weaker. So later on, Krishnamurthy et al. In 2020, they have considered comparison of two parameter exponential distributions. So they have given the likelihood ratio test for comparing location, scale, and homogeneity of the distributions. They also proposed an iterative test based on an idea by Shah and Rathod 1976. Then recently, Jana et al. In 2021, they have studied the estimation of stress strength reliability for two exponential distributions with different location and scale parameters. So they derived the maximum likelihood estimator, UMUE, and the base estimators. They have done the confidence intervals using a generalized variable approach as well as bootstrap approach. So let me introduce the model here. We have K populations. So ith population is having the location mu and the scale parameter theta I. So we assume in general that theta i's are different, and this location parameters mu is common for all the populations. So it is basically common minimum guarantee time for K exponential distributions where the rates may be different or the hazard rates are different. So we consider this mixture of this F1, F2, Fk. So if Fi is denoting the CDF of Xij, we take 1 by K sigma I is equal to 1 to K Fix. And we consider a hypothetical random variable Y following Hx. And we consider this probability of, so here you can see I have just interchanged the order. Here it is written probability Z less than Xi1, but we have just taken the reverse of it. So what does it mean? That means the system has less strength than the average strength kind of thing. In the discrete case, the second term is also important, but in the continuous case, the second term will vanish. Therefore, we are then finally restricting our attention to probability Xij less than Y. So 1 minus Pi becomes probability Y less than Xij, which is actually the original measure which is introduced by Brunner and Puri and Brenner et al. Okay, so of course in the statistical inference it doesn't matter because 1 minus whatever things you are getting, it is just that thing. So for our model, when we calculate this index, it turns out to be some constant, and then you have terms like sigma theta I by theta I plus theta j for j not equal to I, this summation. So for the ith component, this is the thing. So you can write for P1, P2, Pk. So our interest is to consider estimation of PIs as well as doing certain testing problem for the PIs. In particular, for example, the homogeneity test. Now the complete sufficient statistics in this particular problem, it is the minimum of all the observations, that is capital X, and T1, T2, Tk, where Ti is the difference of the ith sample mean minus the minimum of all the observations. Okay, so then this X, T1, T2, Tk is a complete sufficient statistics for this problem, and its distribution is available. The only difference from the basic problem, like when we have mu is equal to 0, in that one and this one, is that here the distribution of the complete sufficient statistics is not having an independent structure. In fact, the distributions of T1, T2, Tk are correlated. However, the distribution of that has been worked out, and of course, when we do the calculations, we have to make use of that. Of course, deriving of the maximum likelihood estimators is not difficult. So the maximum likelihood estimator of mu is the minimum of all the observations, and the maximum likelihood estimators for theta I is theta I, that is equal to Ti. So based on that, we have the MLE of the Pi function, so which I call Pi MLE. Then secondly, we also consider a base estimation for this problem, and for theta i's we consider inverted gamma priors. Okay, so we have considered g theta I, where the inverted gamma prior is taken. So you can see here that 1 by theta I has come here, and the scale parameter is beta I, and some shape parameter alpha I is taken. That means basically 1 by theta I as a gamma distribution. And for mu, we consider some sort of shifted exponential distribution, and we make it dependent upon this theta is here. So basically, the complete prior distribution of thetas and mu, it is g theta 1, g theta 2, g theta k into g mu given theta. So this is the structure of this distribution. So here there are a lot of hyperparameters, that is lambda, xi, alpha I, beta I. So these are all hyperparameters of this problem here. Then anyway, the usual calculations can be conducted. That means you can carry out the posterior distribution and then you calculate the base estimator. So the base estimator is here, it will come as the these constants will remain as such, and here you will get the posterior mean of the terms which are appearing here. These calculations are little bit complex. I'll just mention here the final expression which is given in this particular form. So here this delta 1, delta 2 which are coming here, they are actually consisting of infinite series involving the hypergeometric functions, and here gamma functions are coming into picture. We observe here that it is possible to actually consider a simplified version of these estimators if I take limit with respect to the hyperparameters in some sense. So for example, if I take alpha I is going to 0, beta I is going to 0, xi eta going to 0, then the limit of base estimators can be derived. In decision theoretic point of view, this limit of base rules is helpful provided it becomes this itself becomes a generalized base estimator with respect to certain prior, because then one can attempt to prove that it is an admissible and minimax estimator. So what we did, we again actually tried a improper prior here. So for theta and mu, we take this prior distribution, which is actually obtained as a limit from the original prior distribution that I have considered just before this one. Fortunately, it turns out that the usual mathematics works here, and the posterior distribution becomes a proper probability distribution, and therefore the base estimator with respect to this generalized prior can be calculated. And actually we get this result here, that is the generalized base estimator with respect to this particular prior is given like this. And this is the same as the expression which is obtained as the limit of the base rules. So what we prove here, that the limit of base rules leads to a generalized base estimator here. So this is a good theoretical result, and actually proving that now this estimator is minimax and admissible, that work is still in progress. I mean, we have not been able to prove it because it is somewhat complex mathematical problem. So it is still an open problem, and we are working on that. Then the next one is that we try to consider the improvement using equivariance. So the group of invariants we can consider. So initially we have considered some simple forms here. So we get this particular form as the, I'll just mention to you, yeah. If we consider the UMVUE of θ1 based on all the samples, then we need to consider the expectation of Z1 given T, where this Zi's are actually Yi minus Xi's. So if we consider this, we are able to get the form of the UMVUE. So here you can see that there is, it's some constant times T1 plus something. So what we do, that in order to consider scale multiples, we can try to improve that what is the best choice of C. Fortunately, here the calculations work out. We get the minimizing choice here, but the minimizing choice depends upon the parameter. Then we are able to actually get the minimum and the maximum of that, the minimum and the maximum are evaluated like this: n minus 2 by n minus 1, and maximum is n by n plus 1. So we have the following inadmissibility result for such estimators, that delta 1u is improved by delta 1u star for C is equal to n by n plus 1 as n by n plus 1 is less than 1, and the improved UMVUE of θ1 is obtained like this. So we are actually able to obtain this particular estimator. Then the next one is to obtain the uniformly minimum variance unbiased estimators for the original parameters themselves. That means for P1, P2, Pk. This requires a little bit of complex distribution theory, Fortunately, here we are able to work it out. So let me mention here that we need to calculate the conditional expectation of xj given xi with respect to the complete sufficient statistics. Now, in this particular case, because it is dealing with the indicator function, it reduces to the probability only. So the uniformly minimum variance estimator of pi, that is 1 minus 1 by 2k minus 1 by k plus this summation and individual component, that is theta by theta I plus theta j. If we substitute the individual UMVUs, then it will give, because the sum of the UMVUs is an UMVU. Now these terms require the calculation. This is little bit complex, but we are able to break down this conditional distribution into certain parts, and then we are able to carry out the calculation. So I will skip this portion and present to you in the equation 7.2. This is the uniformly minimum variance unbiased estimator for this particular case. We consider another group of invariants here. We consider the scale group of transformations. And under the scale group of transformations, the form of an equivalent estimator is T1 into a function of W1, W2, Wk minus 1, where W1 is T2 by T1, W2 is T3 by T1, and so on. So we consider the conditional risk function of this estimator given W, and then we minimize with respect to this function psi here. Then the minimizing choice of psi, it will depend upon W, mu as well as theta. And it is turning out to be theta1 into expectation of T1 given W and divided by expectation T1 square given W. Fortunately, the distribution theory of calculation, this conditional distribution and conditional expectation can be worked out. We are able to successfully do that. And we obtain this psi head function as 1 plus summations wi xi I by k, where xi i's are theta 1 plus by theta I kind of terms. So we can actually obtain the minimum and the maximum value over the parameter space, as infimum as 1 by k and the supremum as of course infinite. So that has no meaning. I mean, it doesn't help here, but the minimum actually gives you a complete class result, that if there is an estimator such that probability of psi w is less than 1 by k is greater than 0, then the estimator delta psi is actually improved by delta psi I, where psi I is defined as 1 by k if psi w is less than 1 by k, and it is psi w otherwise. So this is a complete class result. We considered another group here by introducing C on each of them. And again, let me just, I think because time is short, I will just go to the result here. Yeah. So again, we get the minimizing choice, and this minimizing choice is a function of u, w, mu, and theta. And we are able to apply certain argument to get the minimum and the maximum. So maximum is of course infinity, but the infimum is also not giving any result. So that is 0. So the complete class result is not possible for mu greater than 0. Now we consider mu less than 0. In this particular case, the infimum is a non-trivial quantity, that is n by nk plus 1 into u plus 1. For u less than 0 also we get similar type of term here. And therefore we are able to prove the following theorem here, that for a given choice phi, if I define phi iw as n by nk plus 1 u plus 1, if phi w is less than this and phi w otherwise, and if the probability of this set is positive, then the estimator delta phi I improves delta phi. So we are actually able to get a complete class result for the scale invariant estimators here. Then of course we have carried out the numerical computations here for comparison the mean squared errors of the various estimators that we have given here. We have improved the MLE, we have the generalized base estimators, and so on. So all these estimators have been compared here, and we can show that the MLE performs better than the UMVUE, but if eta 1 increases, then UMVUE performs better than the MLE. maybe I think I have to skip this. Professor Malik, how much time do I have?
You can continue, sir.
Okay. Yeah. So I mean, these are the actually outcomes of the numerical study. Somewhere we have got the generalized base estimator performs better than the MLE. If we increase eta 1, then the MLE performs better than the. So we have done a comprehensive comparison here. So of course, this is presented in the graphs here. You can see here the UMUE is performing very well in this big region here. In this region, you can see that the generalized base estimator is performing better, and so on. So all these outcomes have been worked out. Maybe I will not need to read all of this. I'll move to the asymptotic distribution. So we actually employed the delta method, and we are actually able to obtain the asymptotic distribution of the MLE also. So the delta method is that if we have a sequence of random vectors such that root and t minus theta converges to normal 0 sigma, and if g is a function which is of course having partial derivatives, etc., then the square root and gt minus g theta converges to normal distribution with a certain covariance matrix, which is given by this term here. So in our particular problem, actually we are able to establish that and prove that thing. Okay, so we are also just mentioning here that if I consider the hypothesis of homogeneity of the these relative treatment effects, that is P1 is equal to P2 is equal to Pk, in this particular problem the hypothesis reduces to equality of the means, and we have actually considered several tests here, including the Waltz test, because Waltz test, of course, because asymptotically you get a chi-square distribution, so that has been done. And we have also implemented it on a real data set. The real data set is about the percentage energy intake for 3 different categories, that is for IL crops, pulses, and tree nuts. And we considered from 170 populations across the countries. And we carried out the chi-square goodness of fit test, and we divided the population size in 8 intervals to get the corresponding frequencies. And we conclude that each group is exponentially distributed with level of significance 0.05. Then from these populations, then we take random samples of size 20 for each category. So of course, for the purpose of implementation, we have taken equal sample size. But of course, you could have taken unequal sample size also, because the population data we have taken from there. This is the summarized data, that is the sample means and the sample minimums for the 3 groups here. And then we are able to calculate this MLE, UMUE, generalized base, plug-in UMUE, improved UMUE, and the plug-in BSC. These are the values of the estimators here. And since the estimated value of P1 is greater than half, it means that the random variable generated from the energy intake in IL crops is more than the random variable generated from the mean distribution. Whereas in the case of pulses, the random variable generated from the mean distribution of energy intake is higher than the random variable generated from the energy intake present in the pulses. And the estimated value of P3 is nearly half, but slightly less than that. So that means it is statistically, we can say that it is almost equal to the percentage energy intake in random variable generated from the mean of all the categories. So this is actual implementation to show the this relative treatment effect measure here. Then for the testing part, we have actually done a thorough thing. I mean, earlier I just now mentioned the Waltz test, but then we considered it as a full-fledged problem in its own. Some of the tests which are already available for this one, we have done a comprehensive study of the comparison of the size and the power using the parametric bootstrap here. So the tests which are available, that is the likelihood ratio test, then the asymptotic likelihood ratio test, a heuristic test which is based on the principle of the union intersection test of Roy. Then in the non-parametric setup, we have Kruskal-Wallis test, the asymptotic version of that one, and then the 3 non-parametric tests which have been proposed by Brunner et al. So these are the calculations. I will not be reading all these things because the form of the likelihood ratio test statistic can be derived here. And this is the algorithm for doing the parametric bootstrap for this one. That means we generate samples from the original population, then we estimate the parameters of the original population, and then we derive the bootstrap sample from the estimated distribution. Based on that, we calculate the critical point, and through simulations, then we estimate the size and the power. Same thing we have done for the asymptotic test and the heuristic test, which is based on the maximum divided by the minimum of these values there. And the non-parametric test, one is the Kruskal-Wallis test, which is of course the standard test, which is known to all of us. And then there is asymptotic distribution of that, that is the chi-square. And then the three tests which are proposed by Brunner et al. So these are the tests which are given here. For this, they have to write the hypothesis in the form of a linear transformation. You can say the relative contrast here. This contrast matrix is 1 minus 1 0 0 1 0 1 minus 1 0 0 0 0 1 minus 1 etc. The estimators of the relative effects are pi head is equal to 1 by k sigma w head li, where w head li is given by this. This Rij li is the rank of Xij among NL plus Ni observations within the two samples from the Lth and the Ith group. Then they have suggested that we should use a matrix like C transpose, CC transpose, generalized inverse into C. And based on that, the test function has been constructed. Let me just give the test function here. Yeah, this is the QNC statistic or QNT statistic, that is n by trace TV and head, P head transpose T P head. So basically what we have to do, that for exponential distribution, we have to decipher this thing and implement it. Here, three different choices of these functions are taken. That is given by the equation number 14.7, 14.8, and 14.9. And we actually implemented the parametric bootstrap approach to implement these tests. We calculated the critical points for given sample, and then we estimated through simulations the size and the powers of this. Okay, so these are the power comparisons which are given in the form of the tables here. And you can see that the test based on the likelihood ratio, and the heuristic test, they are performing better than the non-parametric test.
Professor Somesh, please confine the topic.
Yeah, sure,
Yes,
sure.
We are getting late. Yeah, please.
Yeah, we have come to the end of this one.
Yeah, please.
So let me just summarize what we have done. We have considered a new stress strength index, which is again motivated by a non-parametric setup of a relative effect. And so we considered for the parametric setup of the exponential populations with common location and different scale parameters. We have carried out the full estimation. That means we have considered the maximum likelihood estimator, UMUE, the base estimators, the generalized base estimators, and we have proved certain inadmissibilities and got improved estimators. Secondly, we have done the testing comparison of the existing likelihood ratio test, the union intersection test, and certain non-parametric tests here. So this is a quite comprehensive study. We have now extended this study to both the parameters are unequal and unknown, and also the scale parameter is common. So this part we are still doing, and we are working on this thing. Thank you. I think with this one I will end up here.
Thank you, Professor Somesh Kumar, delivering a nice lecture. And that is David Henninger endowment lecture. So I request the audience, please, any query they can ask. Yes, any question from the audience, please.
Professor Deshpande, I think he is asking some question.
Yeah, please.
His voice is not coming. His voice is not coming.
Yeah. Oh, Professor Deshpande, we are not in a position to hear you. Is there any technical problem in the voice? Voice is not coming to us.
Yeah, sir, I think your connection, there may be some issue.
Yeah. Still, okay. So, okay, if there is no, any other question from the audience?
Deshpande sir, are you using a headphone? Please remove it once and then connect it.
Okay. So if there is no question, let me thank Professor Somesh Kumar for delivering the nice lecture. Thank you very much, Professor Somesh Kumar, to be here. Thank you very much.
Thank ISPS and Department of Statistics for giving this opportunity. Yeah.
Yes, thank you, please. Thank you. I hand over the to the organizers.
For chairing the session. The next.
Sir, this is Professor Jayashree from Osmania University.
Madam, mute.
Now, I request Professor Somesh Kumar sir.
Yes, in holidays they are
To invite for chairing the session.
Yeah. Good morning to all of you. It is my privilege to.
Small announcement, sir.
Yes, please. Yeah.
So 11 to the 12 sessions are 2 speakers are there. Actually, one speaker. The first speaker is Professor D.S. Huda, and the second speaker is Professor Ravanan sir. This Professor Ravanan sir talk is shifted to 5:35 to 6:10. So due to sir is having some the emergency work, so it was shifted to this one. Now we are having only one talk now in this time. That is Professor D.S. Huda sir. So we are having the times here. Then only the contributory paper session will start. Now handing over to Professor Somesh Kumar sir, Professor of IIT Kharagpur. Thank you, sir.
Yeah. Good morning. It is my privilege to chair this session on the design and analysis of experiments. And Professor Huda is the speaker. And of course, Professor Huda does not need much introduction in this community. He is very well known. And since we are running a little bit late, I would request Professor Huda to start so that we can actually hear him more. I request Professor Huda to share his screen and present his lecture. Professor Huda.
Yes, please. Are you listening me?
Yes, yeah, we can listen you. You can just make it a full slideshow or maybe full screen kind of thing. Yeah.
Yes. Is all right?
Yes, we can see it. Yeah. Yes.
Chairman of this session and friends, I feel privileged to be here to deliver a talk on estimation of missing data in design of experiments and contingency table. Main points of my talk will be firstly introduction, a brief introduction, estimation of missing data in design of experiments, an algorithm method for estimation of missing data in fuzzy matrix, estimation of missing data in contingency table, and then conclusion. Actually, missing data in design of experiment contingency table causes incomplete information, which leads to more ambiguity in decision-making process. Thus, to estimate missing data is important and challenging also. And this, everybody, I think, well acquainted what is contingency table. When one attribute has the missing, just like M students, and there are n papers, and each students have the marks in each paper, then it becomes, and then sum total is also row total and column total is also given, then it becomes a contingency table. Actually, contingency table is represented like that. This is like that. A is some attribute, B is corresponding attributes, and this is row total, and this is column total, and this Yj is called Ij cell, which represents the frequency of the characteristic of attributes A and B, where Ri and Cj are marginal and columns, and T is the total. Actually, this is about the, I think, nothing to be tell contingency table. A decision, actually, summation values, what is used for decision making purpose? Summation values are used for decision making purpose, but missing value remain unknown. So this is very interesting. And in a contingency table, and you friends, mostly data is represented in the matrix form or contingency table. And contingency table is also one kind of the matrix, because if you living rows and columns, then this becomes a matrix. And this matrix, when actually the method of finding the missing value to contingency table is equivalent to find the missing values or estimate the missing values in a matrix. Here, you see there are two contingency table, design of experiment and contingency table. I have dealt with. Design of experiment has been dealt by statistician already, is very known. But to estimate in a contingency table, very new, and this is very new research. And that is, firstly, what we do, contingency table is living rows and columns. We take this matrix inside, and that matrix is converted to fuzzy matrix. And we have developed a technique of how to fill up, how to estimate the missing values in a fuzzy matrix. Very, very interesting. And you will see, just like first thing, I will let you know a brief field of experiment. The plots are designed in different blocks before administering the field of experiment. Friends, in agricultural statistics or in a research in agriculture is done by the field of experiments, and this is, they are using design of experiments. And in one or more observations are missing due to natural calamities or by a pest or eaten by the animals, it is cumbersome to estimate the missing value or values in the field trial, as it is practically impossible to repeat the experiment under the similar conditions, because in agriculture research, we take the weather, temperature, everything is counted, and it is not possible to repeat the same thing. So, keeping this, the statistician Yates suggested a method. They have estimated the missing values. I'm not going to so much in this yet, already known. And another method was developed by maximum entropy principle method, we can say. And that was studied by Professor Jain Kapoor and Kesavan. And they also think, but this is second method is Kapoor and Kesavan, which yields X is the missing yield. We obtain the maximum entropy estimate for X by maximizing this. This is, you must be knowing, this is entropy, and Shannon's entropy. And taking X as a missing, adding that, all Xi's we are given already, Si's are known, X is unknown. Then we estimate by applying this maximum entropy principle, and that will come out to be x1 raised to power x1, x2 raised to power x2, and this raised to power 1 by t, 1 divided by t, and t is the sum total. And you must be knowing this is known as maximum entropy mean of x1, x2, x3 up to xn. So this is why entropy principle, and we estimate is x, unknown is x is known. Suppose two are missing, and x and y are determined from. Firstly, we take like that 1 divided by t plus y. Y will be taken 1 divided by t plus x. And solution will be, both will be the same. Both will be the same. So this is the defect, that the values value will be coming the same in all. And there are other drawbacks also. X is rather unnatural. In fact, x is always greater than the arithmetic mean of x1, x2, x3, xn. And if two values are missing, the maximum entropy estimated for each is the same as given by, just like I have done. And that is why it is not very useful for estimating missing values in design of experiments. But it is very useful. I will explaining the method in the contingency table. However, those drawbacks can be overcome by, instead of taking Shannon's entropy, we take some other entropies, Burger's Burger's entropy, and other generalized Rennie's and all others. You see, if we take those, then it can be improved. But however, second drawback is understood by the information theoretic estimate for a missing value depends on actually the missing value, the information available to is the purpose for this missing value is to be used. Third drawback, as according to the principle of maximum entropy, we should use all the information given us and avoid the scrupulously using any information not given to us. But in design of experiments, we are given information about the structure of the design being not used in estimating the missing values. Consequently, estimate is not accurate. However, the method defined in section 2 can be applied to estimate the missing values, as in contingency tables, where the value size is to be chosen to minimize the measure of dependence D. So, as I told you, in contingency table, we have developed a method on fuzzy matrix. And firstly, we must know the method of estimation of missing values in fuzzy matrix. Second part will be then taking contingencies matrix, leaving rows, sum total and column total, row total and column totals, that is the matrix, and then we change into fuzzy matrix. This I shall explain how we do this, and this is very accurate method. And this work has published in very good journal, Springer Journal, and very recently, 2020. Let us consider, if firstly I will explain how to estimate the missing data in fuzzy matrix, and this will be applied in contingency table. And everybody must be knowing, I think, fuzzy matrix. This is very simple. Then a matrix, you must be knowing, have the its entries belongs to 0 and 1, close it, including 0 and 1, and between 0 and 1. Then this is known as fuzzy matrix. And Vasanta Kandaswamy was the person who gave this idea of the fuzzy matrix, and this is very simple and has been applied to many social and natural situations. Myself and my student defined maximum, minimum, and minimum max binary operations on a set of fuzzy matrices and proved that the set of fuzzy matrices is a lattice under these operations. Now I am giving the algorithm for estimation of missing data in fuzzy matrix. Now let UE, having the entities HIs, U is the, you see the first attribute, E is the second, U just like U is D1, D2, DM, E is E1, E2, En, and then we have the fuzzy matrix and having some missing values where U is this, E is with the corresponding values of another attribute. Each missing value in H is denoted by star in the tabular representation. Now we explain an algorithm for estimating the missing value star in H, which is analogous to algorithm. And this method was actually firstly was given by in the soft matrix. We have, and soft matrix was given Pongman and Anziganolu. We have given in simple fuzzy matrix. That we have improved that method by giving in fuzzy matrix, simple fuzzy matrix. Mean value of xj. First step, mean value xj for each attribute ej. Ej attributes E1, E2, E just like, and I am taking xj mean value and is computing xj just like first column divided by the total usage. That will be the hi, that is hij. I is given 1 to m, and then uj is this. Then we take this xj. Average distance of each entry xij from xj. What is the average distance from? This is, you understand, you see, this is the mean value xj. And suppose you are to take the first column. First column, you add them and all values in the first column and divide by the number of the users, leaving the missing data. Naturally, leaving missing and missing number that will not in counting user will also it will not be counted. Then we take this xj. Average distance of every hij from the mean xj is taken. In xj, the average will be taken xj minus hij. Every value we subtracted from that and take the summation. That will be known as average plus value. In the same way, it will be taken minus also. You see, and the pair of distance information, dxj plus as well dxj minus. Dxj plus will be xj plus d average, and dxj minus will be xj minus d average xj. Next step, xij, j is equal to 1 to n for each di, I is equal to 1 to m is compared with the mean xj, j is 1 to n, xij, 1 I goes from 1 to m, and let nl be the number of count for which xij is less than xj, and nj be the number of count for which hij is greater than xj for the corresponding attribute value ej. J is equal to 1 to n. This will be illustrated by the example. Utilizing NL, after finding these values, that probabilistic weights WL and WG of each object's DI is determined, and as just like WLI is equal to NL divided by NL plus LG, WGI NG divided by NL plus NG. And the unknown or missing entry in the fuzzy matrix of attributes value EJ is computed as this will be multiplying xj plus by wgi plus dxj minus into wlj, where hi is star is equal to this. So this will be illustrated by now in contingency table, how to, as an example also, and in contingency table we shall be using this algorithm. And now I consider the contingency table, how to develop a method for estimation of estimate data in incomplete contingency table. Hence, when there are missing values, then it is known as incomplete by applying the algorithm proposed just like in section 3. The contingency table can be transformed to fuzzy contingency table on dividing by the largest entry or any convenient value near to the largest entry. This is one step. Then let X, Oij, M into N be the contingency table having missing data in some rows and columns with their corresponding marginal row and column sum totals are also missing in such a way that it is not possible to estimate any of these values. It is not possible to calculate actually by any way. Then these are the steps. Step 1, consider the incomplete matrix of rows and columns. We consider leaving rows and columns, sum totals of rows and sum total of columns. Then this is incomplete matrix. And divide each entry except the missing entries by the largest or any convenient value near to the largest. Apply the algorithm. Near to the largest means that value will be greater than the largest, because otherwise if we see less, then this value becomes greater than 1. But the value should be lying between 0 and 1. Apply algorithm method proposed in section 3. Just like this is the method. Now I will illustrate by the example. Let us consider the following incomplete contingency table for estimating of the missing value. This is the example. There is, you see, we are taking, and these are the missing values. And friends, you can see that they cannot, missing value cannot be calculated, cannot be estimated by any calculation. Now, except our method which we have developed. Here we consider the incomplete matrix. Because this is the incomplete matrix, just like leaving this becomes the incomplete matrix. Only for of rows and columns of the following contingency tables. Just this is the incomplete matrix of contingency table. We divide each, because you see, which is the maximum, 25. So we divide by 25. Any value, suppose we have here 24 instead of, then also we can divide by 25, because it is easy to divide by 25 and then 24. So that's why it can be taken either greatest or greater than the greatest, near to greatest. But that should be the near to greatest. We divide each entry by 25. Thus, we get the following incomplete fuzzy matrix. We get this. If you divide, we get this becomes incomplete fuzzy matrix. Now, mean of Vj, just like mean of B1 will be adding this, divide by 4. B2, mean of B2, adding this 3, divide by 3. This is divide by 2. Adding this, divide by 2. In this way, so this will be called x1, this will be called x2, this will called be x3, this will be called x4, this will called be x5. So these are the mean values of this. Next. Now D average of x1. That was the average was xj was decimal, x1 was decimal 48, and subtracting that value from that value and take the mod values and divide by the number of that will come out to be decimal 26. In the same way, x2 is the average x2 is taken. This is the value actually x2, and subtracting from each value given value, not the missing value, because we don't know the missing value, and divide by 3. And in the same way, here is 2. Other are missing, 2 are missing, so this is D, and D4 and D. Distance pair. Now we take distance pair, and just like dx1 plus, and this add, and here subtract. Because we subtract this, we have found out x1 average, x1 average was decimal 26, decimal 26, and then we add, and in this is subtract, and hence dx plus dx minus is decimal 74, decimal 0.22. Similarly, other distance pairs are computed as on the same lines. dx2 plus dx2 minus will be coming to this, and this value will be coming this, and dx4 dx minus will be coming this, and so on and so forth. Now, step 6. Now compare O to J, just like, because A2, you see in our matrix of contingency table, you see that A2, in front of A2, there is O to J. J is 1, 2, 3, because in the first row, there is no missing value. In the second way, there is a missing value A2. In front of or A2, there are missing values. They are B1, B3, like that, and all this. So that's why. So in that, as shown in algorithm step 4, table 4, B1, this is O21. O21, because first, what they means, the second row and first column. This is entry which is less than x1. We have to compare how many of them. Oh, sorry. Yes, how of them are less than x1, how many of them are greater than x3 in a row. So O21 is less than x1, and for B3, O23 is greater than x3, and H4, this is less than x4. Hence, how many? This 2 are less and 1 is, and 2 are greater, 1 is less. So NL will be 2, NG will be 1. And probabilistic weights corresponding to the value of attributes A are calculated 2 plus 1. 1 divided by 2 plus 1. So this WL2 will be 2, 3, and WG2 will be N2, L3. This is corresponding to A2. This. So
you can use your mouse actually to move. Yeah. It has actually gone inside the equation, your cursor actually. So you can just click on outside. Yeah. You can go to the right scroll. You can go to the right scroll. Yeah.
no,
You can press F5 also.
F5. It is
F5.
all right. It is all right. Just see, from that probability weights we have found out 2 by 3 and 1 by.
Huda sir.
Yes. Next.
F5 press karo sir. F5 to puri screen aa
Now the
jayegi na,
unknown
slide show.
entry O22 is table 4 is computed like that. O22 dx plus into WG2 and dx x2 minus into WL2, and this will come out to be 0.33. Similarly, other entities are also estimated. This O22 was missing, you must know. Another entry was missing O23. O23. Another was O33. And that has been found out by this method. And next, multiplying each one by 25. Because we have divided by 25 every value. What we have estimated, this was the line between 0 and 1. Then we multiply 25 and we get the missing data by approximating to the integral value in the table 2 up to 2 decimal as given below. This will come out to be O22 8, O24 10, and like that. Finally, putting these values in table 2, we obtain the following complete contingency table as this is the contingency table. Hence, this is very, it looks very simple, but first time this idea has come and how to do was a research point. And this is a work, this is a innovative and very novel also, recently done, published, and it can be used in practical. The estimation of missing values is very important area in many fields of research like agriculture, economics, science laboratory, and data management. Because data can be, you see, maybe rubbed by someone due to some reasons, and reasons can be many. When observed values are found missing due to climate conditions or any other reason, and it's very difficult to repeat the experiment. For example, the field trials of agriculture cannot be repeated. Then there is a need to predict or estimate these values. And various scientists and technocrats have suggested different methods, as I have explained also, like maximum entropy method, Kapoor and Kesavan, and that have been played in a better role than Yates. Kapoor and Kesavan method was better than Yates method for estimating the missing data, and you can judge whether our method is better than already two methods are known. You can see in my opinion, that's our is much better because we have given accurate values and different values. Contingency tables, because contingency the very good applications. You see the contingency tables have applications in economics, agriculture, medical diagnosis, laboratory and data management to study independence of attributes. Kullback discussed contingency table from MDI principle point of view. Hu and Kullback used a similar approach to discuss interaction in multidirectional contingency tables. In the present talk, we have given a novel method of estimating missing data in contingency table, and that has been described by applying logarithm of estimating missing values in a fuzzy matrix. The simple idea was how to convert this in a fuzzy matrix, and that has come to your mind. And you see, it's very simple algorithm and has been illustrated with a numerical example also. It is hoped that this technique would find applications in economics, laboratories, data analysis, and data management. And these are the references you can see. And now, any query, any question, you are welcome.
Yeah, thank you, Professor Huda, for such an interesting and new method for estimating the missing values. Firstly, I would like to invite comments from any of the audience. Any of the participants would like to ask any question to Professor Huda. Then you can ask, switch on your mic and ask the question. Okay, so if there is no question, let me firstly ask one question. Sir, so this method which you have told, it is based on, I mean, basically from a fuzzy matrix, this idea has come. Is there any method of comparison that if this method is used, or any of the previous method like maximum entropy method of Kapoor and Keshwan, or the earlier methods of estimation which were given by Yates? How to compare? I mean, what is the criteria for comparison?
No, actually, already I told you that method has the drawbacks, and it has no drawback. Actually, they have the same values comes, and that has been done only. You see the in one case that is known as maximum entropy mean value, that has been determined, but that is not so accurate. This method is more accurate. Rather, till now, I can say this is very accurate.
Okay.
And applicable in such a situation. But this is firstly thought fuzzy. But the idea came, high contingency table, it may not, firstly, actually, it was studied in the fuzzy soft matrix by Surjit and all this. This idea came to me, can we do the problem of contingency missing values in contingency table? Or you see, design of experiment is also one type of that matrix. That is also because data is arranged in matrices mostly, all contingency tables. So actually main is the matrix. So I thought actually the background is that why it cannot be applied in contingency table, and ignoring like that we have developed. This is the background of this one.
Thank you, Professor Huda, for such an interesting and exciting talk.
Here, sir, 1 minute I will say. Actually, what I have done the research, my research is very simple, but have a good values. So research is not, you see, not simple calculation and all this. I have 135 paper published. Most of the papers are of this type. No, very simple. And my students are so jolly. They are always accept, oh sir, very simple and very, very important. So
yeah, research is of two types. One is that we can put a lot of hard things, difficult things, but the other is that it should be understandable to all and it should be implementable. So
Yes.
both approaches are fine. Yeah, I know your student Parmil, so he is a nice guy and a very nice and happy person. So,
so nice for your compliments. Anyway, I have finished in time.
yes.
Or before time.
Yes. So if there is no other question, let us thank Professor Huda for such an exciting talk. And I hand over the session to the organizers.
Thank you, sir. Thank you for chairing the session. I thank the speaker, Professor D.S. Udagar. And now I request Professor D.S. Uda to occupy the chair and conduct the next session of contributory papers on design and analysis of experiments. Sir, actually the time will be from 12 to 1:40. So meanwhile, we also, because already another 15 minutes is another 10 to 15 minutes is there. So you distribute the time as per depends upon the number of members that are present, and please I request you to conduct.
Yes. So have you break or 15 minutes or not?
Shall we continue, or as we wish, sir? If you want, we'll give the.
No, there should be a break. Let us have.
Otherwise, we will continue it.
As you say.
If you need a 10 minutes break that you can give, otherwise we can continue, because we can give the more time to the contribution, 1 or 2 minutes that you can give.
Okay. No, okay.
Because we will check also, I will ask the members how many members are present.
Okay.
The row column designs for 2-level, Sukanta Dash, is it present?
Yes, sir. I am here only.
Amin Sahib? Anusha?
Yes, sir. I am present.
Deepti?
Yes, sir.
Okay. Ajanta Rudra?
Yes, sir. I'm here, sir.
And Chiranjeevi? Victor Babu? Sir, Victor Babu garu? T. Shekhar Gaut? And there is another paper is also there, sir. Number is 200. The classical analysis of two-way analysis of variance with the replications under fuzzy data by Rahul.
Yes, sir. I am here, sir.
Yeah, most of them are present. You can start, sir. The request for DS would also share and will conduct the session.
Okay. So first,
row column designs.
Serial number 86.
Yes, sir.
Who is presenting?
Sir, myself, Dr. Sukant Das.
Okay.
Yes, sir.
Okay, then.
Shall I share the screen, sir?
How many speakers are there? 7. And now 1 hour. How many minutes? 10 minutes presentation?
10 minutes that you can give.
Okay. And 2 minutes for discussion.
Yes.
Okay, let it be like that. Yes. Yes, please.
My screen is visible, sir?
Yes.
Okay, thank you, sir. So, respected chairman and dear colleagues, a very good afternoon to all. The topic of my presentation is row column designs for two-level fractional factorial experiments. So, heterogeneity in the experimental material is the most important problem to be taken care of while designing of physical experiments or scientific experiments. Coming to the row column designs, as you know that when heterogeneity is in two directions in the experimental material, these row column designs are useful. And if more number of factors are to be studied simultaneously in this row column setup, that is row column designs for factorial experiments. These two-level factorial and fractional factorial designs are widely used to identify significant factorial effects in agricultural as well as in industrial processes. But in some experimental situations, due to cost and time consideration, it may not be possible to run a design for estimation of all the factorial effects. So considering these limitations, many researchers develop different procedures for obtaining row column designs in two rows for estimations of main effects and two-factor interaction effect. That is, here the experimenter is not interested in all the factorial effects. He is only interested in main effect and two-factor interactions. Also, when number of factor increases rapidly, it is desirable to consider a fraction of the complete factorial setup to handle such type of situations. Now, accommodating small number of blocks is especially challenging, and it is not always possible to set up a design without confounding some factorial effects of interest. In these aspects, a little work is available in literature to construct designs in fractional replicates in block conditions for block size 2, where some of the references are here. But coming to the row column setup, construction of this row column designs in two rows, which permit orthogonal estimations of all the main effects and two-factor interactions in fractional factorial experiments may provide experimenter a greater benefit in conducting such type of experiments. Hence, by looking to the above situations, it is desirable to develop a construction method to resolve the problem as mentioned above. Hence, this presentation focus on construction methods to obtain row column designs for two-level fractional factorial experiment in two rows, where all the main effects and two-factor interactions are estimated. Here, interest is to estimate all the main effects and two-factor interactions in minimum number of columns. Also, a catalog was prepared under proposed method of construction for half replicate of 2 to the power n factorial experiment for any number of factor ranges from 3 to 9. This is the preliminaries of this factorial experiment. I'm not going in detail about this preliminary. This is all everybody know about this. So I'm directly jump to the method of construction. These developed construction methods are described in different steps. Like by using different step, we have developed the construction method to obtain row column designs for fractional factorial experiment in two rows, where all the main effects and two interactions are estimable. Coming to the step 1. First step, what we can do, we have to obtain the block designs in block size 2 for the fractional factorial experiments in half replicate in minimum number of replication. Here we derived that the minimum number of replication required for estimation of all main effect to interactions in block designs of block size 2 is log n base 2 plus 1. That is, if number of factor is, for example, 4, then we need 3 replications. Then for obtaining, now from this, we first find out how many replications required to estimate all the main effect to interaction in fractional factorial setup. Now, obtaining block designs in fractional factorial setups, suitable defining contrast of same order have to be selected for each replication to get half replicate. So here important part is to select suitable defining contrast, and in each replication, for each replication, we have to select different defining contrast of same order. Now, in step 2, by using treatment combination of fractional factorial experiment, once we find out a defining contrast and we find out the half replicate of the complete factorial setups, then we can find out the key elements with the 1. Means the first column should be represent 1 with the defining contrast, and that is known as the principal block. And from the principal block, by after getting the principal block in the design, easily one can get all the other rest of the blocks, because the block size is 2, and we get the single block with 2 elements. where one element is 1 and second element is the defining contrast. After combining all the replication, one can get the block design for 2-level fractional factorial experiment in block size 2 easily. Now, in step 3, the important part is to convert the block design setup to row column setup, because our aim is to construct row column designs for fractional factorial experiments. So a methods for converting any block designs to row column setup is given by Das et al. In 2013. So using that method, we can easily convert the block design setup to the row column setup for this purpose only. So here the basic flavor of the converting a block design setup to row column design setup is identify the factorial effects possible higher interaction which are unconfounded in all the replications of block design setup obtained in step 1 and step 2. Then we have to confound that particular factorial effect with row component design. For example, let's take an example half replicate of 2 to the power 5 fractional factorial experiment. Here, the minimum number of replication required to estimate all the manifest interaction is log n base 2 plus 1, that is 4. Here, the bracket, the square bracket forms the greatest integer functions. So it is 2 point something it is found out. So that is 3 and 3 plus 1 is 4. So now that means we need minimum 4 replications in a fractional factorial setup, fractional factorial experiments to get estimate of all the manifest at 2 factor interactions. So that means we have to find out 4 different defining contrast for each replications. So since we have to form defining contrast of same order, and we are going to develop the design, construct the design for half replicate of 2 to the power 5 fractional experiment. So we are taking the 4 order interactions. I equal to ABCD for first replication, I equal to ABC for second, ABD for third, and ACD for fourth replications. Now coming to the first replication, when we take defining contrast as ABCD, then the 16 treatment combinations, because we have to take the fraction which is the key element is present, 1 is present. So the 16 out of the 32 treatment combinations, the 60 treatment combinations are 1, A, B, A, C likewise. That easily one can find out. Like A plus B plus C plus D equal to 0 we can take, and we can easily find out the treatment combinations of the half replicate of 2 to the power 5 factorial experiments. Now the important part is here in the principal block, means the first block, what we can do, we placed 1 with the defining contrast what we take. This is the important part here. Here, since we are taking defining contrast as ABCD, so we keep the first block, because block size is 2, only 2 units can be accommodated in a single block. So what we can do, we have to, first unit should be 1 always, and second unit should be the defining contrast. Like 1 and ABCD here, we can see 1 and ABCD are in the first couple of block. And then the rest of the 7 blocks can easily find out from the first block, because we can take AB means here ABCD, then AC, then BD, because that can be easily find out from the first block. The important part is the finding out the first block of the design. So once we find out the first block for a first replication, that means the first one is the first replication. The second one, A1 with ABC, that is the second replication. 1 with ABD, third replication. 1 with ACD, that is the fourth replication. So if you combine all the replications, first to 4, that means 32 blocks, we can easily get the block designs which estimate all the manifests and two interactions. So here, if we go for the factorial experiments directly, minimum 64 blocks needed to estimate all the manifest interactions when we take block size 2. But in fractional factorial experiment, we reduce it to 64 to 32 blocks only. Now, the main part is to convert this block setup to row column setups. So here, yes, sir. Yes, sir.
Time is about to finish.
Yes, sir. Yes, it is finished, sir. It is finished. So the next part is to convert the block setup to row column setup. Here, the row column design obtained by confounding the ABCD, since ABCD is unconfounded in all the applications. So after confounding the ABCD, the corresponding what we get, this is the row column designs for fractional factorial experiment in 2 rows. Here we can get, in first replication, we can estimate A, B, C, D, all the things. From out of all these 4 replications, we can easily get all the manifests and two fatal interactions are estimates. So this is the way how we can find out for any number of factor, any number of replicate, we can find out the fraction of factorial experiment for this row column setup. So regarding concluding remarks, one can refer to this Yadav 2021. This is my MSc student. On this MSc thesis, this work has been carried out. So I dedicated this work to his MSc thesis. These are some of the references. Thank you.
Yes. Thank you, sir. Thank you, speaker.
Yes.
Very good presentation. Anyway, any question from any side? What's your name?
Sukant Das, sir, from ISRA, Indian Agricultural Statistics Institute.
Sukant Das?
Yes, sir. Yes, sir.
Sukant Das.
Yes, sir.
Okay. I think I should thank you. And if there is no question, then really very good work you are doing. This is your students' work?
Sir, my MSc student, sir.
Okay, so nice. Thank you. Please keep up.
Thank you, sir.
Yes, next speaker, 87, serial number. Yes. 87. Yes, please.
Dr. Amir Sahib, please unmute yourself.
Next speaker.
Yes, sir. Good afternoon, sir.
Okay.
Is it visible, sir?
Yes.
Put it on full screen mode, please.
Sir?
Okay. Go ahead.
Full screen mode, full screen mode.
Yes, sir, I am in full screen.
Dr. Amin, start.
Yes, sir. Good afternoon, sir. Good afternoon, one and all. This is Dr. Amin. I am working as assistant professor in BURT, Hyderabad. Today, my topic of presentation is new series of construction of second order rotatable designs. So the logical construction of an experiment is known as design and analysis of experiments. So in real life, we have different applications. For example, scientists involved in improvement of manufacturing process to maximize the yield and decrease the variability. And experimental design techniques become extremely important.
I mean, your slide is not moving and it is not in slideshow mode. Please make it slideshow mode, and it is not moving also.
It's not slides. Yes, now it is all right.
Yes, now it is moving, I think, but not in slideshow mode.
Yes, size may be increased. Anyway, go ahead.
So experimental design techniques become extremely important in such situations to develop new products and process in a cost-effective and confident manner. So what is response surface design? Let there are V factors, X1, X2, and so on, Xn. Each factor has S levels for experimentation, and D is the design matrix for the combination of all factor levels is given by D, and the combination of factor and response relationship is given by response surface. The designs for fitting response surface is known as response surface design. Generally, we are using first order and second order response surface models for fitting response surfaces. Here I am giving first order response surface design y equals to x beta plus epsilon, where y is the vector of observations and x is the youth row of x and v, and beta is the vector of parameters, and epsilon is the vector of random errors, and the expectation of epsilon equals to 0. So this is the first order model y equals to beta naught plus beta 1 x1 plus and so on. And the least square estimate of beta hat is x dash x whole inverse into x dash y, and this is the movement matrix x transpose x. So the variance of the predicted response at youth point is variance of y hat is given by here. And similarly, the second order response surface model is y equals x beta plus epsilon, where y is the vector of responses and xu is the youth row of x, and beta is the vector of parameters, and epsilon is the vector of random errors. And we are imposing some restrictions on the movement generating function towards the orthogonality, where product of each column has to be sum of y equals to 0, and summation xu square equals to n lambda 2, and summation x power 4 equals to cn lambda 4. And this is the inverse of movement matrix x transpose x. And similarly, what is second order rotatable design? Because in this presentation, we are proposing new methods for construction of second order rotatable design. So initially, what is second order rotatable design? If the variance of this estimated response at any design point is a function of rho square, that is distance from design point to the origin, then the design is called second order rotatable design. And this is the variance of estimated response can be expressed in the form of rho square, and we are giving a, b, k values here. And there are many researchers attempted on the construction of the second order rotatable designs. Initially, Box and Hunter introduced a new series of response surface designs with the property that the variances of estimates of response at points equidistant from the center. These designs are called rotatable designs. And there are many researchers attempted on the constructions of rotatable designs. And in 1960, Draper extended the method of transformation group for the construction of infinite series of SORD in 3 and more factors. And Dasan Narasimhan in 1962, they give general construction methods for the SORD by using balanced incomplete black design. And this is our first proposed method, balanced incomplete black design. Initially, we are taking incidence matrix of balanced ternary design with parameters V, B, R, K, lambda. And we are in incidence matrix of BTD, balanced ternary design. We have 1 and 2 elements. Just we are substituting beta instead of 1 and 2 by alpha. And we are adding some more central points if necessary. And the unknown levels alpha and beta can be chosen satisfy the condition summation x power 4 equals to 3 into summation x square into x square u into x square uj. So the resultant design matrix D provides V-dimensional second order rotatable designs in 5 levels. And based upon this method, we are proposing some theorem. So a new series of second order rotatable design can be constructed with alpha equals to 2 and beta equals to 1 using the series of balanced ternary design with parameter V, B, K, R, K, lambda. So just we are substituting alpha, beta in the instance matrix of balanced ternary design, and we are adding some more central points if based upon the requirement, and we are checking the condition, this condition is a rotatable condition summation x power 4 equals to 3 into summation x square u into summation square u square, and the number of design points here n, and we are making a relationship between this by solving these two equations. We are getting the t value here. This is the quadratic equation here, rt square minus 3 into tv plus b minus 3k equals to 0. Based on that, we are evaluating t value where t equals to alpha square by beta square. Then we will get the design matrix with 5 levels. So this is the one numerical example how we are transforming, how we are deriving second order rotatable design based upon the balanced ternary design. Here we are considering balanced ternary design with 9 parameters and 3 blacks, and black size is 3, and n1 equals to 4 and n2 equals to 4. Based upon the proposed method, we are converting alpha ones as betas and 2 as alphas, and this is the proposed new second order rotatable designs with 5 levels. This is our second proposed method. So this is just we are changing the parameters of the balanced ternary design. Same we are considering incidence matrix of balanced incomplete black design. The elements 1 and 2 in the balanced ternary design replaced with beta and alpha, and based upon the requirement, we are adding n not central points, and we are using verifying the rotatable condition here. The resulting design matrix D provides SORD in 5 levels. So, the existence of a BIBD with parameters VB, RK, lambda results to the existence of balanced ternary design with parameters VB, RK, lambda, K, and pi. So, based upon the second proposed method, we are giving one theorem, existence of the theorem, a new theorem, a series of SORD can be constructed with alpha equals to 2 and beta equals to 1 using the series of balanced ternary design with parameters VB, RK, pi. So we are considering, initially we are taking incidence matrix of balanced ternary design and we are replacing with alpha and beta, 1 by beta and 2 by alpha. And based upon this, we are adding some more central points and we are verifying the condition of rotatable condition and based upon the relationship, we are taking these equations and we are solving the equations. Here t equals to alpha square by beta square. Then we can obtain RT t square minus 3kt plus R equals to 0. This is the t value here. And this resulting design provides V-dimensional SORD in 5 levels. So this is the numerical example how to constructing. We are constructing SORD from balanced ternary design. Here we are taking balanced ternary design and we are converting into SORD based upon the proposed method. So similarly, this is the third proposed method. In just we are changing the parameters of balanced ternary design VBRK. We are taking incidence matrix of balanced ternary design for the given parameters and we are replacing the elements 1 and 2 by alpha and beta, and we are adding based upon the requirement, we are adding some more central points and we are verifying the condition, rotatable condition, and the resulting design provides V-dimensional SORD in 5 levels. So here the existence of a balanced incomplete block design with parameters VB, RK, lambda results in the existence of balanced ternary design with parameters VB, RK, and pi. So based upon the proposed method, we are giving one theorem. We are proposing one theorem.
To the conclusion.
Yes, a new series of SORD can be constructed with alpha equals to 2 and beta equals to 1, and these are the methods. So this is the numerical example based upon our proposed method. So these are our references. Thank you.
Yes, thank you, Dr. Amin. Yes, any queries, any question? Dr. Amin?
Yes, Dr. Amin, I have one query that one of the paper written by Dr. Prasanthi in 2020, have you referred that paper? That is
No,
also second order using balanced ternary designs. They also developed, and those are also in general nature, means some more parametric combinations of this alpha and beta. Please refer that paper. Maybe
okay, sir. Sure, sir.
Okay.
Sure,
by
sir.
Prasanthi in 2020.
Sure, sir. Sure, sir. Thank you. Thank you.
Dr. Amin, I want a question. What type of research is this? Is extension or the new theory, or what type of the thing? One thing, have you followed? Is it an extension, just like second order rotable design? Was first, this is extension of first order, or what type of research you have done this?
So just to, we are proposing the method, new method for construction of second order rotatable design based upon the balanced ternary design, sir.
Okay, method of second order rotable design, new method for that. It is not an extension.
Yes, sir.
New research.
These are new methods, sir.
Okay, what is the best application? Cite any best application of your work?
So we are comparing with the previous methods, sir. So then we got some efficient.
Method is actually that's not a application. Application in other topics, other science, other something. Have this application or not? Have
yes, sir. Yes, sir.
This part remains. You see, when you work, you should know the applications. What work you have applied, of course, has the impact on the application or not? it is not necessary that it has always, mostly work is not applied. Anyway,
Okay.
have you not worked any application in your mind?
No, we are not. We are observing in engineering field, sir. We have many applications of response surface design, but we not applied real time this application.
Okay, okay. Thank you then.
Thank you, sir. Thank you.
Yes, next. 88.
Yes, sir. I am Manusha. Good afternoon, sir.
Manisha.
Yes, yes, sir. Good afternoon, sir.
Good afternoon.
Good afternoon, one and all. This is Anusha, research scholar from the Department of Statistics, Usmania University, sir. So my presentation is on the topic of analysis of variance for a Latin square design. For this, we derived the non-parametric method. So first, we will see what is the Latin square design. Let's suppose if n treatments are there, the arrangement of these n treatments in n rows and n columns is called as a Latin square design, and each treatment will occur once and only once in each row and in each column. That means all the treatments will appear in each row as well as in each column. So this is called as a Latin square design, and this Latin square design is completely complete block design. And this is an example of the Latin square design. That means it is the layout of the Latin square design. So here A, B, C, D are the different treatments. If you observe that A is repeated in once and only in one row and in one column. So this is a general layout of the Latin square design. And this is the linear model of Latin square design. So here alpha I, beta j and gamma k are representing the effects of the treatments, rows and columns. And in Latin square design, the total variation is divided into 4 parts. That is treatments wise variation and row variations, columns variation, and finally the error variation. And these are the different sum of squares and mean squares. So for this Latin square design, we have derived the non-parametric approach. Generally, the non-parametric methods are used when the assumptions of normality is violated. That means when the given data is ordinal or nominal. So this method or this procedure is derived when the data is ordinal. So for this test procedure, first we have to arrange the observations in ascending order, and then we have to rank all the observations. So here small Rijk is representing the rank of a observation. So that means Rijk takes the values from 1 to n square. And Ri double dot and R dot J dot and R double dot K be the totals of the rows, columns and treatments. And in this procedure, we have derived the total variation into 4 parts. That means treatment wise variation and rows wise variation, column wise, and as well as error based upon these ranks. And these are the sum of square with respect to the treatments, rows, columns, and error. And these are the non-parametric test statistics. So we derived the non-parametric test statistics with respect to the rows, columns, and treatments. So here my hypothesis is I have to check whether the all treatments are homogeneous or not, treatment effects are homogeneous or not, and also rows effects are homogeneous or not, as well as columns too. And this is an example data I have taken. So this is the rank transformer data. So for this data, I have derived the, I have found out the test statistic values. So these are representing row totals and column totals, and these are the treatment totals. And this is the ANOVA table based upon these rank values. And this HR is my test statistic value row, and this is the column wise test statistic value and for treatment also. And I have compared this with respect to the chi-square value, that is 7.815. So if I compare this chi-square value to this row, column and treatment values, so that means from these comparisons, I am concluding that there is no significant difference between the row effects and column effects as well as treatment effects. And these are my references. Thank you.
Good. Thank you. Yes, any question, please? Any query?
Yes, I have few queries regarding this Latin square design. So first of all, nice work. And one thing is that, have you taken the condition of incomplete Latin square design? Incomplete Latin square part?
No, sir.
Okay, only
No,
the complete setup you are considering.
Yes, sir. Yes, sir. We are still working on this.
Okay. And second thing is, if your observations not follow normal, then you can go for transformation of data, and then you can go for standard F statistics, all those things you can refer. Where to go for non-parametric approach?
Yes, sir.
And my question is, where to go for
Actually, only we have seen in this area. So with your suggestion, we'll go on this only.
Okay, try to compare that after transformation of data, go for normal statistics, and without transformation, go for your approach, and compare those to F statistics. Then you will be able to say that your approach is good or comparably what it affect the taste. Okay.
Yes, sir.
Thank you.
Thank you, sir.
Yes. Dr. Nusa, let me know what research you have done this briefly. What contribution you have made in 1 or 2 lines? Tell me what in this work.
Actually, sir, sometimes we are not having the normal data, that means direct values. Sometimes we are having ordinal data, that means ranks we are having.
Okay.
So in that situation, how can we carry out the analysis?
Okay, this is the modus operandi.
Yes, sir.
This is your modus operandi. And what about, you see, you have written non-parametric approach. Was there parametric approach already? No. Non-parametric.
Sorry, sir.
You have written non-parametric.
Yes, sir. Yes.
Was there any parametric approach also?
Yes, sir. Actually, this Latin square design comes under the parametric approach only, sir.
My point is, was there any parametric approach also?
No, sir.
No. With non-parametric outcome, must be there be parametric.
Yes, sir. Yes, sir. I will look into this.
Okay, thank you. Thank you.
Thank you, sir.
Next one. 89, serial number.
Am I audible, sir?
Yeah, you are audible, yes.
Yes, audible.
Good afternoon to everyone.
But your slides, okay, now it is audible, visible, yes.
Now it is okay, sir?
Yeah, yes.
Thank you. Good afternoon, everyone. This is Dr. Deepthi, working as Associate Professor in the Department of Mathematics in Geetanjali College of Engineering and Technology, Hyderabad.
Okay.
Today, I would like to explain about the Bayesian estimation for missing responses in RSD model, means response surface design model. So coming to the main objective of the study is, in this, we need to study the feasibility of estimating the parameters when responses are missing in response surface design model. So coming to the main abstract of this, nowadays, in recent years, missing responses plays a major role in designs, and it has a great deal of attention. In any design model, if the responses are missing, then the sampling results is insufficient. Very few authors made an attempt on various types of problems that are associated with missing responses in designs of experiments. But there is no significant work is done on estimation of missing values in response surface design model when responses are missing. So coming to the introduction to the response surface methodology. In statistics, design of experiments plays a key role in any scientific investigation. Many of the designs were developed with increase of applications in science and technology. Science and technology, medicine, agriculture, social sciences, etc. The methodology of response surface explores the functional relationship between the several explanatory variables and one or more response variables. Response surface methodology is a collection of mathematical and statistical techniques developed by Box and Wilson in 1951 to find the optimal settings of input factors or design variables that maximize or minimize or target measured response variables. Why? What is the necessary to estimate the parameters when the observations are missing? Because missing values in designs of experiment is a common phenomenon in a real world problems, and it has attracted a lot of attention in the recent decades. Suppose if any experimental design has missing observations, it results in insufficient sampling. So it is necessary to estimate the parameters and missing responses to carry out the analysis. Several authors made attempts on estimation of missing values using different approaches for various designs of experiments. Very few authors made attempt on estimating the parameters when responses are missing in response surface design model. Recently, Ajanta and Bhattacharya in 2022, they made an attempt to estimate the parameters for missing values in randomized block design using Bayesian approach. Srinivas and Bhattacharya in 2015, they made an attempt to estimate the parameters for missing values in first order response surface design using EM algorithm. So, but no significant work is found on the estimation of missing values in first order response surface design using Bayesian approach. As we know that Bayesian approach is a powerful technique that can be used to estimate the uncertainties of parameters based on their posterior probabilities. As posteriors can be computed using the likelihood and the prior distributions, since the marginal likelihood is a simply normalized constant, which need not be explicitly calculated. Coming to the response surface design. So how the design will be under response surface design. There are V factors, X1, X2, so on up to XV. Each has S levels for experimentation. Let YU represents the response at the Uth combination and D represents the design matrix, which consists of the elements XU1, XU2, so on up to XUV. So, which is the ith factor in the Uth treatment combination. The study of functional relationship between the factor combination to the response is expected value of YU is equals to the functional form of the design matrix, which is said to be a response surface, steady, and the designs used for fitting the response surface called response surface design. And the model fitted is called as response surface design model. So, in particular, response surface design model consists of first order response surface design as well as second order response surface design. So first we will move to the first order response surface design. Let Y be the vector of response corresponding to a design matrix, and assume the functional form of the response surface design model be linear, and which can be expressed as like this: y is equals to x beta plus epsilon. So simply just like a linear regression. But here each x is having ith factor in the uth treatment combination. Here y be the response and x be the uth treatment combination, and beta be the vector of parameters, and epsilon be the random error corresponding to the response yu. And here we assume that epsilon, that is error, follows normal distribution with parameters mean 0 and variance sigma square I. So here, how to estimate the parameters in first order response surface design model when responses are missing using Bayesian approach. Let y be the vector of responses corresponding to a design matrix X, and beta be the vector of parameters, and epsilon be the vector of random errors. Suppose if any observation is missing in the resulting data is incomplete to carry out the analysis as per the original plan of an experiment. Hence, it is necessary to estimate the missing responses to carry out the further analysis. Let us assume that at some design points, the responses are missing. Then the model, that is y is equals to x beta plus epsilon, can be expressed as y1 ym, which is equals to x1 xm into beta plus epsilon. So simply like y is equals to x beta plus epsilon, where y1 be the vector of n minus m known observations, and ym is the vector of m missing responses, and x1 is part of the design points corresponding to the known, and xm is the corresponding to the missing observations, and the error is also partitioned accordingly. The least square estimate of the parameters from the known observations is beta hat equals to x1 prime into x1 whole prime whole inverse into x1 prime into y1. The joint probability density function of observed sample y for the given parameter theta, which is called as the likelihood function of y and is denoted by p of y given theta. Probability distribution for each parameter encapsulates the prior beliefs held about their most likely values called prior distribution. This p of theta explains the information about the parameter theta called prior distribution of theta. An updated measure for each of the parameter values theta based on prior and given knowledge on y, which we are going to call that one as a posterior distribution of theta, that is p of theta given y. Then the estimated missing observations can be obtained as ym hat is equals to xm into beta hat. As we know that y beta responses means which known to us, then the likelihood function of an observed sample y with the given parameters beta and sigma square is this one. So this is the likelihood function for the given parameters. So likelihood function of y given beta comma sigma square. So these are the things, and here we need to partial differentiate with respect to each parameter, that is here beta and here sigma square, and making it to 0. Then the distribution of the parameters is this one. Here we got the posterior distribution of the parameter beta, which follows multivariate normal with the beta hat and x prime x whole inverse into sigma square. And posterior distribution of the parameter sigma square follows inverse gamma distribution with n minus v by 2 comma n minus v sigma hat square by 2. So here in this paper, we made an attempt to estimate the missing responses in first order response surface design using Bayesian approach. For this, we use Winbuck's software to re-estimate the parameter values. So here the method is illustrated with a suitable example. For example, if you take the effect of pressure, temperature, moisture, and the flow rate and the peanut particle size. So like this, we will be having x1 to x5 variables and the total yield y of oil per batch of peanuts with 16 design points, of which 2 responses are missing, and the corresponding design matrix will give 5 factors are given below. So if you observe, these are the responses, and here in these responses 2 values are missing. So if the values are missing, we are not able to continue the analysis. So for that, first we need to estimate these parameters by using the Bayesian. So these are the design points corresponding to this variable y. And here, the estimation of missing responses at the 4th and 11th design points are evaluated using Bayesian approach and is presented below, and the estimated values of parameters at the known design points are evaluated are presented here. So here, these are the values which are which the responses are known to us, and here the resulting estimated missing responses are 83.8394 and 80.1726. So to estimate these parameters, we use the Winbugs software. That is, here it is the Winbugs code. First, we need to construct the model, and we need to specialize the parameters involved in the model. That is, as we are having 5 variables, so we need to construct that 5 variables with the beta naught intercept form. And here, this is the data given to us. So,
yes,
this is the program code.
If we come to the conclusion,
yes, yes, sir. It's completion, sir. And here, this is just a sample extension, whether we are going to get the results or not. So just we are in this work presently. As few observations are missing, we are trying to estimate using Bayesian, and hence we are moving to the model reduction. So here, I estimated the missing responses at these 2 design points, and by using the R program, we evaluated the 5 and 2 possible linear combination models, and here the resulting reduced Bayesian model. As the model is with respect to 5 variables, by using the Bayesian approach, means by using the estimating the parameters using Bayesian approach, we reduce this model to 2 variables with error sum of squares as 98.906 and with 8 degrees of freedom, and with R square value is 0.895, means almost 89% is selected the model with highest probability value 0.128 with these 2 variables. And these are the references.
Yes, very good.
Thank you, sir.
Deepti, very good presentation, very clear. Any question, please? Any query?
Yes, sir. Nice presentation.
Thank you, sir.
First thing is that have you any real experimentation example with you where really the missing observations are there? Because I'm asking why. Because before conduction of any RSM experiments, we have developed some RST, and we suggest those particular RST because those are only few settings we have given for this conduction experiments. And I don't think the missing cases are obtained because only 10 to 15 or 15 to 30 the settings were given to the experimenter to conduct the experiment when RSM is used.
Yes.
So if you have any real experimentation with you, then it is very good. The first thing.
Actually, I am trying to project on towards the dimensionality reduction when responses are missing. So this is just like my extension to the thesis.
Yes. And second thing is about how up to how many percentage of missing observation your method can be estimate the parameter.
Presently, I am taking randomly, sir. this like 2 missing observations, 3 missing observations, like that I'm taking, means already existing models only. I'm not moving to the real life example. So presently I'm doing on the work of whatever the existence examples were there. So checking the model checking, so that then later I
More
can
number of missing observations can be handled, then your method will be more appreciable, I think.
Yes, yes, sir.
Okay, okay.
Any suggestions regarding real life, sir? Real life,
Yes,
like how the data is going to be taken?
Yes, yes. In post-harvest technology generally, in agriculture experiment I'm considering, in post-harvest technology, there are many experiments there regarding RSM experiments where different, also in agricultural chemicals, so many chemical compositions are there.
Yes,
like, so on the situations, previously they required a particular design, maybe some this any type of box Benkin design or central composite design, any type of designs for the number of factors and levels, those are given. Okay, so then after the settings getting particular combinations, they conduct the experiment. So rare situations maybe occur where missing response are coming. So that's why I'm
yes, sir.
Okay, okay.
Thank you very much, sir.
Should be made after that. It is not, it is a question. You should ask the question, not the discussion. Yes, please, you see this is response. Is it response is not a value?
Sir, sir, your voice is not audible, sir. A very low voice is coming.
Are you listening?
Yes, yes, sir.
Yeah, this response you say, response is a value or the set of values, or what probabilities, set of
values, continuous variable only, sir.
This is the difference. Otherwise, yes, this is generalization actually of that.
Yes, yes, sir.
Okay, okay, okay. Thank you.
Yeah, may I take up?
Yes.
May I take up, sir?
Yes.
Sir, this is in connection with dealing with real life data for missing observations. Okay. I think she has made very good progress with respect to the models. She might actually look at using even her existing mobile camera and then, modeling the camera aspects. And then, the missing data, it comes out in wonderful ways. Then as they generate the terrain surfaces also, the surface response models can be understood and better. This is my suggestion, sir.
Okay, okay. Thank you very much, sir. I will look into that, sir.
Good suggestion. Thank you for that. Yes, anything? Yes, I again thanks Deepti for your.
Thank you, sir. Thank you for organizers for giving me this opportunity.
Next, 90, serial number 90.
Yes, sir, I'm here, sir.
Yes.
Sir, is my screen visible, sir?
Yes, visible.
Okay. Good morning, one and all. This is Dr. Ajanta Rudra, working as an assistant professor in Geetanjali College of Engineering and Technology, Shirial. So here I am here to present on estimation of parameters and missing values using Bayesian approach in factorial experimental designs. So in sometimes, even in well-planned experiments, the responses on experimental units may not be available due to natural or man-made causes like washed away by floods, fire, plant eaten by animals, destroyed by animals, and so on. And experimental units mixed during the time of transporting, etc., etc. So the missing observations may influence the distribution of known responses and orthogonality in the model. So the distribution of observed random variables.
Yes, open.
Your slide is not moving.
Slides are not advancing.
Okay, sir. The distribution of observed random variables of the model may be same or may differ with the missing observations. So the most common approach to solve this problem is
your slides is not advancing. You see, this is the only first slides you are showing.
Yes, sir. Yes, sir.
Show the next one.
Is it slide moving, sir? Now I have moved.
Slides are not moving.
Okay. Now, sir?
It is now all right.
Okay, sir. So let us come to the factorial experimental design. So experiments where the effects of more than one factor, say variety, manure, etc., each at 2 or more levels are considered together or called factorial experiments. So let IIJK be the observed responses when factor A is at ith level and factor B is at the jth level for the kth replicate. So let the number of observations be total observations are A into B into R. So the classification of responses of a factorial experimental design is as follows. So then general linear model for factorial experimental design is represented by y is equals to x beta plus epsilon. So where y be the vector of observations and beta, mu, alpha, beta and alpha beta interaction effects. So be the vector of parameters and mu be the general mean and alpha I be the effect of due to ith level of row factor A and beta j be the effect due to jth level of column factor B, and alpha beta be the interaction effect due to alpha I and beta j, and epsilon be the random error. And we are assuming that epsilon is follows normal distribution with 0 comma sigma square parameters and x be the design matrix. So we are coming to the posterior distribution of estimated parameters in factorial experimental design model with missing observations. So let the number of missing observations corresponding to ith treatment and jth block be mij. So then the number of observations be n, capital N. So let y be the vector of observed sample and assume out of n observations m are not available. So the resulting partition model is given by this in equation number 2. So here y abr minus m be the vector of non-observed sample and ym be the vector of m missing observations and x be the design matrix and epsilon be the random error. And here the y is follows the normal distribution with mean x beta and variance sigma square. So here I am derived a likelihood function for the sample vector for the known observations. So with the unknown parameters beta and sigma square under the normality, which is represented in equation number 3. So from this likelihood function, I derived by using maximum likelihood estimators. So I estimate the parameters beta and sigma square values. So which can be given beta hat is x dash x inverse into x dash y and the sigma square by as follows in equation number 5. So the likelihood function of the non-observed sample y BBR minus m with estimated parameter is given by as follows. So now I estimated the posterior distribution of sigma square and beta can be estimated as f of beta. So these are the posterior distribution of the parameters beta and posterior distribution of the variance sigma square. And here, yes, we can observe that the beta hat parameter which follows multivariate normal distribution with the mean x with mean beta and variance x dash x inverse into sigma square and the sigma square variance which is follows inverse gamma distribution with the parameters ABR minus M minus A minus B minus AB minus 1 and the variance half into ABR minus M minus A minus B AB minus 1 into sigma square. So here the sample mean which follows the normal distribution with the mean y bar and variance sigma square by n minus m and the precision is follows gamma distribution with parameters a comma b where a and b are values are given by a is equals to abr minus m minus a minus b minus ab minus 1 by 2 and b is 2 by abr minus m minus a minus b minus m b minus 1. So by generating a sample using Gibbs sample from the known values using the equations which is represented by 4 and 5, then the posterior distributions of given y can be evaluated by using the equation number 6 and 7 from the sample such that the distribution of sample values more closely approximates the desired distribution and is used to evaluate the normalized constant. So from the simulated sample estimated parameters and estimate the missing responses. So here I take one example, factorial design with 2 by 2. So that is, this is the example with studying the effects of A is equals to 2 different culture and B is different times on the growth of a particular virus. And we perform then a balanced design experiment with n is equals to 6 replicates. So this is the totally n is equals to 24 measurements are there. So these are the results for the factorial design with the 2 levels, two square factorial experiments. So here we have considered the data. So the mean and variances are the data are 29.26087 and 32.747. And the precision is follows gamma distribution with parameters 29.2608 and variance 0.0305. And mean and variance pair per estimated parameters. So these are, so to estimate these estimated parameters, mean and variance, we use Winbug software. By using Winbug software, we are estimating the new parameters, that is estimated values of beta, so which are 29.28, 12.57 and so on up to 2.919. So for this I used a Winbug software to generate the new parameters, and estimated by using this new parameters we can estimate the missing response value as 48.207. So conclusions. A new method was proposed for the estimation of missing estimations in 2 to the power of k factorial experimental design. So, and derived estimation of parameters in 2 power k factorial design using Bayesian approach. And it can be noted that from Bayesian estimation, we can estimate the parameters using the general design Nealian model. From the estimated parameters using Bayesian estimation, we can find missing values. Bayesian estimation gives the best result as the traditional method which were already existed. It can be noted that Bayesian approach is very good approach method when the data is very large. When the data contain more missing values, Bayesian approach method is suggestible. So these are the conclusions we have drawn from the method. So these are the reference I prefer. So this is the end of the session. Thank you, sir.
Thank you. Thank you.
Okay,
thank you, Ajanta.
Thank
yes,
you, sir.
please, any question, any query?
Yes, I have one query that in one of your slide in your example, you are showing the variance is something 32 and mean is 29. Is it so? Variance is larger than mean in this example. Next slide, I think. Yes, your variance is 32. Is it so? How variance is more than mean? I'm surprised.
Sir, these are known observations, sir. Only known observations we consider the mean and variance values.
The variance is more than mean. Is it so really? Please check this, I think.
Okay, I will check, sir. Okay.
Variance should not
But,
be.
okay. So, okay. The precision values were given correctly, but the mean and variance only. But yes. I will check, sir. Sorry, thank you, sir.
Okay. Any more? Any question, please? If there is no query, I should thank the speaker. Thank you, Ajanta.
Okay.
Thank you,
sir.
sir. Yes, next speaker, 91. Yes, there is no. Serial number 91 on second order rotatable designs of second type, a review. Yes, then okay. Then the next one, general efficiency balanced incomplete block design. Yes. Then any others who wants to present the paper, most welcome.
Sir, Rahul is the next person. We can.
Pardon?
Yes, sir. I want to present my paper, sir.
Yes, Rahul. Rahul is presenting now. Sir.
Rahul, which one? Which serial number?
200, sir.
200. Okay.
Yes, sir.
200.
Yes, sir. Yes, sir. 200.
Okay, Rahul.
Yes, sir. It was included yesterday.
Okay.
200.
Okay. 10 minutes and plus 2.
Okay, sir. Good afternoon, sir. I'm Rahul, research scholar in Department of Statistics, working under the supervision of Professor S.C. Malik, and I want to present my paper, Classical Analysis of Two-Way ANOVA Model with Replication under Fuzzy Data. In decision-making problems, ranking fuzzy number is useful tool to deal with data that has ambiguity and uncertainty. That's why fuzzy quantities are used to explain the performance of alternatives in modeling with real-world problems in fuzzy decision analysis. So there is an aspect of fuzzy ranking method that is used to convert the fuzzy numbers. Fuzzy ranking method extract distinct characteristics from each fuzzy number and rank them according to their features. As a result, ranking fuzzy numbers becomes more difficult due to the fact that different ranking methods provide different ranking orders for the same set of fuzzy numbers. Jade in 1965 introduced the concept of fuzzy set theory to deal with uncertain and imprecise data. So Jain proposed ranking fuzzy numbers as a technique for making judgments in uncertainty and ambiguity by describing the inadequately quantity as a fuzzy set. Several arithmetic operations on fuzzy numbers was introduced by Du Bois and Pratt. Chen presented ranking fuzzy numbers with maximizing set and minimizing set. Similarly, Liu and Wong's present ranking fuzzy numbers with integral value. Wong et al. In 2006 presented the method for centroid formula for generalized fuzzy numbers. Garika and Lametta in 2007 modified the index of Liu and Wong for ranking fuzzy numbers by stating that the index of optimism is not alone sufficient to discriminate fuzzy numbers and proposed an index of modality to rank fuzzy numbers. Rao and Shankar proposed a fuzzy ranking method based on the circumcenter of centroid and index of modality, which allows the participation of decision makers in ranking fuzzy numbers. A new approach to problem of testing statistical hypotheses is introduced by Chachi and all in 2012. Gazarowski and Moroka in 2005 formulated the operators to approximate the fuzzy numbers to trapezoidal expected interval. There are so many authors who discussed the statistical hypothesis of fuzzy sets. Similarly, one of them was Gajarudhan and Parthiban discussed the fuzzy analysis of variance through defuzzification by alpha cut interval for trapezoidal fuzzy number. A comparative study for two-factor ANOVA model under the fuzzy environment through using trapezoidal fuzzy number, membership function, ranking function, and graded mean integration represented discussed by Gajarudhan and Parthiban. There was a this paper was unable to tell the interaction effect between the two factors. So I extend this paper for the fuzzy analysis of M factor ANOVA. In two-factor fuzzy analysis of variance method discussed before, only one observation per cell is considered that do not enable us to find an estimation of interaction effect between two factors. So to study the interaction effect, more than one observation per cell is needed. So in this paper, a comparative approach for two-factor ANOVA model with replications for triangular fuzzy numbers using several ranking methods is discussed. For the clarification of concept, we illustrate a numerical example. So first question is, these are some preliminaries which is used in the paper, that is fuzzy number and alpha cut interval method. As we know, all the classical two-way. Yes, sir. Sir, are you saying anything, sir?
No, continue.
Okay, sir. Classical two-way ANOVA model with M observation per cell. Let us consider Xij represent the kth observation corresponding to the ith U factor and jth V factor classification. The linear model for two-factor analysis of variance with M observation per cell is given by Xijk is equal to mu plus tau I plus beta j plus delta ij plus Eijk for all I from 1 to A, j from 1 to B, and k from 1 to M, where mu is the general mean effect, tau I is the effect of ith U factor classification, and beta j is the jth V factor classification. Delta ij is the interaction effect of factor U and factor V. Eijk is the error effect due to chance that is normally distributed with mean 0 and constant variance. Also, summation or I is equal to 1 to 8, tau I is equal to 0, summation or j is equal to 1 to b, beta j is equal to 0, summation or I is equal to 1 to 8, delta ij is equal to 0, and similarly delta ij from j is equal to 1 to b is 0. The parameters of this model can be estimated using the least square method by minimizing the sum of square of errors. That is equal to E is equal to summation or triple summation or ijk E ijk square, that is equal to ijk from I from A to I from 1 to A, j from 1 to B, and k from 1 to m, x ijk minus mu minus tau I minus beta j minus delta ij whole square. Then the normal equations can be estimated by differentiating them with respect to the the parameters which we want to estimate, like curly e or curly mu, curly e or curly tau I, and curly e or curly beta j, and curly e over curly delta ij. These are the normal equations obtained from the minimizing the sum of square of errors. So substituting the values obtained from parameter mu, delta I, beta j, delta ij in the linear model, we will get the equation, and where Eijk is chosen such that the both sides of the estimated model are equal. That we did in the classical ANOVA, and we can estimate the true total sum of square values, sum of square of factor u, sum of square of factor v, sum of square of interaction between factor u and v, and the sum of square of errors. The ANOVA table can be made using the result obtained here. So the null and alternate hypothesis for factor u, which we are testing, that all the means of factor u are equal, and alternate will be at least two of the means are different. Similarly in the factor v, and similarly in the interaction between u and v, h naught mu h naught u is equal to tau I is equal to 0. That shows that there is an interaction between the two factors, and h1 uv shows that alternate hypothesis we want to test that u and v are the independent, that is there is no interaction between the factor u and v. So decision rule will be based on the calculated value of the app statistics and the tabulated value of the app statistics. If the calculated value of app statistics for factor u will be less than the tabulated value of the app statistics, then we will reject the then the null hypothesis is accepted, otherwise we are reject the null hypothesis. Similarly for the v factor, and similarly we can do for the interaction effect. Now I introduced the same classical ANOVA factor. In classical ANOVA, in classical two factor ANOVA, there was the work on the real data, but in Fuji two factor ANOVA, there are some situations where we consider we do not have the data in the form of real data. We have the data in form of the Fuji data. So Fuji two factor ANOVA model with m observation per cell using alpha cut interval method is discussed. The two factor Fuji analysis of variance model with m observation per cell under the Fuji environment is proposed here. The observations are considered in terms of triangular Fuji number. Using the alpha cut interval method, we transform the Fuji triangular Fuji numbers. We defugify the triangular Fuji numbers in form of the crisp value. By separating the lower and upper level of the model, we construct the lower level Fuji ANOVA model with m observation per cell, and the upper level Fuji ANOVA model with m observation per cell. For lower level model, we have the observations Pijk plus alpha Qijk minus Pijk for all I from 1 to A, j from 1 to B, and k from 1 to m, and where alpha lies between 0 and 1. Similarly for the upper level model. For lower level model, we analyze the lower level model separately and upper level model separately. Then on the basis of their results, we draw the conclusion of accepting and rejecting the null hypothesis. Let us consider Xijk LL represents for the lower value of the interval after defugification, represent the kth lower Fuji observation corresponding the ith u factor and vth factor jth v factor classification. The linear model for two factor Fuji ANOVA with m observation per cell is given by Xijk lower L is equal to mu alpha L plus tau I alpha over L plus beta j alpha over L plus delta ij L plus Eijk L, where Eijk is the error component. Similarly, we estimated the parameter value of this model by applying the least square criteria for minimizing the variations, minimizing the errors. and we obtained the total sum of square value for lower level due to factor sum of square due to factor u, sum of square due to factor v, and sum of square due to interaction u and v. The same hypothesis we are testing under the fuzzy environment, and degree of freedom is calculated for lower level model, and the resulting ANOVA table is in terms of alpha. Then decision is made as in the classical statistics based on the tabulated value and the calculated F statistic in the form of alpha. Similarly, I did for the fuzzy ANOVA for the upper level model.
Rahul, come to the conclusion.
This is the example on which I applied the results. Then I used the graded mean integration representation for ranking the fuzzy numbers, and I apply it on the same example. Then I use the graded mean integration representation method. After that, Liu's and Wang ranking method on the same data, and the results were there. Then I applied the membership function method of ranking fuzzy numbers and applied on the same data. Then I have the comparison table. Using the alpha cut interval method, I found that there is a significant difference between the factor u, and there is no significant difference in the mean values of factor v, and there is no interaction between the factor u and factor v using the alpha cut interval method. While using the graded mean integration representation method, there I observed the significant difference between the means of factor u. There is no significant difference for the in the mean of factor v, and there was then no interaction. Using the Liu's and Wang's method, there was significant difference the mean values of factor u, and there is no significant difference between the mean value of factor v, and there were no interaction between the u and v. Using the membership function method, there was no significant difference between the means of factor u. There was no significant difference between the mean of factor v, and there was no interaction between the factor u and in the factor v. So the conclusion. This paper addressed the multiple cell to factor ANOVA model using the triangular fuzzy numbers for fuzzy data. Observing the decision obtained from the alpha cut interval method for the null hypothesis is accepted for the factor u and v for all alpha between 0 and 1. There was no interaction effect obtained in the ANOVA model using alpha cut interval method for both lower level and model and upper level model. The membership function method do not provide reliable result as they reject the null hypothesis for factor u, while it rejected for all the methods which I used in this paper. The Liu's and Wang's ranking method and graded mean integration represented method providing the same decisions as obtained using the alpha cut interval method. The alpha cut interval method is the best method to perform the ANOVA for fuzzy numbers, as it includes the all value of fuzzy numbers in the analysis and satisfy the same results based on the other two methods. So in future work, this work can be extended for the several other experimental design. These were the reference. Thank you.
Thank you, Rahul. Yes, any query, any question, please, from the audience?
Yes, sir. Mr. Rahul, I have one query that number of observations per cells you are taking equal here or what?
Yes, sir. Yes, sir.
So what about unequal number of observations? Have you dealt with this situation?
Sir, that can be done in using in another paper, sir.
Okay.
Yes, sir.
So only for
that can be done.
You are handling the situations of unequal observations.
Yes, sir. There can be unequal observations in replication. That's why we can do this work on the in that direction which you were saying, sir.
Okay. And one thing that in comparison table, what type of comparison you are taking place? I could not follow that. What comparison?
Sir, we were comparison there the results obtained from each ranking method of fuzzy number. That what are they giving?
Now,
and on the basis of
Q factor is significant and it is not significant. From where this is coming significant and significant for UV and interactions? From where any example you have taken?
Yes, sir. I have taken an example, sir. I have taken an hypothetical data, sir.
Okay, you
And
are
I
so,
applied the
you are
same.
so fast that I could not see that example. That's why I am worried.
Sir
Okay.
was saying that conclude, so I
Okay.
made it into I come. Yes, sir. That's why.
That's all. Yes, Rahul.
Yes, sir.
One or two queries I want to ask you. One is, what is the difference
yes, sir.
between ambiguity and uncertainty? You have written in the first sentence, ambiguity and uncertainty. How will you define ambiguity and uncertainty?
Sir, they both tells about the fuzziness into the data.
In fuzziness, what you see? Actually, you have not understood actually the things. Okay, this ambiguity is a uncertainty. It is a type of uncertainty. There are two types of uncertainty. One is ambiguous and other is probabilistic. Actually, you have done ambiguous uncertainty. That is also uncertainty. Because ANOVA and all this are the uncertainty. Ambiguous uncertainty or probabilities. The difference is that's ambiguity and uncertainty. You see, if you take experiment and they have the values, random variable as the values, and this sum is not ambiguity uncertainty. You have the sum is not equal to 1.
Yes,
and probabilistic uncertainty, the sum will be equal to 1.
Equal to 1.
This is the main difference, and that's why this theory is different.
Oh, okay, sir.
Okay, uncertainty has, now you have just like fuzzy numbers. They
Yes,
are
sir.
different because of this is ambiguous uncertainty. So there are two types of uncertainty, ambiguous.
Sir, you are not audible, sir.
Huda sir, you are on mute.
You are muted.
You are
Sir.
muted now, and you need to unmute. Unmute, please. Huda sir, unmute.
Yes.
Yes.
Yes. So uncertainty, you see, there are two types. Probability distributions, probability uncertainty, and ambiguous uncertainty. And difference is that probability uncertainties, if you take the probability distribution, sum is equal to 1. Ambiguous, there is no condition.
Is not equal to 1.
That's why this is a different story. Okay. Otherwise, you have done very good work. Congratulate. And
Thank you,
really,
sir.
I congratulate your supervisor also. That's good. Any other?
Thank you, sir. Thank you.
Any other speaker? Let us then close.
One is there, sir. Shekhar Gaud.
Organizers. No.
He is serial number 92. Yes.
Yes, sir.
One is left, I think, sir. One is left. This is the last candidate.
Yes,
Yes,
sir.
yes, 92.
Yes, sir.
Yes, now you present.
My topic, sir, my name is Dr. T. Shekhar Gada. I am working assistant professor, contact assistant professor, Hyderabad College, Usman University. Now I will present to my paper, variance balance incomplete block design. The definition of incomplete block designs, the arrangement of treatments in B blocks of sizes K1, K2, Kb when none of the block contains all treatments and the treatments are appearing exactly in R1, R2, RV blocks such that N1 pairs of treatments occur in lambda 1 blocks, N2 pairs of treatments occur in lambda 2 blocks and so on. Then the resulting design is said to be general incomplete block design. The C matrix for an incomplete block design in the form C equal to R minus N, K power of minus 1, N transpose, where N is the incidence matrix of the incomplete block design. N dash is the transpose. R equal to diagonal of replications R1, R2, RV, and K is the size of the block designs, diagonal of K1, K2, Kb. The definitions of balanced incomplete design. The definition of balanced incomplete block design and incomplete block design is said to be balanced if all the non-zero characteristic roots of the C matrix are equal. When R equal to R and Kj equal to K, and then C equal to R of IV minus K power of minus 1, R of R minus lambda IV plus lambda J VV, that equal to C equal to theta of IV minus V inverse J VV, where theta equal to lambda V by K is the characteristic root of the C matrix. Definition to efficiency balance. An incomplete block design is said to be efficiency balanced if all the V minus 1 treatment contrasts are estimated with the same efficiency mu, where mu equal to V by K or 1 minus lambda V by RK is non-zero eigenvalue of M equal to mu I plus 1 minus mu J R transpose depends on whether the design is orthogonal or non-orthogonal. Definition of variance balance design. An incomplete block design is said to be variance balanced if all the elementary contrasts are estimated with the same precision. The estimation of all treatment contrasts have the same variance. Here is the two series of the combinatorial construction of incomplete block designs using the combinatorial arrangement of efficiency balanced incomplete block designs. Number 2, combinatorial construction of new series of general efficiency balanced incomplete block designs. Method 1 and 2. I will present two methods. Method 1. Let capital N be the incidence matrix of efficiency balanced incomplete block design with parameters V, B, R, K. Arrange the incidence matrix capital N in the form N dash equal to NN, JJ. The resulting design is the incidence matrix of variance balanced design with parameters V dash equal to B plus 1, B dash equal to 2B, R dash equal to 2B, 2R, K J dash equal to 2B, K plus 1, where R equal to 2B, 2R stands for V treatments each replicated 2R times and the remaining 2B, one treatment replicated 2B times. This method is illustrated in the example 2. Example. Let us consider capital N be the incidence matrix of efficiency balance incomplete block designs with the parameters V equal to 6, block size is 11, replicated is 4 or 5, block size K equal to 2 or 4. The resulting is the incidence matrix of variance balance design with parameters V dash equal to 7, B dash equal to 22, R dash equal to 8 or 22, K dash equal to 3 or 5. The table is the construction of variance balance design. N is the incidence matrix of matrix. Variance balance incomplete block designs. Method 2. Combinatorial construction of variance balanced incomplete block design using efficiency balanced incomplete block design is presented below. Let capital 1 N and capital 2 be the incidence matrices of two efficiency balanced incomplete block designs with the parameters V, B1, R1, K1 and V2, B2, R2, K2. Arrange the incidence matrices N1 and N2 in the form N transpose equal to N1, N2, JJ. The resulting design is the incidence matrix of variance balance design with parameters V dash equal to V plus 1, B dash equal to B1 plus B2, R1 dash equal to B1 plus B2, Ri dash equal to R1 plus R2, I equal to where I equal to 1 to V plus 1, Kj dash equal to K plus 1 for J equal to 1 to B1, Kj dash equal to K2 plus 1, J equal to B1 plus 1, B2 up to B1 plus B2. This method is illustrated in the example 2. Example 2.2, let capital N1 be the incidence matrix of the efficiency balanced incomplete block design with parameters V equal to 6, blocks 11, replicated 4 or 5, block size K equal to 2 or 4, and another design N2 be the incidence matrix of the efficiency balanced incomplete block design with the parameters V equal to 6, B2 equal to 21, R2 equal to 15 or 30, and K2 equal to 5. The resulting design is the incidence matrix of variance balance incomplete design with the parameters V dash equal to 7, B dash equal to 32, K dash equal to 3 or 5, 3, 5 or 6, R dash equal to 19, 32 or 35. the incidence matrix of n dash equal to n1 into jj. The table is the efficiency balance design incidence matrices n1 and n2. Here is the variance balance equal to n dash equal to n1, n2, jj. Note, a variance balanced design with unequal replications is not an efficiency balance design, but a balanced incomplete block design with unequal replications becomes a variance balanced design. These are references of variance balance incomplete block designs. Thank you, sir.
Oh, thank you.
Thank you, sir.
Very good. Any query, please?
Yes, you have not defined what is general efficiency balanced incomplete block design.
What's that? General
efficiency balanced incomplete block design. You have not defined that thing in whole of the presentation.
General efficiency incomplete block design.
Yes, yes.
Okay, 1 minute.
You just tell me. No need to show the slide. Just tell me. Concept general efficiency, because
We are general efficiency block design. The parameter symmetrical. We are equal to BK, sir.
No, what do you mean by general efficiency? Efficiency balance equation, I know that. But what is
efficiency means variance is less, means efficiency more, sir. Efficiency variance is more, efficiency very less.
You are not getting my point. My question is, what is general efficiency? Because in one of slide you write the general efficiency in incomplete block design. Because efficiency balance incomplete block design, I know that.
Yes,
what is
sir.
general efficiency balance incomplete block design? That I want to just ask.
Treatments blocks are equal, sir.
No, that is in efficiency balance also.
Okay, if you are not doing, then you can.
It's okay, sir. No problem.
Okay. Yes, anything more? Any question? Then if there is no question, please, I should thank the presenter, Dr. Shekhar.
Yes, sir.
Yes, I think he's the last one. So now I invite the organizers to take the mic.
Thank you, sir, for chairing the session. Thank you.
So we'll meet after the lunch.
So there's a lunch break until 2:30. We'll join the session back at 2:30, sir.
Yes, please close the slides. Close the slides. Yes. So, okay, then let us disperse.
Thank you, Huda sir.
Thank you.
Thank you, Huda sir. Okay, sir. ಏನೇ ಸರ್ ಹತ್ತಿರ ಇದೆ
Shekhar sir, mute yourself.
Hello, Professor Langan sir.
Yeah. Yes.
What is that? So myself Manoj from University of Kerala.
I am here only.
Yeah. Yeah.
Yeah.
Are you
Yeah.
fine? Yeah.
Bluetooth. Yes.
Hi. Hi, sir.
Yes.
Yeah.
Sir, good morning.
Sir.
Good morning. Good morning, sir. Good morning. Good morning. எல்லாம் கரெக்ட் ஆகுது.
Satar.
இது ஆகுதா?
Manoj.
இது என்னப்பா அது? இது எடுத்துட்டுமா? இதையும் நிறுத்துது. ஸ்விட்ச் ஆஃப். ப்ளூடூத்தை கனெக்ட் பண்ணா கனெக்ட் ஆட்ட முடியும். கரெக்ட் ஆகுதா? பிரேக் திரும்ப க்ளோஸ் பண்ணிட்டு திரும்ப பண்ணியாச்சா? Hello? Hello?
Sir.
Yeah. I'm here only. Hello?
Yes, Professor. Can hear you.
Yes, I'm Professor Langan is here.
Yes.
Session started now?
I think so, because the time is, oh, it's 2:35.
Hello? Hello?
Yes, sir.
So you're waiting. I don't know, no one introduced my chair. This is only lunch break.
Only the chair and speakers are there.
Yeah, I'm not. Hello?
Good afternoon, sir.
Yeah, good afternoon, ma'am.
Hello, good afternoon, along
Good
with sir.
afternoon, good afternoon. Yeah, yes. Please. Please, ma'am.
Thank you for chairing this session, sir.
Yes.
You accepted for
Yes.
that. Thank you.
Okay.
Shall we start the session, sir?
Yes. You start now.
Okay, thank you, sir. Let me take the privilege of introducing Professor Elangovan, sir. Sir is working as professor in the Department of Statistics in Annamalai University. Sir's major area of research is stochastic process and its applications, reliability theory, and survival analysis, biostatistics, and cocoa regression analysis. Sir has over 30 years of teaching experience and published over 100 publications and attended over 50 conferences. We are very lucky to have you here, sir. Thank you for chairing this session, sir. Thank you.
Thank you very much. Thank you very much. Thank you. Thank you very much. Let us call upon the first speaker, Dr. Manoj Chako. Professor Manoj Chako.
Yes, sir.
Yes. He is the Associate Professor, Department of Statistics, University of Kerala. His research interest is order statistics, record values, ranked set sampling, and 10 students awarded PhD under his guidance, and 4 students are currently doing his research. And he completed 15 MPhil, and he published more than 45 papers. The award to his credit is UGC JRF in 2002, and Dr. K.N. Pillai Young Statistician Award, and he is UGC Raman Fellowship for Postdoctoral in US 2014. And also World Bank Trust Fund for Statistical Capacity Building. He is a matrices fellow for SCRB, DST, and he has a good researcher as well as teachers. On behalf of the organizing committee and chair, I invite Dr. Manoj Chako to deliver his talk on progressively type 2 hybrid sensoring scheme and its application in parametric estimation. So 45 minutes for you, sir, 25 minutes for you, sir, and 5 minutes for your discussion. Please go ahead, sir, please. I invite Dr. Manoj Chako to deliver his speech on progressively type 2 hybrid sensoring scheme and its application parametric estimation. Please, sir, please.
Okay, very good afternoon to you all. Thank you, Chair, Professor Elangovan, and also I thank the organizers to give me an opportunity to present my work. Okay, shall I? Is my screen visible, sir?
Oh, you can go ahead. It is
Okay, okay. So the title of my today's talk is a progressive.
Manoj, can you make it?
Okay, okay. 1 minute, 1 minute.
Yeah.
Okay.
View full screen.
Okay.
Go to view.
1 minute, 1 minute.
There itself you can do it, sir. View full screen on the top.
1 minute, sir.
At the left hand side top, sir. Left hand side top. Above the home. View. View full screen.
First I think you continue.
Excuse me, sir, 1 minute.
It's below, sir, below full screen.
Okay.
Yes.
It's okay? Now it's okay,
Yes,
sir?
go ahead.
Okay.
Yes, go
So
ahead.
title of my talk is Progressive Type 2 Hybrid Sensoring Scheme and its application in a parametric estimation. So it's a work together with my PhD student Agi Mokan. Recently, he has been awarded a PhD from the University of Kerala. So the title of the presentation is organized as follows. So first we give an introduction about what is progressive type of sensoring, and then introduce what is progressive type of hybrid sensoring. Then move to estimation part. For estimation, we assume we do parametric estimation. So we need a distribution assumption for the data. So we assume consider Kumarasamy exponential distribution, and in Bayesian estimation we consider both the maximum likelihood estimation and Bayesian estimation. And we do some simulation studies are also included in this work, and illustrating using real data, and finally some concluding remarks. So that is the organization of the today's talk. And all of you are familiar with the word sensoring. Sensor sample is actually arises in a life-taking experiment when the experiment doesn't observe the failure times of all units based on a life test experiment. And in medical and industrial studies, researchers have to treat transferred data because they usually don't have a sufficient time to observe the lifetime of all subject in the study. So that is the situation where we apply sensoring cases. And all of you are familiar with the sensoring, and there are two types of sensoring. Type 1 sensoring. So in type 1 sensoring, the time is fixed, and we have n items put on a lifetime experiment, and observe the number of failures before the up to the predetermined time t. In this case, the experiment time is fixed, but the number of observed failures is the random variable. And similarly, type 2 sensoring scheme, we fix the the number of failures needed for their further study. So in the type 2 experiment, the experiment continue until a pre-specified number of failures occurs. So that is type 2 sensoring. In type 2 sensoring, the number of observed failures is fixed, but the experiment time is a random variable. So that is all of type 1 sensoring and type 2 sensoring. And a hybrid sensoring is introduced by Epstein in 1954. It's a mixture of type 1 and type 2 sensoring scheme. And here also we have two types of hybrid sensoring. So type 1 hybrid sensoring is we fix both the number of failures and the number of failures we need, and the time is also prefixed. And the experiment stop at the time t star, where t star is the minimum of x, m, and t. That means if m failures occurs before the time t, then we stop the experiment at the time xm. That is the failure occur at the mth failure occur. And if that doesn't happen, that the mth failure doesn't occur before the time t, then we stop the experiment at the time t and observe the number of failures. That is the type 1 hybrid sensor scheme. So in this sensoring scheme, this sensoring doesn't guarantee the required number. That is the m number of failures, a number of items in the sample. That means if there are only less than m failures occur before the time t, then it doesn't guarantee the required amount of samples in the sample. So this is a major disadvantage of either both type 1 and type 1 hybrid sensoring schemes, that if there may be very few failures occurs up to predetermined time, so this results in the low efficiency for the estimated procedures. So to overcome this disadvantages, Chill 2003 considered a sensoring scheme. It's called a type 2 hybrid sensoring scheme. We call it as type 2 hybrid sensoring scheme. In this sensoring scheme, the experiment terminates at the time t star. Here t star is maximum of x, m, and t. That means if the mth failure occurs before the time t, then the experiment continues up to the time t. And if the mth failure doesn't occur before the time t, then the experiment continues up to the mth failure occur. So in this sensoring scheme, minimum m failures is guaranteed in this sensoring. So this is advantage of considering type 2 hybrid sensoring scheme. And in both type 1 and type 2 sensoring scheme, and also in hybrid sensoring scheme, in all this scheme doesn't permit the flexibility of removal of units at the point other than the terminal point of the experiment. So that is also a major disadvantage of considering type 1, type 2 or hybrid sensoring scheme. If you want to remove the items in between the experiment, that doesn't permit for the type 1, type 2 or hybrid sensoring scheme. So now to overcome this drawback, Cohen 1963 considered a sensoring scheme known as type 2 or progressive sensoring scheme. So this is introduced by Cohen in 1963. So it allows or permits the experimenter to remove units in between the experiment. So this is the schematic representation for the type 2 sensoring scheme. Suppose there are n items in an experiment, in a lifetime experiment, and at the time of first failure, and denoted by x1m n, that means, and m is also fixed, that means we need m failures, and x1mn is the time of the first failure. And at the time of first failure, R1 units are randomly withdrawn from the or removed from the remaining n-1 units. So at the time of the first failure, R1 units are randomly removed. And at the time of the second failure, noted by x2mn, R2 items are randomly removed from the remaining n-R1 minus 2 units. Similarly, at the time of third failure, noted by xmn, R3 items are randomly removed, and so on. And at the finally the time of the mth failure, noted by xmn, all the remaining units, that is not by R, all the remaining units are randomly removed from the experiment. So, and the experiment terminate at XMN. So that is the progressive type 2 censoring scheme. And this is, I already mentioned that. So at the time of the first failure X11, RM units are randomly removed from the N1-1 surviving units, and so on. And the procedure is continued at the time of mth observed failure. The remaining N-, M-, R1-, etc. Rm-1 units are removed from the experiment. And also in usual progressive type 2 censoring scheme, the R1, R2, etc. are prefixed. So there are the removals R1, R2, etc. Rm are prefixed before the start of the experiment. We fixed R1, R2, etc. And the R1, R2, etc. are also called the scheme of this censoring scheme. And sometimes, for example, but it is not happen in all situations. For example, the number of patients drop out from a clinical study at each stage is random and cannot be predetermined. And also in some reliability experiment may decide that it's inappropriate and too dangerous to carry on the testing of some of the tested units, even though these units have not failed. So in that situations, the pattern of removal at each failure is random, and this leads to progressive censoring with a random removal. That is, the removals R1, R2, etc. R1 follows a random numbers and follows a random distribution. And usually we assume that RI follows a binomial distribution with the parameter P. And this is the distribution for the R1, R2, etc. And so R1, the distribution for probability of R1 is equal to R is this. There is a binomial probability, and so on. And there are some references regarding progressive censoring is there. That is Brusso and Balakrishnan 1994 find the Wesleyan unbiased estimator blew up the parameters of both type 1 and 1 and 2 parameter exponential distribution. And there are certain other references. All these references are parametric estimation for certain non-distributions. Almost all the distributions are considered by several others. And Rostagi and Tripathi 2012 considered the Bayesian estimation of parameters of per distribution under progressive type 2 censoring. And Mohan and Chako 2016 considered Bayesian estimation for Gombert's distribution. And again, Chako and Mohan 2007 considered estimation of parameters of the Kumarasamy exponential distribution. And again, Chako and Mohan 2018 considered the Bayesian estimation of progressive type 2 censored competing risk data when the lifetime follows variable distribution. And also 2018, Chako and Mohan considered Gombert's distribution when removals are binomial distribution. Okay, and recently, Raki and Mohan 2011 considered the estimation parameters of Kumarasamy exponential distribution under progressive type 2 hybrid censoring. So this talk is mainly based on this paper, the Chako and Raki 2021 paper. So the main drawback of type 2 progressive censoring is that it takes a lot of time to get the mth failure. So we wait for the mth failure occur, maybe it takes a lot of time to occur the mth failure. So not to overcome this drawback, Kundu and Jordar 2016 proposed a censoring scheme called progressive type 2 hybrid censoring scheme. So it's a mixture of progressive type 2 and hybrid censoring scheme. So this is the schematic representation of the progressive type 2 hybrid censoring scheme. And in this case, suppose the n identical units are placed on a lifetime experiment, and the integer m, the number of observations needed, is fixed, and a time point is also fixed. So here we fix the n and also the time point. And at the time of first failure, as usual, R1 units are randomly removed. And at the time of second failure, R2 units are randomly removed. And if the mth failure occurs before the time t, that is at the time x mm, Rm units are randomly removed from the all the remaining units are removed from the experiment. So this is the case 1. That means the mth failure occur before the time t. It is a prefixed time to be fixed before the start of the experiment. And the second case is there are only j units failed before the time t. In this case, at the time of first failure, R1 units are removed, randomly removed, and at the time of second failure, R2 units are randomly removed, and at the time of jth failure, Rj units are randomly removed, and at the time t, all the remaining units are removed from the experiment, and experiment terminate at the time point t. So, anyway, in both the cases, in the first case, if mth failure occur before the time t, then we stop the experiment at the time xm and if there are only j failures occur before the time t, then the experiment terminate at the time point t and remove all the units from the experiment. So that is the type 2 progressively type 2 hybrid censoring scheme. So this is I already described, and these are the notations we used in this scheme. So x's are lifetimes, and ith observed failure denoted by ximn, and m is the number of failures before the termination for the case 1, and j is the number of failures observed before the termination of the experiment for the case 2. So that is only j failure occurred before the time t. And we also define a term d here. The d is equal to m for case 1 and d is equal to j for case 2. And ri is the number of units removed at the time of the ith failure. And rj star is the number of remaining units left at the time point for the case 2. That is, if only j failures occur at before the time t, and then rj star is the number of remaining units at the time t in the experiment. So that is the notations we use, and this is the case. There are two cases. Suppose that means mth failure occur before the time t. This is our usual progressive type 2 censoring scheme. If mth failure occur before the time t, then this is our usual progressive censoring. Case 1 is nothing but the usual type 2 progressive censoring scheme. And case 2, if only j failure occur at the time t, and then the observations are xm, x2m, etc., xj. So these are the two cases in the type 2 progressive hybrid censoring schemes. Based on that two cases, we can write the probability density function of both the observations. And the first density function, that is, this is nothing but the density function of the usual progressive type 2 censoring scheme. And this is the case when only j items fail before the time t. So this is the density function for the case 2, and first density is the density for the case 1. And we can combine this density, the above two densities. These two densities can be combined, and we can write the density in this form. That is, c is equal to c into the density c into this product of density. Here d is equal to m for the case 1. And the d star is equal to 0. That is all the m failure before the time t. And for the case 2, d is equal to j. So that is the joint density function. So now we move on to the estimation or application part or estimation part. For estimation part, we use I give an assumption for the lifetime distributions that follows a Kumarasamy exponential distribution. And this is the PDF and CDF for the Kumarasamy exponential distribution. And it's a generalization of exponential distribution. And if beta is equal to 1, we have generalized exponential distribution. And if alpha is equal to 1, we have exponential distribution. And this is a generalization of exponential distribution. So based on this progressive type 2 censored hybrid censored data, we can write the likelihood function like this. And in this, well, we consider both the maximum likelihood estimation and the Bayesian estimation. So as usual, for likelihood estimation, we find the maximum likelihood for we find the log function and the derivative with respect to both parameters alpha and beta, and we get the normal equations. and solve for the normal equations by using nonlinear equation functions. I use our program to solve the nonlinear equations, and we get the MLEs of both alpha and beta. So this is our usual procedure to obtain the MLEs. So now we move to the Bayesian estimation. So in Bayesian estimation, all of you know that we need several loss functions. So in this work, we consider both the symmetric and asymmetric loss functions. For symmetric loss functions, we consider square loss function, and this is also all of you know that the square loss function, the Bayesian estimation is nothing but the mean of the posterior density, and for the next loss function, the Bayesian estimation is like this. That is -1 by h log of expectations we raised to minus h mu, for mu is the unknown parameter and h is the non-zero quantity. And also we consider generalized entropy estimation, then entropy loss function. And that is and expected the Bayesian estimation. The Bayesian estimate in this case is the expectation of mu raised to minus q all raised to -1 by q is also non-zero here. And the prior assumptions for the parameters we consider as both the gamma price for parameter alpha and beta, and pi1 and pi2 is the unknown, the gamma pairs for both parameters alpha and beta. And so we can write the posterior density like this. This is alpha star. We join prior this, and this is the expression for the posterior density, the likelihood multiplied by the prior divided by the normalizing constant. So this is the posterior form of the posterior density, and you know that this is not in a closed form. So it is there are different methods to find the base estimators. One method is the MCMC method, and another method is Ringley approximation method, and another method is importance sampling method. In this case, in this work, we consider the importance sampling method to find the base estimators. For that, let h alpha beta be any function of the parameters alpha beta, then expectation of alpha beta is given by this. So this is a ratio of two integrals. So what we do in importance sampling method is we find the functions of alpha and find density functions of alpha and beta, then generate samples from the density function and find the expectation. So this is we can write as a ratio of two expectations. And we can approximate this expectation with our sample mean. Then that is the method we use. That is the procedure we use applying the importance sampling method. So that is this step, that is likelihood multiplied by the prior. We can write as a product of three quantities. The first quantity is f1 alpha. That is, this f1 alpha is the density function of alpha. And f2 beta given alpha. For a given alpha, beta, this f2 is again a density, and q alpha beta is a function of alpha and beta. So we are here, f alpha is a gamma density with parameters d plus 1 and b minus this summation I is equal to 1 log of 1 minus e raised to minus xim. And f2 beta given alpha. For a given alpha, f2 is again a gamma density. So we can easily generate samples from f1 alpha and f2 alpha, and q alpha beta is the function of alpha and beta. So if consider the square error function, square error loss function, then the base estimate is this. That is summation. CS are the samples generated from the G1 alpha and the G2 beta given alpha. Then we can find the base estimator based on the square loss function is this. This is, I already mentioned that the estimate is the ratio of two expectations. So we can approximate that expectation with the sample. That summation I is equal to 1 is alpha I q alpha I beta divided by summation I is equal to 1 is q alpha I beta. So alpha 1, alpha 2, etc. Alpha s are sample generated from f1 alpha, and beta 1, beta 2, etc. Beta is our sample generated from that F2 beta given alpha. Similarly, we can find the estimate based on square loss function. The estimate based on the Linus loss function is this form, and the base estimators of alpha and beta under the entropy loss function. So now we move on some simulation studies. So simulation studies, we take different sampling schemes. So I already mentioned that R1, R2, etc. are full sampling schemes. So first we consider scheme 1, that is R1, R2, etc. Rm minus 1 is equal to 0, and the Rm is n minus 1. So this is nothing but a usual type 2 sensoring scheme. So R1, R2, etc. all Ris are 0, then it is a type 2, and last term is Rm is n minus 1. This is a type 2 sensoring scheme, usual type 2 sensory. And another scheme, scheme 2, and scheme 3. We consider 3 sensory schemes, and the estimators are compared based on the mean square error and biases. And for base estimation, we took hyperparameters as A is equal to 2, B is equal to 2, and all the hyperparameters are equal to value 2. And this is the algorithm we use for the simulation study. So this we generate type 2 progressively, type 2 hybrid sensor data, M progressive type 2 hybrid sensor data from Marasami exponential distribution. And we generate samples from the gamma distribution from parameters, the given parameters, and values from beta from the density G2 beta given alpha, and repeat the procedure for 25,000 times, and we obtain the base estimators. We repeat all the procedures 500 times, and we obtain the bias and mean square of all the estimators. So that is the algorithm for the simulation study. And for the simulation study, we take our top T is equal to 0.07. And these are values of biases and the mean squares for the alpha cat and beta cap. So different sensory schemes and different values of N and M and different values of alpha and beta. And this is again the bias and mean square of different loss functions. This is the bias and mean square for MLEs, and this is the base estimators. Okay, then so in the simulation study, we take H is equal to 1 and Q is equal to 1. And from the table, we can see that bias and mean square of base estimators are smaller than of MLEs. So we can conclude that MLE is better estimate than, base estimators are better than MLEs. And base estimator of alpha underscore loss function possesses minimum bias, and the mean square Linux loss function possesses minimum mean square for small values of n. And from the table 3, we can see that base estimators of beta under entropy loss function possess minimum bias and mean square for scheme 1. And square loss function possesses minimum bias, and the Linus loss function possesses minimum mean square for scheme 2 and 3 respectively. So to illustrate the procedure, we use real data. So real data is active repair times in airborne transceiver. It's the data set reported in Johnson 1982 paper. So this is data, and we fit a Marasami exponential distribution to data, and the Anderson learning statistic value and the p values are given. We find the MLEs and base estimators, and we use the scheme like this 2 times, that the first 2 4 removals are 2s, and at the mth failure, at the 5th failure, all the remaining items are removed from the experiment. So this is the scheme, and these are the values for the estimators alpha cap. This is MLE, and these are values for the base estimators. For the parameters, values of alpha and beta. So move to the conclusion part. So in this paper, we consider progressive type 2 hybrid sampling scheme, and we consider the estimation of parameters of the Marasami exponential distribution. We consider both maximal likelihood estimator and base estimators. For base estimators, we consider there is entropy loss function and square loss function, inner source function, and general entropy loss function. And for base estimators, to find base estimator, we use the important sampling method. And based on the simulation study, we observed that base estimators perform better than MLEs. And among the base estimators of alpha, estimators under square loss function and inner source function perform better than entropy loss function. And among the base estimators of beta, estimators under entropy and inner loss function perform better than square loss function. And also real data has been used to illustrate the estimation procedures developed in this paper. And these are some of the references I already used in this presentation. Okay, thank you for the patient hearing.
No, thank you very much, Professor, for your wonderful. Now the floor opens for some question and session. Please see questions from the participants. Please ask one question. Any question? Okay. If it is not the case, let us thank the speaker, Professor Manoj Chako, for his wonderful presentation. Thank you very much. On behalf of the organization, thank you very much, sir. Now we call upon the next speaker, Professor Abdul Sattar. Please, sir, please. Thank you very much, sir. Thank you very much.
Thank you, sir.
Thank you.
Good afternoon, sir.
Yeah.
Sir, this is Professor Jayashree here, sir. Sorry.
Yeah. Please. Good morning. Yeah. Good morning, Jayashree. Good morning.
Good morning, sir. I just wanted to introduce Professor Abdul Sattar, sir.
Yes, sir, please.
Sir is a professor in the Department of Statistics, University of Kerala, Thiruvananthapuram. Sir's research areas of interest are non-parametric inference, Bayesian inference, reliability modeling, order statistics, and distribution theory. Sir's research and academic extension activities are, Sir has successfully guided 4 PhDs and 8 more are ongoing, and completed 21 MPhils and 3 are ongoing, and MSc project thesis 45 completed and 8 are ongoing. And sir has published 51 research papers. Sir has given 47 invited talks and conference presentations of 28, and sir has arranged over 18 conferences. Thank you, sir, for accepting our invitation to give the talk. I welcome you for this particular session. Thank you, sir.
Thank you, Professor Jayashree. Just a minute. Can you see my screen?
Yes, sir.
Okay.
You are audible and screen is also visible, sir. Thank you, sir.
Thank you. Good afternoon, all. Thanks to Professor Elankovan, sir, and Dr. Jayashree, and thanks to the organizers of ICSDS for accepting my work for the presenting here. The topic of my talk is about geometric vitality function based on K records for residual life. So this is the outline. So I will define the measure. I will give a brief introduction about this measure and define the measure on GVF, geometric vitality function based on K records. We discuss some properties based on this measure, and we have a brief conclusion. So this is actually a part of the PhD work of my student Gayatri, and also the part of my project received from DST, the matrix project received from DST. So thanks to DST also for supporting this work. And this is actually a part of this a small work progressing in my department. Actually, we are familiar with this vitality function. So vitality function is very useful in modeling lifetime data. So several authors studied this measure and used this measure for characterizations of lifetime distributions. See, the basic measure, reliability measure, hazard rate, reflects the risk of sudden death within a lifespan. So where the vitality function provides a more direct measure to describe the failure pattern. See, in this context, so this in the reliability context, actually vitality function can be interpreted as the average lifespan of, I will show this measure. So for a non-negative random variable y with probability density function q and cumulative distribution function capital Q, the vitality function is actually expectation of y given y greater than t. So this is actually the average lifespan of components whose age exceeds the small t, and it is, and also we know that this geometric mean is very useful average in situations such as analyzing data related to the size of bacterial populations, because the concentration of bacteria may vary over a wide range, a large range, vary over a wide range. So besides being used by biologists, so geometric mean is also useful in many other fields such as this analyzing income data in the context of economics, modeling financial data, etc. So Cover and Thomas observed that in 2006. So stock market, the field of stock markets, one normally remains reinvest every day. So the wealth at the end of n days is a product of factors, one for each day of the market. So the behavior of the product is determined not by the mean, but by the geometric mean. So in the context of this analyzing lifetime data, see the Nair and Rajesh 2000 introduced this concept of geometric vitality function based on the geometric mean of residual lifetime. So in this work, we propose the geometric vitality function of for the residual lifetime in the context of this K records. So under certain conditions, we study some monotone properties were studied using this measure, and bounds and characterizations results were obtained with respect to this measure, geometric vitality function of K records. Actually, aging is considered to be one of the important phenomena in reliability analysis. And we discussed about this, but we already give a background regarding this vitality function. And I mentioned several practical application of geometric mean also. So in that context, this work, geometric vitality function is defined. So for a non-negative random variable x, so the geometric vitality function is defined as log gt is equal to, this is actually expectation of log x given x greater than t. So it can be defined as 1 by f bar t, integral t to infinity log x into fx dx. So where f bar t is the survival function. So if x represents the lifetime of a component, log gt represents the geometric mean of lifetimes of components which have survived up to time t. So in survival analysis and reliability engineering, this measure plays a very significant role in studying the various characteristics of a system or a component. See this measure, this definition 1.1, we can simplify to 1.2. It's a very nice form. Log gt by t is equal to 1 by f bar t, equal t to infinity f bar x by x. So this is a very short form. And some of the works related to this geometric vitality function are this Suno GTL 2009 discussed geometric vitality function related to this interval truncator or doubly truncated random variables. So we have extended also this measure to the bivariate setup, and we studied several characterization results based on bivariate distributions. And Rajesh Shittiel 2014 proposed a non-parametric measure for this geometric vitality function for the complete as well as the censored samples. And this Gayatri and myself analyzed that we have given a definition of this measure in the context of past remaining life. So the measure is past geometric vitality function in the context of order statistics and establish some of its important properties as well. So study of information measures for the distribution of a random variable can be further extended to the study of information measures of ordered random variables arising from a random sample. So ordered random variables are considered to be more informative than observations of a random sample, as they carry with them information about their actual numerical value and additional information about their rank as well. So among the ordered random variables, records are given significant consideration due to its rare occurrence. See, record values arise naturally in many practical problems, and there are several situations pertaining to this meteorology, hydrology, sporting, and athletic events where only record values may be recorded. Outcomes of competitions, example in athletics, arise in ascending order. So in particular, sports events attract many people since records and best results appeals to people. So being most popular in sports, list of best results and records are of particular interest in many other areas of real life as well. So similarly, the next highest or the lowest value of the variable under study is a prime importance in several real life situations. Such a value breaking an existing highest or lowest value is called upper or lower records. See, another situation is one may be interested in concerned about the highest level of water above which a dam may breach. Here, the observer is certain that a dam can hold water till the latest observed level. Thus, uncertainty may arise mainly on the next highest water level. That is the uncertainty about the next upper record of water level that the dam may hold. So similarly, in the share market, the lowest occurring face value of shares is a matter of concern for making investment, whereas the highest occurring face value of shares can be considered for making returns. So note that expected waiting time to observe the next record is infinite. However, statistical inference based on records are difficult since the records occur rarely in real life situations. So the K3 records actually introduced by these authors in 1976, which occur more frequently than the classical records, can be used to overcome this difficulty. For example, consider this observations. So actually the records are, we start from the first value. So the next highest value is 1.486. So similarly, we can construct the records, and the sequence of K records for based on this data are given in this table. So the merits of K records have leads to extensive study of information measures based on K records. For theoretical and practical aspects of K records, one may refer to this Asinullah 2004, Hoffman and Balakrishnan 2004. So several others use this concept in the context of studying this different information measures. So several are this one, Medadi and Tata 2014, Ashan Chako 2015, So Goel 2018, Yosan Sata 2019, 2020, and we have several works in this context. So I will briefly give the definition of k-records value. Suppose we have the sequence yi I greater than or equal to 1 is a sequence of random variable with CDF q and corresponding PDF q. If for a positive integer k, we collect those observations in the sequence which occupy the kth largest position but exceeds in value for the first time the just previously recorded kth largest value. Then the resulting sequence is known as sequence of kth upper records or simply the k records. Let us denote the times at which upper k record values occur as p of j for m is equal to 1, 2, etc. and are defined by p1k is equal to k, where k is a positive integer, and pmk is minimum of this sequence, and zmk y of pmk minus k plus 1 pmk m greater than or equal to 1. So where rth order statistics from a sample of size m is denoted by yrm. So the sequence zmk is referred to as the k record values. So next we define the PDF of the upper k record value. So that's given actually in Arnold 1998 QMKY. So that is given in equation 2.1, and the same fashion we can define the lower k record values also. And corresponding to this lower k record values, we have the PDF. PDF is given in equation 2.2. And in this context, we have defined the geometric vitality function. The context of first we define for the context of m the upper record value, we define the geometric vitality function as for the residual life as log g u ym kt is equal to 1 by q bar m kt into integral t to infinity log y qmky dy. PDF. Q is a PDF, where QMKY and Q bar MKY is the PDF and survival functions of mth upper k record value. So we can simplify this equation 2.3 into 2.4. So it's a very simple expression. Log gu ym kt is equal to log t plus 1 by q bar mkt integral t to infinity q bar mky by y dy. So in the same fashion, we can define the lower record values that is actually given in 2.5 log GL. So we use the notation log GL xm kt equal to 1 by h bar m kt equal to t to infinity log x into hm kx dx. So this is for lower record values, and where HMK and H bar represents the PDF and survival function of mth lower k record value. The same fashion as for upper record value, this lower record value simplifies to equation 2.6. And it is noted that when we put k is equal to 1, this reduces to the classical records values. So in the following, we give an expression of geometry vitality function of k records in terms of expectation of truncated gamma distributed random variable. See Q, capital Q and Q bar. See correspondingly the PDF, CDF and survival functions of sequence of random variables, and YMK be the mth upper k record value from the sequence yi greater than or equal to 1. Then GVF of mth upper k record value is defined as log gu ymk is equal to expectation of log q inverse 1 minus e raised to minus wm. So where wm is actually the truncated gamma distribution with the corresponding PDF is given as in p of y. And in example 2.1, so see y is a sequence of random variable from uniform 0, 1, and y star denote the mth upper k record value drawn from this sequence. So figure 1a, so this is figure 1a, and the next So this represents the geometry vitality function of upper K record value arising from uniform 0, 1 for varying M and T, and figure 1b also corresponding the upper K record value from uniform 0, 1 from M is equal to 5 and K is equal to this values 4, 5, 8. So the interpretations are, so from this figure we can observe that this log GUYM star KT is increasing with respect to different choices of this M, and it can be seen that GVF of K records from uniform 0, 1 is less than that of GVF based on uniform 0, 1. So similarly, so the 1B we have GVF of K records for uniform 0, 1 shows an increasing behavior for various values of T. So first we change the values of M, now we change the values of T, and it is to be noted that from both figures we have this relationship log GT greater than or equal to log GUY star and KT. So which means that GVF based on K records is more preferable than GVF based on the original variable in some situations. So we can derive a relationship of this measure with hazard rate function. So that's actually given in 3.1. So this is a very simple expression, a direct relationship of this measure with hazard rate function. So we can see that using this relation, we can say that this GVF of upper K record value is actually uniquely determined the failure rate function of YMK. So this is a direct relationship. So we can see that based on the monotonicity of geometry vitality function, we can define a class of distributions that's given in definition 3.1. See, for random variable X is have a decreasing or increasing geometry vitality function based on, so denoted as DGVF or IGVF. If log GT is a decreasing or increasing in T greater than or equal to 0. So next we give a necessary and sufficient condition for the mth upper record value YMK have increasing geometry vitality function or decreasing geometry vitality function in terms of this hazard rate function. So Q and Q bar is actually the PDF and survival function of this IID random variables YI. Correspondingly, QMK and Q bar MK be the PDF and survival function of YMK drawn from this sequence. So now YMK has this increasing GVF or DGVF, decreasing GVF, if and only if log GU YMKT greater than or equal to or less than or equal to log T, where this is actually the hazard rate function of K records. To rho MK is actually the hazard rate function of K records. And we use the following example to illustrate this theorem 3.1. So Y follows this distribution Q bar by survival function B raised to A by B plus Y raised to A. So we have the expression of geometry vitality function for this distribution that is given 3.2, and we plotted this expression, say from 2.1 for using the expression definition and 3.2 we have we can find that C equal to 0 for T equal to 1. So 3.2 becomes log this can be, if C is equal to 0, this expression reduces to 1 by T plus log T. So this is actually the relation of for this particular distribution. That is that corresponds to theorem 3.1. So in the following theorem, we derive bounds for geometry vitality function for the mth upper K record values. So that is log GU YMKT. So Q and Q bar is actually the PDF and survival function of this YI, and correspondingly QMKY and Q bar MKY represents the PDF and survival function corresponding to this records. So we have this bound for 0 less than or equal to 2, T less than or equal to 1, log GU YMKT less than or equal to SUMK0 by q bar m k t, and for t greater than 1, log gu y m k t greater than S2 mk0 by q bar mk t, where SU mkz is actually this integral 0 to infinity q bar mk by dy. So this is actually a we derived the bounds for the upper k record values, geometry vitality function, and corresponding to the lower record values for the bounds for geometry vitality function of lower k record value, we have this log gl xmkt. See, that is given in theorem 3.3. See, h and h bar is a PDF and survival function corresponding to the sequence xi greater than or equal to 1. Similarly, hmkx and h bar mkx is the PDF and survival function corresponding to the xmk drawn from this sequence. So we have for 0 less than or equal to t less than or equal to 1, log gl xmkt less than or equal to slmk0 by h bar mkt, and for t greater than 1, log gl xmkt greater than slmk0 by h bar mkt, where slmk is this is integral 0 to infinity h bar x by x dx. So this is for the lower record k values, bounds corresponding to the geometry vitality function of mth lower k record value. And the following definitions we used, that is given in Shekhar and Shantikumar 2007, which is yeah, sir, which might be helpful for proving the upcoming theorem. See, y and zb two non-negative random variables with corresponding PDF and corresponding survival function. So this relations hold usually for all increasing function of psi by if and only if expectation of this relationship hold. So LR and ST actually represents actually the likelihood ratio and this stochastic order. So this definition we will use to prove in the upcoming theorems. So the following theorem established the monotonic nature of geometry vitality function for the mth upper k record value based on different values of m. So Q, capital Q and Q bar represents the PDF, CDF and survival function of the sequence of ID random variables. And YMK be the mth upper k record value drawn from the sequence yi greater than or equal to 1. Then log GUYMK, this is an increasing in m greater than or equal to 1. And we use the following example to illustrate theorem 3.4. So we use the distribution, Weibull distribution. So y follows Weibull distribution with corresponding survival function e raised to minus y raised to theta. And the expression corresponding to this geometry vitality function of k records simplifies to this form. And this is actually the denominator, that's actually the incomplete gamma function. And the following figure we depicts geometry vitality function of mth upper k records from Weibull distribution with parameter theta equal to 0.5 for various values of m. So this is the shapes of this graph, and we can conclude that for different values of k, this is an increasing choices for m, although this is increasing in y. So based on different values of m, the following theorem we established the monotonic nature of geometry vitality function for the mth lower k record value. So h
so
anyone is talking?
No, sir, you can continue.
Yeah. So let H, capital H and H bar represents the PDF, CDF and survival function of the sequence. HMK be the mth lower k record value from this sequence. So log GL XMKT is, this is a decreasing in m greater than or equal to 1. So the example, the following example we illustrates the above theorem. So x be a not inverse exponential random variable with CDF hx is equal to e raised to minus delta by x. So we have the expression corresponding to log GL XMK, that is log T plus this expression. So we use this expression to plot this measure GVF for delta equal to 6 for different choices of M. So this is the shape of graph obtained for this log GLXMK for T is equal to for different values of M and for different values of K. And from the figure, we can see that for the log GL is decreases as the values of sample size increases, and we can conclude that log GL is decreasing in M, although this log H inverse is increasing in X. So next we define an ordering based on this GBF of K records. So Y1 and Y2 represents a lifetime of two components, random variable Y1. So Y1 is said to be smaller than Y2 in geometric vitality order. See GVF, we define this as GVF if log GU YMK1T less than or equal to log GU Y2MKT. So, and the following theorem we discuss GVF order based on K records between two non-negative random variables that is closed under scalar transformation. So for any two absolutely continuous random variables Y1 and Y2, so we define this one Vi is equal to Ya by B. So we try to change, we try to study the scalar transformation of the original this random variable. So this is VMK1 GBF less than or equal to VMK2 provided this relationship is satisfied. So the following theorem that is actually given in Gupta and Kirmani 1998 and Gupta and Kirmani 2008. This is actually useful for providing the upcoming theorem. So using the lemma, we will prove this theorem. So the following theorem shows that GVF K records determines the parent distribution. So we already stated this results earlier. So Q be the distribution function of random variable Y. So log GUYMK represents the geometry vitality function of YMK drawn from this sequence. So we can say that log GUYMK determines the corresponding distribution function uniquely. So these are the important results connecting to this measure. So we are the conclusion of my talk is that we have the concept of aging has received a considerable attention among the system designers because of its outstanding application in reliability engineering. So at any time t, so the vitality function actually explains the life expectancy of system or components where GVF measures the relative performance of the system or components under consideration. So in the context of residual lifetime, we have extended the concept of this Naira and Rajesh to K record values. So under certain conditions, we have established monotonic properties for the proposed measure, and we have obtained some bounds and characterization results using this measure. So these are some of the results we have references we have used for this study. So this is our recent work in Metrica 2020, and these are some of our works related to record values using from information measures, thus SPL 2019, RIDSTAR 2020, and this is the original work of this Naira and Rajesh 2000. This geometry vitality function is originally introduced in 2000, and this is actually the non-parametric estimator proposed for this measure. That's actually 2014 in communication and statistics and theory. And 2020 we have SQL. We have a work related to K records, and this is actually 2010 we have introduced this measure in geometry vitality in the context of bivariate random variable. And for studying about this recent study about this measure with geometry vitality function, we have doubly truncated random variable. This Sunoji et al. In 2009. That is actually published in Communication Theory and Methods. And these are some of the works. And thank you for your patience.
Hello.
Sir, we cannot hear you.
Now the floor is open for discussion.
Sir, I think you have a network issue, sir. Alan, go on, sir.
Sound is not clear, sir.
Hello.
No, sir, it's still not clear. There's some network issue, I believe.
Hello. Is open for any question, any session. Thank you very much.
He's disconnected, I believe. So,
Thank you, Ellen Govan, sir, for chairing this session. Now, I would like to introduce Dr. A. Riaz, sir. Sir has got his PhD from the Department of Statistics, University of Kerala in the year 2015. He worked as a contract lecturer from the year 2012 to 2020 in the Department of Statistics, University of Kerala. Worked as an assistant professor in University of Kerala in the year 2020. So far, sir has published 15 research papers. Sir is also working as a reviewer of several reputed journals, communications and statistics, statistics theory and methods, communications and statistics, computation and simulation, and Journal of Applied Statistics. Sir has got Professor A.M. Mathai Best PhD Thesis Award in the year 2016. Life member of Indian Society for Probability and Statistics, life member and treasurer for the year 2021, Alumni Association, Department of Statistics, University of Kerala. Sir, now I request you to occupy the chair and please conduct the contributory papers session.
Okay, thank you. Can you hear me?
Yes, sir, you're audible.
can hear you, sir.
Okay, thank you for the organizers for giving me an opportunity to chair the session. Okay, now we will start our presentation. The first one is discrete pseudo Lilly distribution properties, estimation and applications on INAR1 process. Okay.
Hello.
Okay.
Hello, am I
Veena?
audible? Yes, sir. Am I audible?
Yes, Veena, please.
Yes,
Yes,
okay,
you can start your presentation.
Okay, thank you, sir. My screen is visible, right?
Yes, visible.
Okay, thank you. First of all, I thank the organizers for this opportunity. I'm Veena Dicruz. The topic of my presentation is on the discrete pseudo-linear distribution, properties, estimation, and application. This is a joint work with my supervising guide, Dr. Irshad Anwar. This is the outline of my presentation. First of all, going towards the introduction. Count data represents number of times a discrete event that has been observed. Such data sets can be seen in various fields such as geography, actuarial, that is the descriptive number of destructive earthquakes, monthly traffic accidents, etc. And these can be modeled using discrete distributions. Researchers have proposed many flexible distributions in order to model these type of data sets, and two popular methods to construct this new discrete distribution is that the mixing Poisson with the corresponding distribution and also with the survival discretization method. Now, discretizing a continuous failure time distributions are now a common interest, and it is such that if x is a continuous random variable having the survival function s of x, then its probability mass function can be constructed as given in equation number 1, and some of the recently introduced discrete distributions are given below. Now, in this context, I intend to propose a discrete model, that is the discrete pseudo-Lindley distribution, by using the pseudo-Lindley distribution, that is survival discretization of pseudo-Lindley distribution, which can model over-dispersed as well as under-dispersed count data sets. Now, moving onwards to the next section, that is, we first define the pseudo-Lindley distribution. It is a distribution defined by Zagdowdy and Nedjar in 2016, and it is obtained by mixing two distributions, exponential theta and gamma 2 theta, with mixing probabilities beta minus 1 by beta and 1 by beta. Suppose it's having the pseudo-Lindley distribution, then the PDF and the survival function of PSL is given in equation number 2 and 3. Now, we define the new distribution with discrete pseudo-Lindley distribution by the survival discretization method and the survival function of PSL, that is the pseudo-Lindley. The probability mass function or PMF of discrete pseudo-Lindley or DPSL is derived as in equation number 4, and the corresponding cumulative distribution function and survival function can be obtained as in equation number 5 and 6. The PMF given in 4 is low concave. Now, the possible PMF shapes for DPSL is plotted in figure 1. The figure clearly indicates DPSL is rightly skewed and have longer right tails. Now, my slide is moving, right? No?
Yes, it is moving, yes.
Okay. Okay, now the hazard rate function is given in equation number 7, and the hazard rate is plotted for chosen values of theta and beta as in figure 2. Figure 2 clearly indicates that DPSL is always increasing for the values of different values of parameters. Now, suppose the random variable x follows DPSL beta theta, then the PGF is given in equation number 8, and we can find out the moment generating function by substituting s by e raised to t in equation number 8. Now, then the mean and the variance of DPSL can be obtained as an equation number 9 and 10. The coefficient of variation and the dispersion index can be obtained as an equation number 11 and 12. Now, a table 1 and table 2 represent some of the descriptive statistics of DPSL. For the table 1 represents that of the fixed values of for a fixed value of beta, various values of theta, and table 2 represents the descriptive statistics for fixed values of theta and for various values of beta. And the figure 1 and 2 clearly indicates that a distribution can be used to model under dispersed, over dispersed, and also the positively skewed and leptochaotic data sets. Now, we give a formula for stress and reliability. Suppose x stress and x strength be two independent random variables having DPSL theta 1 beta 1 and DPSL theta 2 beta 2 respectively. Then the stress and reliability for the DPSL is given in equation number 13, and these tables gives some numerical values for the DPSL distribution, for the stress and reliability of DPSL distribution. From these tables, it can be clear that the reliability increases as beta 1 tends to infinity and theta 1 tends to infinity. Also, it decreases as beta 2 increases and theta 2 increases. Now, generating random variables from DPSL can be done using the Condale function, which is given in equation number 14, and also it can also generate random variables using discretizing the pseudo-Lindley distribution. Now, estimation and simulation. Here, we use two methods for the estimation of the unknown parameters. Suppose x1, x2, x3, xn be a random sample from DPSL. Then we first use maximum likelihood estimation, and hence the log likelihood function is given in equation number 15, and the normal equations are given in 16 and 17. And by using numerical optimization techniques, we can obtain the MLAs of the parameter theta and beta. Now, the weighted least square estimation, equation number 19 can be optimized with respect to the unknown parameters in order to obtain the unknown parameter, in order to obtain the weighted least square estimates of theta and beta of DPSL distribution. Now, we do a simulation study in order to prove the efficiency of the two estimation methods. We here use two sets of parameters for different sizes, and 1,000 replications are used. Now the estimates, and hence we use the estimates bias MSE and MREs in order to compare the two methods of estimations. And this one is for the first set, and this one is for the second set. And from these two tables, we can clear that theta is performing well for MLE, and for beta, WLSE performs well. Now the empirical study. In this section, we consider two real data sets, not to prove the application side. And the first one is that the first data set is based on a discretization concept, and the data is of a failure times of sample of 15 electronic components in a lifetime acceleration test, which is given in Lawless 2011. Table 5 gives the MLE's confidence intervals, Ks, the p-value, and the fitted p-values for all the fitted distribution, and also of the DPSL. We compare DPSL to that of discrete 3-parameter Lindley, discrete log logistic, discrete inverse Weibull, discrete Bar-Hutke, discrete Pareto, Poisson, and geometric. From this table, it can be clear that DPSL performs well since it has lowest minus log L, lowest case value, and have the largest p-value of that the other 7 distribution. Figure 3 depicts a PP plot for the fitted distributions as well as of the DPSL, and the figure 4 depicts the estimated CDF plot of the fitted distribution as well as of the DPSL. From these two plots also, we can be sure that our distribution DPSL provides better fit than the other distributions. Now, table 6 have the descriptive measures, some of the descriptive measures of the DPSL distribution of the Lawless data set. Here we can see that the fitted DPSL is overdispersed, moderately rightly skewed, and leptocratic. The second data set is a biological experiment data, which represents the number of European condor larvae pyrasta in the field, which is given in Bohtiswan and Sankum in 2016. The fits of DPSL is compared together with new Poisson-weighted exponential, discrete inverse Weibull, discrete Bar-12, discrete Bilal, discrete Pareto, discrete Bar-Hutke, and Poisson distribution. Table 7 reports those results. It have the data, observed frequencies, and the fitted expected frequencies, the estimates together with the standard error and the confidence interval, and also the log likelihood, chi-square statistic, degrees of freedom, and p-value. From this table, it is clear that DPSL gives the better fit since it has lowest log likelihood, chi-square statistic, along with maximum p-value. Now, the figure 5 gives the estimated PMF of the fitted distribution, and from figure also we can clear that DPSL yields a better fit than the other distribution. Now, table 8 have the sum of the descriptive statistics of the DPSL distribution, and here also we can see that DPSL, the fitted DPSL is overdispersed, moderately rightly skewed, and leptocratic. Now, moving towards the conclusion. Okay, today I have presented a distribution, discrete distribution, that is the discrete pseudo-linear distribution, and its statistical properties are derived. It can model under as well as over dispersed data sets. Now, also two estimation methods, the MLE and WLSE, were used to obtain the parameters, and a brief simulation study is also performed. Now, two real life data sets were analyzed to prove the efficiency of the model. And summing up, we can say that DPSL will be a commentable model that can find a wider application area in different sciences such as medical, finance, and actuary, etc. These are my references. Thank you.
Okay, thank you, Veena, for your presentation. Now, any questions?
Yeah, I have a simple question. In the step stress, what are the random variable?
Sorry, sir.
We have two random variable and stresses. Both are this distribution
yes.
or different?
Yeah, the both are independent random variables having DPSL. One is having parameters theta 1, beta 1, and other one is having theta 2, beta 2. Both are from the same distribution.
So you get a closed form there, or?
Yes.
Okay. Okay, you just see the table too. Some
table. Okay, shall I show it, sir? Hello.
Thank you.
Thank you, sir.
Yeah, thank you. Nice talk.
Okay, thank you, sir.
So next presentation will be of Ranjita Chol, CHO.
Hello. Is that audible?
Yeah, it is audible. You please share your screen also, ma'am.
Okay, sir. Is this visible, sir?
No, madam.
Now is this visible, sir?
No, madam, not visible.
1 minute, sir. Now is okay, sir? Hello.
Yes, I think.
Okay, sir. Good afternoon to the chair and all the participants. Myself, Ranjita Chol. The research scholar of Department of Statistics, Usmania University. I'm presenting on Poisson derived power series distribution. Here is abstract of the Poisson derived power series distribution. And let's discuss with this power series, then the power series distribution, and then the properties and the literature reviews, and then the Poisson derived power series distributions. Here the power series distribution. Let X discrete random variables taking the positive integer values with the generating function f of theta, which is expressed in the form of summation ax to the power of x, and this f of theta is said to be a power series, and the power series distribution is represented in the form of P of means probability of x is equals to x, that is represented with your ax theta power x by f of theta, where ax and theta are greater than 0 and the x values are from 0, 1, 2 and so on. And this is one of the example of the power series distribution, that is a binomial power series distributions where your x follows the binomial distribution, which is consists of the probability mass function NCX p power x 1 minus p n minus x is the power, and this can be expressed in the form of our power series distributions by selecting ax and theta power x in such a manner that so we can represent the binomial distribution in the form of the power series distributions. So here the ax is represented with NCX and the theta is represented with p by 1 minus p, so that when we are taking the summation of ax and theta power x, it is represented with here 1 plus theta whole to the power of n. And similarly, we'll do the same for the Poisson distribution. As a Poisson power series distribution, the literature reviews on the power series distributions are started with the Knock in 1950, then Khatri in 1990. 1959 and Patel in 1962 and so on are the persons who discuss about these power series distributions. Here the brief review on the literature of the power series distributions was started with the Knock in 1950 initially to introduce the power series distributions for the set of non-negative integers. And then Khadri and so on, the peoples have been presented these power series distributions. And these are the set of the power series distributions examples: binomial, Poisson, geometric negative binomial, or logarithmic and hypergeometric power series distributions. And here is the derived power series distributions. It is introduced by the Jayshree ma'am and Swami sir in 2006 by taking the ratios of the two power series distributions, and they have been selected this dx and ax. Dx is equals to ax and minus summation of bj and b x minus j, whereas initially d naught will be taken as 1, and this ax is represented with ax divided with a naught of a1 to the power of x, and bj is represented similarly. These are the properties of the power series distributions, and these non-central moments and central moments are given here, and the moment generative function and the characteristic functions of the power series distributions. These are the applications of the power series distributions. Zero inflated power series distribution model is mostly applicable in the clinical trials and also in some regression analysis, and it is also used in the flow frequencies and software reliability structures. And it is also used in our statistical quality controls. And this is Poisson derived power series distributions. Here we have took the definition of the Poisson in the form of the ratios of the two Poisson distributions with respect to the x and y variable, and is represented with the ratio of this Poisson, or we can say that in the form of the derived power series distributions. Here are the ratios of this is taken, and finally we got this probability of x is equals to s and divided with the probability of y is equals to x is represented with the summation I is equals to 0 to infinity pi x to the power of I, where pi is represented with e to the power of minus lambda 1 plus lambda 2 into di, where di is nothing but your ai minus summation bj di minus j. And here this ai and bj is represented over here, and this is a theorem to represent that whatever the answer we have got, it is equals to 1 or not. And this is the probability generating function of the Poisson distribution, so that from this we can derive its mean and variance, skewness and kurtosis. This is the mean for the Poisson derived power series, and the variance is also given, and this is the skewness and the kurtosis. And this is examples of this Poisson derived power series distribution in the medical field. So here we have to comparing the two Poisson distributions. It is used for the examining the relations of the post-menopause hormones and the coronary heart disease. When the women have this post-menopause problem, then what is the chance that they have this heart disease or not? And similarly, when we are going with the X-rays, what is the chance that the women will get this breast cancer or not? And this is the conclusions of this Poisson derived power series distribution, that this method is almost equally and much better than the distribution derived power series distribution which is there in our literature. These are my reference. Thank you.
Okay. Any question? Any question? Ranjita, you are starting your work in initial stage.
Yes, sir.
Okay. You have to do a lot of things in this paper. Yes. You have to study its properties of these distributions.
Okay, sir.
Or certain recurrence relations, and you have to estimate the parameters. So in future, you please do these things as very well. Okay. Thank you, and wish you all the best for your very nice presentation. Okay.
Thank you, sir. Is there any more suggestions, sir?
Yes,
regarding to this?
yes. Suggestions. You have to study more properties of this boson power series distribution.
Okay, sir.
Okay, some recurrence relation for probabilities, star moments, central moments, etc. And you have to estimate the parameters of this distribution by using maximal likelihood estimation like that, and you have to compare with the other existing models, and you have to prove that your model is a better fit for some practicable applications. Okay.
Okay, sir. Thank you so much, sir, for the
Okay.
nice,
Thank you very much for your nice presentation. Now, next presentation. Next one, a note on mixing proportions of new mixtures distributions. Swarnalada E. Swarnalada?
Yes, sir, she is there. Come.
Okay. Swarnalada, you can start now your presentation.
Is there an audible, sir?
Audio? No.
Yes, we can hear you.
Here, but it is not visible. We can hear you, but it's not visible. Okay. It is now. It is visible. You can start now.
Thank you, sir. Good afternoon, one and all. I'm Swarnalata. I'm Mrs. Scholar in Usmania University. My supervisor name, Professor G. Jayashree Garu. So today I'm going to present a topic on a note on mixing proportions of new mixture distributions. So this is my extra. So in this paper, and I propose a new mixture distributions using parameter distribution and composition of linear and Lorenz distributions with different proportions, and some of its properties are derived. And first of all, I'm giving the.
Please increase your volume, Swarnalada. Please increase your volume.
Okay. Audio, sir. Okay, sir. Now mixture distribution. Is it okay, sir? Now. Hello, sir.
Okay. It is now. It is okay.
Okay, sir. So mixture distribution is a probability distribution of a random variable x derived from the convex combination of individual distributions as component of the random variable with the corresponding weights of each component called the mixture weights. So here the random variable x takes the real values in a sample space omega space, follows the probability density function f1 of x with probability p1, f2 of x with probability p2, then the density function of that mixture distribution that can be expressed as the linear combination of this probability and individual density functions. Here the condition for the probabilities are pi greater than or equal to 0 and summation of pi is equal to 1, and the f of x is said to be a finite mixture distribution. So here I have given some of the mixture distributions I have listed here. So mixture of binomial and Poisson distribution, and mixture of two normal distributions, and the mixture of binomial beta distribution. So here this is the beta binomial distribution, is the mixture of binomial and beta distribution, and the corresponding density formation is f of x. Here the parameters are n comma alpha comma beta. NCK beta of k plus alpha, n minus k plus beta, beta of alpha plus beta, and mixture of exponential Weber distribution. So here the real-time applications on the mixture distributions are the particles deposited in ash at various distances downwind of the organic eruption of a mosque. This follows a mixture distribution when the samples are analyzed by sieving, measured by percentage of total weight in various range of size, results in a mixture distribution. And Second one is the underlying categories in catching a fish are possible age groups to which an individual fish might belong. That is whether it is from the current year's spawning or the previous years and so on. Then the component densities, length distribution for fish of different ages. Mixing weights are age distribution of snappers in the total population. And the third one is electrophoresis, is the study of the mobility of protons from an initial boundary with a buffer solution when subjected to an electrical potential difference, which also follows the mixture distribution. And these are some of the applications on mixture distributions. And here I have listed the some of the few items on this mixture distributions. Some of the other names I have listed here. And the brief review on the literature. Here, Tittergan, D. Smith, A. and Markov in 1985. The statistical analysis of the finite mixture. So there has been great amount of work done in the recent years, as well as of linear distribution. Its mixture with other distributions, generalizations, and extensions by many researchers, those including Zacher, Jade, and Vilati 2009, Nadraji 2011, Dennis and Ozeda 2011, Bakosh et al. 2012, Shaker and Mishra. So these many authors have studied that mixture distribution. So here I'm discussing about this mixture of Pareto distribution. So in the year of 1895, Pareto, Cleaver and Coates in 2003, Pareto distribution was taken as a model for income distribution for more generally heavy tail data, particularly in hydrology, finance, and insurance. In all of the aforesaid fields, loss distributions are usually skewed with a small number of very large observations corresponding to extensive money amounts or to disastrous losses. Hence, precise estimation of large quantities, that is 99% or more, must be based on the specifications with a suitable tail behavior of a distribution. Now, the Pareto distribution. So, the name, this name of an Italian world Swiss professor of economics, Vilfredo Pareto, 1848 to 1923. So this is the density function of the Pareto distribution. Here the X is the random variable, A comma K are the parameters. So this is the two parameter probability density function of the Pareto, that is A into K bar A by X bar A plus 1. Here A and K are the shape and scale parameters, and the range of X is greater than or equal to K. So here the mixture of Pareto distributions, here I have taken the, it is a mixture of three component Pareto distribution having fixed shape parameters 5, 6, 7 and a scale parameter K with their mixing proportions K square by 1 plus K square and K by 1 plus K square and 1 by 1 plus K square. Its probability density function is given by K power 7 by 1 plus K square into 5 by X bar 6 plus 6 by X bar 7 plus 7 by X bar 8. Here also the range of that X should be taken that it has the greater than or equal to K. And for this density function, the rth moment can be derived. So that is mu r dash is equal to K bar 7 by 1 plus K square into 5 into K bar R minus 5 by 5 minus R into plus 6 into K bar R minus 6 by 6 minus R plus 7 into K bar R minus 7 by 7 minus R. Here the condition with R must less than A. And next, I'm reducing, I'm going to explain about this linear distribution. It is a two-component mixture of an exponential distribution having scale parameter theta and gamma distribution having shape parameter 2 and scale parameter theta with their mixing proportions theta by theta plus 1 and 1 by 1 plus theta. So the corresponding probability density function of these two density functions, it becomes the linear distribution, that is theta squared by theta, a mixing of these two becomes a linear distribution. So theta squared by theta plus 1 into 1 plus x into e bar minus theta x. Here the range of the random variable x greater than 0 and the parameter theta also greater than 0. The corresponding distribution function is 1 minus of 1 plus theta into x by theta plus 1 into e power minus theta x. And Lomax distribution, a continuous random variable x is said to follow the Lomax distribution, and its density function is theta into beta bar theta by theta into beta bar theta into x plus beta whole power minus theta plus 1. Here theta and beta are the shape and scale parameter. So now here I am considering the mixture of this Lindley and Lomax distributions. So it is a mixture of the Lindley and Lomax distributions with their mixing proportions theta by theta plus 1 and 1 by theta plus 1, where in the scale parameter value of beta is equal to 1 has been taken in Lomax distribution. So now the new derived the probability density function is theta square by theta plus 1 whole square into 1 plus x whole power theta plus 1 into 1 plus theta plus 1 plus x whole power theta plus 2 into e power minus theta x, x greater than 0, theta greater than 0. And for this new density function, the rth moment can be derived as the mu r dash is equal to gamma r into 1 gamma of r plus 1 into theta square by theta plus 1 of gamma of theta minus r by gamma of theta plus 1 plus 1 by theta plus 1 into theta power r plus 1 plus r plus 1 by theta plus 1 into theta power r plus 2. So these are the references I have referred. So still I am working on this. So this is my presentation. Thank you, sir.
Okay, any questions or any comments? Any questions? So Swarnalata, you are mixing two distributions here.
Yes, sir.
Yes.
Yes, sir.
Lindley and Lomax.
Yes, sir.
Yes. So Lindley and Lomax distribution, two existing distributions you are mixing. So what is the mixing proportion here?
So here,
I think theta by theta plus 1 and 1 by theta
I'm
plus
not
1.
mentioning that.
Okay, is it the mixing proportion?
Yes, sir. For me, yes, sir.
Okay, what happens when beta equal to 1?
Here,
so what happens when, I think when beta equal to 1, your PDF reduces to the PDF of a Lomax distribution. Is it correct? Yes. Is it correct?
Lomax distribution.
Okay, beta equal to 1, this mixing distribution. That means Lindley and Lomax mixing distribution reduces to the Lomax distribution. Okay. 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 You have also studied several properties of this distribution. So you are starting only your work. Okay. Anyway. Okay. Anyway, thank you. Best wishes for your very nice presentation, Swarnalata. Now next topic is statistical inference of some new probability distribution and its applications.
Yes.
Pavan Kumar Singh. Yes.
Yes,
okay,
sir. Thank you, sir.
Okay, it is visible.
My screen. Good evening, respected chair, sir, and all participate. My name is Pavan Kumar Singh, Department of Statistics, Central University of Rajasthan. Today, I am going to present my work on a new lifetime distribution, statistical inference, and its application. My research supervisor, Dr. Abin Pandey. Sir. Next slide. My next slide is introduction. Lifetime distribution are common statistical tool used for the modeling and analysis of the lifetime phenomena for different characteristics of lifetime data sets. The hazard rate of exponential distribution is constant, which restricts its use of it. We are proposing a new single parameter distribution which has increasing hazard rate, decreasing hazard rate, and first increasing then decreasing. The proposed distribution can use a heavy tail alternative to the exponential distribution, gamma distribution. the probability density function of proposed distribution in equation number 1 given, and its plot for different value of theta. The cumulative distribution function of proposed distribution in equation number 2 and our CDF plot in given below for different value of theta. The hazard weight of the proposed distribution in equation number 3 and its plot in given below. We see that in the plot of hazard function, for small value of theta, the hazard is highly increased than highly decreased. But for large value of theta, the hazard rate is small increases. Similarly, the survival function in given equation number 4 and its plot in given below. Statistical property, moments. First, moment. The moment is not exist for all greater than 1. We calculate the inverse moment. The rth moment about origin exists only for r less than 1. It calculated from equation number 5. The general equation of our proposed distribution moment in equation number 6, where gamma k alpha is the upper complete gamma function defined in equation number 7. The integral of the equation number 5 is evaluated by Monte Carlo method. First, we draw a sample from a proposed distribution with parameter theta equal to 1.5 with sample size n. We calculate the expected of x to the power r. Plot the value of x to the power r with different value of sample size. First in figure 1, r equal to 0.2, we see that the convergent in figure 1. The value of integration at r equal to 0.2 is 1.44. We can see in the figure. Similarly, the above integral equation number 5 is not convergent for r greater than 1. This integral, for example, for r equal to 1.5, since the integration is not convergent, the plot does not converge to any point, as we can see in the figure 2. Quantile function, skewness and kurtosis. The quantile function QP can be obtained by using the equation number 8, where QP is the quantile function and of order P, where P belongs to 0 to 1. If P equal to half, we get the equation number 8 is the median value. Similarly, we can use the more measures of kurtosis and skewness in given equation number 9 and 10 respectively. Strength reliability. Strength model describe the life of the components having a random strength x that is subject to a random stress y. Let x and y follow the proposed distribution with the parameter theta 1 and theta 2 respectively. Then strength reliability evaluated by integral equation number 11. For different value of theta 1 and theta 2, we calculate the strength reliability reported in this table. For different value of theta 1 and theta 2, we calculate the strength reliability and given table. Similarly, estimation technique. Estimation based on percentile. First, we calculate 6 method of estimation technique we can use. First, estimation based on percentile. Among the most easily obtained, the estimator of the parameter of the Weibull distribution are the graphical approximation to the best linear unbiased estimator. It can be obtained by fitting a straight line to a theoretical point obtained from the distribution function and the sample percentile point. This method was originally explored by Cow 1959. We see also Balakrishnan 1994. In case of proposed distribution, also it is possible to use the same concept to obtain the estimator of theta based on the percentile. If pi denotes the sum estimate of f x comma theta, then the estimate of theta can be obtaining by minimizing the equation number 12. Equation number 12 partially differentiating with respect to theta, and we get the equation number 13. Solving equation number 13 using the non-linear method and finding the value of theta for different value of p. Here we the pi equal to I upon n plus 1. we get the value of theta is known as theta percentile. Substituting the value of theta percentile, equation number 3 and 4, we get the estimator of HRF and SF in equation number 14 and 15. Similarly, we calculate the least square estimators. In this method, we provide the regression-based method estimators of the unknown parameter, which was originally suggested by Wilson 1988 to estimate the parameter of beta distribution. The proposed method used the distribution of GXI for a sample size n, the LSC, by minimizing the equation number 16. When the equation number 16 differentiating with respect to theta and evaluating the 0, then we get the value of theta, which is called theta LSC. Substituting the value of theta LSC in equation number 3 and 4, similarly we get the value of hazard rate estimation and survival estimation in equation number 17 and 18 respectively. Similarly, we calculate the weighted least square estimators, the weighted least square, by minimizing the equation number 19 with respect to unknown parameter theta, where Wi is the given in equation. Differentiating above equation 20 with respect to theta and equating to 0, we get the estimate of theta, and the estimated value is called theta WLSC. Substituting the value of the theta WLSC in equation 3 and 4, similarly we get the hazard rate function estimate and survival function estimate in equation from 21 and 22. Similarly, we estimate the MLE. Let x1, x2, xn is a random sample from the proposed distribution with parameter theta, then the likelihood function is given below. Taking log both sides, and we get the equation number 23. Similarly, we differentiate the equation 23 with respect to theta and calculate, we get the equation number 24. The above equation 24 is a non-linear equation solving by the simple iterative procedure can be used to find the solution, and we get the estimated value of theta, and the estimated value is called like theta MLE. Substituting the value of theta MLE in equation 3 and 4, similarly we get the hazard estimation and survival estimation. Similarly, CME, the proposed estimator are based on the Kramer-Von Mises method. Substituting the value of 3 and 4, we get the hazard and survival estimations. Maximum product spacing method of estimation. The maximum product spacing method of estimation is alternate to MLE for the estimation of the unknown parameter of continuous univariate distribution. This method is used for the estimating the parameter. In this method of estimation, the parameter theta is obtained by maximize the geometric mean of the spacing with respect to theta in given below equation number 30. Similarly, we taking log both sides of equation 31, we get. To maximize the above equation, similarly we differentiate and equating 0. We get the value of theta, which is called theta MPSC, the equation number 30 from the 33. Substituting the value of theta MPSC in equation number 3 and 4, we get the estimator of hazard rate function and survival function from equation number 34 and 35. Simulation study. In this section, we generate a random number by using the inverse transformation method by using the R software. We use the Monte Carlo simulation study to assess the perform the proposed estimator PSC, LSC, WLSC, MLE, CME, MPSC of the parameter theta for the proposed distribution discussed in this section. We use the particular value of theta equal to 0.2, 1.05, 2.55, and the corresponding sample size n equal to 5, 15, 13, 50, 100, and 500. For each design, we draw the sample of size n from the original sample and its replicate 10,000 times. We calculate the mean of the parameter theta using the PSC, LSC, WLSC, MLE, CME, and MPSC, and their corresponding MSC. The result of reported in table 6. We see that all the methods follow the same pattern. By increasing the sample size, the corresponding MSC are decreased in all the method of estimation on the basis of MSC. We find the MLE is the best method of estimation on the basis of MSC, minimum MSC. Similarly, the simulation for the hazard rate function estimation and survival function estimation for the same sample size and for given value of t equal to 0.75, 1 and 1.5 and give the theta MLE, we calculate the hazard estimation and survival estimation and calculate the corresponding MSC for 10,000 times. They calculate the average estimate of the hazard and survival estimate with corresponding MSC, and results are reported in table 7 and table 8. Table 6 for parameter, for given parameter MLE, LSC, WLSC, we see that in table increasing the sample size, the MSC decreases and parameter is close to given parameter. Similarly, this table number 6, we find that MLE is the best performance because MSC is the minimum all of the LSC, WLSC, PSC, CME, MPSC. Table 7, true value of hazard estimation and corresponding MSC reported in table 7 for given value of theta. Similarly, the hazard estimation table corresponding MSC in bracket. We use the real data application. We use two real life data sets and compare with various model, namely exponential, Lindley, with corresponding PDF is given below. Equation number 16 and 17. Data set 1 reported in Shukla 2019 and Shankar 2015 come from data set number 8 that represents the survival times of a group of the patients suffering from the head and neck cancer disease and treated using a combination of radiotherapy and chemotherapy. The table for the real data sets AIC corrected, BIC and KS statistics. Our model is based in the basis of the AIC corrected, BIC, KS statistics. Similarly, the table for hazard estimate and survival estimate for the real data set 1. Data set 2 reported in Shukla 2019 in Shankar 2015 come from data set 13. They represent the time between the successive failure of the air condition equipment in 720 airplane. Similarly, the table for two data set, second data set, similarly reported AIC, BIC, KS statistics. Similarly, we estimate the hazard and survival estimation. This graph for data set 1, fitted distribution function versus empirical distribution function. This graph for data set 2, fitted distribution function versus empirical distribution. Conclusion. In this work, we propose a new probability distribution function. We discuss the various statistical properties of proposed distribution. Different parameter estimation technique employed for the parameter estimation, namely PSC, LSC, WLSC, MLE, CME, and MPSC. We find the MLE is the best method of parameter estimation on the basis of MSC, and also discuss the hazard and survival estimation for given theta MLE and given different value of t. The applicability of our proposed probability distribution assessed by two real data sets. The new proposed probability distribution perform well as compared to competitor models like exponential, Lindley, in various model selection criteria like AIC corrected, BIC, and KS statistics. My references is this. Thank you, sir.
Okay. Any question? Any question? Mr. Pawan Kumar Singh?
Yes, sir.
You proposed a new lifetime distribution.
Yes, sir. Yes, sir.
So, and it compare with the existing distributions on exponential and Lindley.
Yes, sir.
So, can you suggest any name your distribution? So, you please note that you can suggest any name. Okay.
No, sir. No decide.
Okay. Okay. Is it in your newly proposed model is increasing hazard relative function or decreasing hazard relative function?
Yes, sir. Yes, sir.
Or both?
Increasing hazard function with and decreasing, and both increasing then decreasing. Or increasing the increasing the value of x.
Okay. Okay. Anyway, thank you.
Thank you, sir.
For your nice presentation. Next
Thank you so much, sir.
topic, Bayesian estimation in exponential power distribution under type 1 progressive hybrid censoring with binomial removals. Prashant Kumar Sangal.
Is it visible, sir?
Visible.
Thank you.
Visible and audible. Now you can start now.
Okay, thank you, sir. Good evening to respected chair, sir, and my dear colleagues. Today, my presentation is on Bayesian estimation in exponential power distribution under type 1 progressive hybrid censoring with binomial removal. Myself, Dr. Prabhat Kumar Sangal, Assistant Professor and Discipline of Statistics. As my topic is too long and it has many terms as the type 1 progressive hybrid censoring and with binomial removal. So we take these terms one by one, and the content of my paper is censoring, implementation, my model, Bayesian estimation, Gibbs sampling, and different methods for generating the random number from my proposed distribution, my considered distribution, exponential power distribution, and sample generation from the posterior distribution, simulation study, and real life data analysis with the conclusion. Now, first of all, we come on the censoring. And if we, as you know, if we put a specified number of the items on the test, then sometimes we could not get the lifetime of all the items put on the test. And this technique is known as the censoring, and the data so obtained is called the censored data. There are main three reasons for censoring. One is that the study time is very short, so that we terminate our experiment due to time or constraint at a time, and so that at the time all the unit do not experience the event. And second one is that we sometimes withdraw the unit from the experiment. As in the case in the COVID situation, we free the medical facility for the more serious patient in comparison to the less serious, and we shift the patient to the general ward. And third one is that sometimes we lose to follow up the subject or participant in such as the participant move to the another hospital or sometimes they refuse to continue to participate in the experiment. And in literature, there are different types of censorings are available, that is in which type 1 censoring, type 2, random censoring, hybrid, progressive hybrid, and generalized progressive hybrid censoring. In this I will give a short brief about the censoring. First is the type 1 censoring or time censoring. In this type of censoring, we terminate our experiment at a pre-decided time point, and after that, we do not observe the lifetime of the units. In this type 1 censoring, the number of failed unit is random and time is fixed. Wherein the type 2 censoring, also known as the failure censoring, we decide a prefix number of units, and after that, when we observe these, suppose it is M, and when we observe the M failure, then we terminate our experiment. In this situation, the time is a random variable, whereas the number of the failed observation is a fixed. And but these both the type 1 and type 2 censoring have the main disadvantage that if the units are reliable, then we have in type 1 censoring, we have a very small number of the observed observation, because we do not wait till the failure of the up to the time t, because they are the more reliable, and the average life of the units is very large. And in the second type of censoring, we have to wait to get the M observation. So Espin in 1954 give a new censoring called the hybrid censoring, and hybrid censoring is a mixture of both the type 1 and type censoring. And he suggests that we terminate our experiment at the minimum of the prefix time t and the prefix number of the observation. And according to this, when t is greater than the failure time of the mth observation, then we terminate our experiment at time t. And when the t is less than the prefix failure time of the mth observation, then we terminate at our experiment at time t. So through this hybrid sensing, we control the time and the number of the observation. And Balakrishna and Sindhu work on the progressive sensing. In the progressive sensing, we withdraw survival unit from progressively from the test before the completion of the test. And this, since we here we remove the survival unit progressively, so it is named as the progressive sensing. And in progressive sensing, at the time of the first unit, we can withdraw R1 survival unit from the experiment, and similarly at the time of the second failure, we can remove R2. Initially, these R1, R2 are fixed, and they are do not follow any distribution. Yoon and Say in 1996 first time assume that these are the random variable and follow the uniform distribution and estimate the parameter of the exponential distribution by considering that the number of removals R1, R2 follow the uniform distribution. Later on in 2000, Say et al. Consider the binomial distribution for R1 and R2 and so on RM. And again, this is the type first progressive hybrid sensing, and Kundu and Jordan in 2016 study the properties properties of the progressive and hybrid sensing, and again they mix both these sensing and propose a new sensing named as type first progressive hybrid sensing. According to this, we can progressively withdraw the unit from the experiment, and we terminate our experiment at the minimum of the t and xm. And similarly, in the hybrid sensing, we just terminate our experiment at time t or at the time of the mth failure. Here we can also withdraw the survival units from the experiment when at the time of the first failure, second failure. And in this article, we consider the type first progressive hybrid sensing with binomial removals. Here we also we assume that the number of removals from the experiment follow the binomial distribution. So at the time of the first failure, we remove R1 unit from the experiment according to the binomial distribution with parameter n, m, and p. And similarly, at the time of the second failure, and we terminate our experiment either at the time prefix time or we at the time of the mth failure, which will be the minimum. In this article, we consider the model as the exponential power distribution, which is proposed by Smith and Ben in 1975. And the probability density function of this distribution is alpha lambda raised to the power alpha x raised to the power alpha minus 1 e raised to the power lambda x raised to the power alpha exponentially 1 minus e raised to the power x lambda x raised to the power alpha, and x follow the x is greater than 0. And here this distribution contains two parameters, alpha and lambda. Here alpha is the shape parameter, while lambda is the scale parameter. And we can also obtain the cumulative distribution survival function, and the hazard function of the distribution. The rationale of the distribution we consider here is that it has the two major properties. First is that the hazard function of this distribution is exponentially increasing for large value of time. Therefore, we can use this distribution when we observe faster failure rate with time. And second property is that the distribution is under certain conditions follow the bar-tub curve. And bar-tub curve is a very nice property of the distribution, and very few distributions have a bar-tub hazard function. And the life of the organism, especially the humans, being also follow the bar-tub distribution. So we can this distribution in very real life situation. In this paper, we consider the Bayesian estimation, and the main difference between the classical and Bayesian estimation is that in classical estimation, approach, we just assume that our parameter is a fixed constant, fixed and unknown constant, and while the sample observation are random. Where according to the Bayesian, the parameter is not a fixed constant, it is a variable, and we treat the observed sample as a fixed quantity. And it is also not, we cannot deny that we do not know about the parameter before the experiment. So the prior belief about the experiment is represented in the term of the prior distribution. And in Bayesian, we improve, or we improve our prior information in the light of the sample observation in terms of the posterior distribution. So in our paper, we just assume that our parameters alpha and lambda, and also the third parameter of the binomial distribution is P, is follow the gamma distribution, and whereas the removal probability binomial distribution probability is follow the beta distribution. The main reason for considering the alpha, the gamma or beta distribution is that because they are very flexible distribution, and by choosing the parameters of alpha, gamma, or beta distribution of first kind, we can convert these distribution in the informative or non-informative. So, and here we also assume that these parameters are independent, so we can write the joint density function of this function by the multiplication of the marginal distribution. And using the Bayesian theorem, we can also obtain the posterior distribution by the by this formula. Yes, sir.
You have only 5 minutes. Okay.
Okay, sir. Thank you. And after that, we can find out the joint distribution of this, and we can also obtain the marginal distribution. And in Bayesian estimation, generally we consider the loss function. So here we consider the square loss function, and we know that under square loss function, the posterior distribution, Bayes estimate is the posterior mean. So we can obtain the posterior mean of the distribution, but the expression has the multi-integration, so we cannot solve these integrals analytically. So here we use the MCMC techniques, and here we use the Gibbs sampling. And in Gibbs samplings, we generally find out the conditional distributions of the parameters of each parameter by considering other parameters as the known. So here we consider that, and we observe that the parameter, the conditional distribution of P is follow the beta distribution first kind. So we can generate the random number from this distribution, very standard, known standard procedure. And for rest, we use the Metropolis-Hastings algorithm within the Gibbs sampling. Here we also present the sample generation algorithm to sample generation from the type first progressive hybrid sampling, progressive hybrid sensing scheme with binomial removals, and also we also give the algorithm to find out, to generate the observation from the posterior distribution under the sensing scheme. And since here we cannot obtain the estimate of the parameters with the help of the analytically, so we use the simulation study, and also we assess the performance of the estimator by taking different parameters as the removal probability. What is the impact of the removal probability on our estimation? What is the impact of the termination time? And what is the impact of the sample size? And we here present the algorithm, and we find the different we estimate our parameters for different sample size and different probability, different termination time. We consider termination time in such a way that we get the 50%, 25%, and 0% censoring, and we consider the effective sample size so that we get 80% and 50% and 20% censoring. And here we also and we find that for sample size 30, 50, and 70, and we also present here a graph of the standard error for Bayes estimate with various M and with various T1, T2, T3 termination time, and we observe that as we increase M, then our standard error also decreases. And real life data analysis for to explore the applicability of our suggested approach, we consider real life data, and which are presented by the Mantel et al. And we estimate our parameter by considering the same parameter as we have in the simulation study, and we observe the similar result as we have obtained in the simulation study. Now, conclusion: effect of sample size. As we increase our sample size by keeping other factors are constant, then we observe then Bayes estimate converge to closer to the true value of the parameter. And also we notice that the standard error, absolute bias, mean square error also decreasing with the sample size. So the number this indicates that the number of unit put on the test play a significant role, and by increasing it, we can improve our estimate of the parameter. And similarly, effect of sample size, effective sample size, we get a similar result of the effective sample size. And this is will happen due to that when our effective sample size increase, then we get the additional information is gathered. And similarly, effect of termination time, as we get the similar result as we have obtained in the samples by increasing sample size. And the reason behind of this, that when we increase the termination time, we the number of observed failure also increase. Hence, it is also a dominant factor in the live testing experiment, and we can improve our performance of the estimator by increasing termination time. And last is the effect of the burnable probability. Parameter P, as we increase P by keeping other factors as constant, then we also get a similar result, that is our base estimate is closer to the true value, and the standard error, absolute bias, and the mean square error also decreases by increasing value of P. The main reason behind this is that when P is large, then majority of the unit would be withdrawn from the initial stage of the experiment, and there is a chance for obtaining the observation, which would be more spread about the whole range of the distribution. And when P is small, then the measure of the units are withdraw at the last of the later stage of the experiment, and we just get the information as we have get in the type second censoring stream. So this is also an important factor for estimating the parameter, and we have not faced any difficulty to considering the binomial parameter for estimating the parameter. Now these are our reference. Thank you.
Okay, any question? Any question? Okay, yes. Thank you.
Thank you, sir. Thank you.
Rafal Kumar Singhal.
Thank you
for your very nice presentation.
Thanks,
the time is very limited. Next one. Statistical inference in inverse Pareto distribution using randomly censored sample. Kapil Kumar. Kapil Kumar, you are not audible.
Radha?
Now, sir, am I audible?
Yes, audible.
Yeah.
Yes, you,
good afternoon.
You have 12 minutes time for your presentation.
How much time, sir?
12 minutes.
Oh, yeah, that's fine. Very good afternoon, respected Dr. Riaz and my colleagues. I'm Kapil Kumar from Central University of Haryana, and today I'm presenting my work, which is the basically work from my PhD students, classical and Bayesian analysis of randomly censored data using the inverse Pareto lifetime model. So Dr. Sangal has already discussed about the censoring, therefore I am skipping these slides. I'm coming down directly on the random censoring. Random censoring is important censoring which is useful in medical studies, especially in hospital data. So this random censoring was introduced in literature by Gilbert in his PhD thesis in 1962. After that, some early work is given by Breslow, Carlo, and Kaplan and Merrier, etc. also. And this is some recent study. So what we have considered in the random censoring, we considered that x1, x2, xn be lifetime of n identical items, or say lifetime of the patients are on the test. And again, we assume that T1, T2, Tn be the random sensing times of those patients or the items with different CDF. And we assume that these x and Ti mutually independent. Here, obviously, xi and Ti only one will observe actually. that is yi, minimum of xi or ti. And we will define another indicator variable di equal to 1 if xi less than or equal to ti. In this way, we have the di is a Bernoulli random variable with PMF this. Here, the joint PDF, joint probability density function of the observed variable y and the indicator variable y is given by this equation. And this is the probability of failure of an item before its censoring, or simply we can say probability of observing failures. Next, we consider the probability inverse Pareto distribution in this study. Actually, the inverse Pareto distribution is obtained by Gui and Gui in 2018. They inverted the Pareto distribution, one parameter Pareto distribution, and they obtained this PDF, CDF, and hazard rate function. Okay, and why I chose this model? The failure rate function of this model is decreasing as well as increasing then decreasing. Sometimes it becomes unimodal, or you can say upside down bottom shape, and it is very useful in hazardia disease data, or you can say medical study data. That's, and it is the beauty of this model is that it has only one parameter. That's why I chose this distribution. So once we have the lifetime x follow IP alpha and t follow IP beta, that is sensing time, then the joint PDF becomes given by this equation 6, and the probability of observing failure is given by this beta upon 1 plus beta. And here we have the observed data in the form y1 d1, y2 d2, yn dn, then the likelihood function of this data given by this equation, and the log likelihood function becomes this. So I'm coming straightforward to the estimation part. And first we find out the log likelihood equations, and from equation 7 and 8 we see that the solutions of these equations are not cannot be found out analytically. Therefore we need some repetitive methods like Newton-Raphson. I have used the optimum function for solving these equations, or simply log likelihood function. And again we say that suppose phi cap equal to alpha cap beta cap be the MLE of alpha and beta, then the observed Fisher information matrix given by this matrix, and there are the element, these are the elements. Yeah, this reference is not correct here. It is Lawless 2003. This is the second edition. In the appendix, they have given that they have shown that the asymptotic distribution of MLEs follow normal with mean parameter and with variance inverse Fisher information matrix. And therefore, with the help of this statement, we can find out the asymptotic confidence interval for the parameters alpha and beta. Again, now we have considered here Bayesian estimation for the parameters, and here we assume that the gamma independent gamma priors are the priors for parameters alpha and beta, and this becomes the joint prior distribution. Therefore, this becomes this with the definition of the Bayes theorem. It becomes like posterior distribution, and this is the posterior distribution. Again, we see that with the help of this posterior distribution, and we use here a squared error loss function to obtain the Bayes estimates. And if we find out the posterior mean, in the we know that the posterior mean is the Bayes estimate under a square error loss function. We find out the posterior mean, and we see that the equation 9 is the ratio of two integrals, and which cannot be solved analytically. Therefore, we use here Lindley approximation method and MCMC method. I have skipped the calculation due to the shortage of time. If someone is interested, I can show in my whole paper. So after that, I considered here one real life application and another one the simulation study. This is the data set of randomly, true randomly censored data set of the remission times of 30 patients with leukemia who received a similar treatment. Here plus sign shows the censored time. Basically, we can say this is the value of the t, and 1, 2, 3, 4. These are the values of x. First of all, we check that this model is good fitted for this data set or not, and after that, I considered Wavell distribution, generalized inverted exponential distribution, gamma distribution for the same data set. First of all, we use the KS test to check that all models are good fitted or not. We see that all models are good fitted at 5% level of significance. After that, I have considered some
model comparison tools like negative likelihood, negative log likelihood criterion, Ekek information criterion, Bayesian information criterion, and all these criterion suggest that inverse Pareto distribution may give us better choice than the others, even Weibull generalized inverted exponential gamma. And also we use Kaplan-Meier estimator for the survival function. This is the scenario, and we see that IPT is given by this green dots, and it is very close to the empirical, that is Kaplan-Meier estimator. Therefore, we can again say that our model is better than the others in comparison for this data set especially. And we obtained here MLEs and the asymptotic confidence interval, Bayes estimates, and high HPD credible intervals for the parameters. And after that, we come out for the simulation study, we have considered different lifetime models, different values of the true value of the parameters, say alpha equal to 0.75 and beta equal to 1.5. I have taken another set, alpha equal to 1.5 and beta equal to 0.75. And we have taken sample sizes, different sample sizes. And these are the observed sample sizes. That is the, we get finally values of the M equal to, this is nothing but summation DI. That is how many times we are getting failures. Actual observed data. So we see that this is the MLE, average estimate of the MLE, mean squared error, coverage probability, average length of the asymptotic confidence interval, variances, observed variances in the case of the maximum likelihood estimator. And from this table, also again for the next table, we consider Bayes estimate. And from these two tables, we observed that as the sample sizes, actually observed sample sizes increases, our average estimate comes out to the almost close to the true value of the parameter, and mean square errors usually decreases, even variances also decreases. Same case happen for the beta parameter. And this is the another set, and the same behavior is obtained here. And these are the references. These are used in this presentation, not the whole paper. So I have cut short this paper, the whole work. Now questions, please. Thank you.
Okay, sir, you are choosing inverse Pareto distribution.
Yes, sir.
So why you are choosing this model, sir?
Actually, sir, I chose this model because it is the one parameter lifetime model, and another one is it has the failure rate function increasing as well as decreasing failure rate.
Okay.
We can consider here log logistic, log normal also, but they have mostly complicated computations. That's why it becomes easy when we have only one parameter.
Okay, sir. Okay, thank you, sir, for your very nice presentation, sir.
Thank you, sir. Any other questions, sir, or may I stop it?
Any other question among the audience? No, sir. So next topic, statistical inference of multi-component strength parameter from Bartol lifetime model.
Hello, sir.
Yes.
Yes, sir. My screen is visible.
Yes, visible and audible.
Okay. Good evening to all of you. My name is Renuga. Today I'm going to present my research article on the reliability estimation of multi-component statistical model for bird type 12 distribution using progressively first failure censored sample. Live testing experiments are usually time consuming and in live testing experiment, the incomplete information commonly arise because of time limits and other restriction on data collection or study. In real life, we generally across with the censored samples, and censored samples are more useful then the complete sample in live testing experiment. In literature, various sensing schemes are available, as Dr. Kapil and Pawan sir also define these things. In my research work, I am using progressively first failure sensing scheme. Basically, this sensing scheme is the combination of progressive and the first failure sensing scheme. It was introduced in literature by Wu and Kuss in 2009. They combined the concept of progressive and first failure sensing scheme. Mathematically, we define as that there are n groups, each having W items are put on a live testing experiment. In going experiment, when first failure occurs in any group, R1 groups along with the group having first failure units are removed from the experiment. Similarly, at the time of second failure, R2 groups along with the group having second failure units are removed from the experiment. This procedure continues until all the remaining Rn groups along with the group having nth failure units are removed from the experiment. This is the PDF of the joint PDF of the progressive first failure sensing scheme. These are some particular cases of progressive first failure sensing scheme. Basically, progressive first failure sensing scheme is the generalization of progressive sensing scheme. If we take W is equal to 1, then it convert to progressive sensing scheme. If we take W is equal to 1 and R is equal to 0 to n minus m that we removed at the nth at item n minus m, that it convert to type second censored sample. Similarly, as for complete case. Now, multi-component stress strength reliability. In many real-life problems, there are reliability systems which containing two random variables as strength variable X and stress variable Y. This system fail if the stress implied on the system is larger than the strength of the system. It was stress strength model was introduced in literature by Wernbohm in 1956. A reliability system which contains more than two components is called multi-component system. This system is known as generalization of stress strength system. This system contains k independent and identical strength components and a common stress component. This multi-component system works until the strength of S out of k strength components is larger than the stress applied on it. It has many real-life problems. For example, a bridge having k number of vertical cables representing its strength can be seen as a multi-component stress strength system. The bridge will survive until the stress due to heavy traffic load, wind load, is less than the strength of at least S out of its k component. The reliability in a multi-component system is given by Bhattacharya and Johnson in 1974. X1, X2, XKB are independent and identically distributed random variable with continuous CTF effects. It represents strength component and Y represents stress variable. Then in this case, upper reliability, multi-component stress standard reliability is defined by expression 2. Now, in our case, we are using Bird type 12 distribution. The Bird type 12 distribution is studied as a failure time model by Solomon in 2005, and he shows its importance in live testing experiment. The PDF and CDF is given by expression 3 and 4, and its failure rate function is given by expression 5. Now, the inference on MSSR for Bird alpha beta. This let x1, x2, xn, k, and y be independent random variables following were alpha, beta 1. Here we are taking alpha, first say parameter alpha as a common. Now using expression 2, that means this, and 3 and 4, our MSSR is given by expression 6. We are inferencing this by using maximum likelihood estimation method and Bayesian estimation method. To estimate RSK, first we find the MLEs of its parameter, and then by using invariance property of MLE, we easily obtain the MLE of RSK. This is the log likelihood function, likelihood function, and the log likelihood function is given by expression 8. And to find the MLEs of the parameters, we solve these non-normal equations, but it is not easy to solve directly. So we can use by using Newton-Raphson method, or in R, we can solve this by using Optim function or NLM function. As we obtain our MLEs, then by using invariance property of MLE, we easily obtain our MLE of MSSR. Now, asymptotic confidence interval. As we see, this is not in a closed form, so it is very difficult to find out the exact distributions of RSK. That's why we are using asymptotic confidence interval. To find out the asymptotic confidence interval of RSK, that is MSSR, we use delta method. Delta method is defined by this expression. As we obtain this, the asymptotic confidence interval of RSK is given by this expression. Bootstrap confidence interval. As asymptotic confidence intervals provide good results when our sample size is large, but when our sample size is small, then in this case, boot confidence interval provides better result in compared to asymptotic confidence interval. Here we use two methods, boot P method and boot T method. These are the some steps that we are using in boot P method, and these are the steps that we are using in boot T method to obtain the confidence intervals. Now, Bayesian estimation. To find out the Bayesian estimation of RSK, we assume that the parameters have independent gamma priors, and the joint posterior density function is given by expression 3. As we see, it is not in a closed form and we cannot solve easily. That's why for solving expression 13, we use MCMC method. We can write expression 3 like this. Now we find out the full conditional density of the parameter beta 1, beta 2, and the parameter alpha. From here, we can easily see this is gamma density, so we can easily generate sample from here and for beta 2 also. But as we see, this density function is not well known closed form. So that's why in this case, we are using Metropolis Hastings algorithm to generate sample from this density function. So that's why we are using Gibbs sampling method with MH algorithm to generate the sample. These are some steps. Okay. Now the Bayes estimate of RSK under squared error loss function is obtained by this expression, that is expression 15. Now the simulation study. Here we consider two set of true values of parameters, and we done simulation study to compare the estimation that we have developed in previous sections. And here we use informative priors and non-informative prior. These are the censoring schemes that we use in our simulation. This is the table for average absolute bias and MSE of the ML and Bayes estimate of RSK. Here we see as the sample size increase, our bias and MSE decreases for both ML and Bayes estimation method. Prior one is for non-informative prior, prior one is for informative prior. As we see for the comparison, we see the results of informative priors are better than ML and non-informative prior. If we compare Bayesian estimator and ML estimation, then Bayesian estimation provide better result. This is the average length and coverage probabilities. Here we compare ML, asymptotic confidence interval, boot T, boot P, boot T, and HPD credible interval also. I skipped that slide. For calculating HPD credible intervals in case of Bayesian, we use the algorithm of Chen and Sau.
Renu, Miss
Yes.
Renu,
Yes,
you
sir.
have only 2 minutes remaining. Okay.
Okay, sir. I'm binding up. So here we see Bayes provide better HPD credible interval. This is my real data set. First, this is my real data set. First, we see whether fit of this data set or not. So bird distribution fit for this data set. These are the result for ML and Bayes estimations. And then we generate progressively first failure censored sample from our complete sample data sets. These are two censoring scheme. And on the basis of this censoring scheme, for the censoring scheme 1, this is my data set that is progressively first failure censored data. And for this data, we find out RSK, ACI, and Bayes estimates. Similarly, we do for the second case. And these are some references that we are using, that I use in this presentation. Thank you.
Okay. Any comments or any questions? It's the time for asking question. Okay, no comments. So the time is very limited. So thank you, Renu. for your
Thank you, sir.
very nice presentation. Next topic is a study on new modified alpha power variable distribution with application to COVID-19 data. Okay, Seema Chatri. Seema you can.
Seema is there, sir. I believe he's starting the presentation.
Yes, Seema is here.
Yeah, she's there, sir. Seema, can you hear us?
Seema, can you hear me? Seema.
She just logged out, sir. 1 second.
Sir,
Hello,
now
sir.
Okay, Seema, you please start now.
Am I audible?
Yes, audible.
Okay. Thank you.
Please share your screen.
Please share your screen, Seema.
Sir, please give me some time.
Okay,
Is my screen visible?
Okay, you start now.
Okay. Good afternoon, everyone. Respected chairperson and dear fellow presenter. The paper which I'm going to present today is entitled A Study on New Modified Alpha Power Variable Distribution with Application to COVID-19 Data. If I have to summarize this paper, I can summarize it in 3 points. Firstly, we'll study what is alpha power transformation method. Secondly, why we have used alpha power transformation method in variable distribution. And thirdly, we have proposed a alpha power modified variable distribution. And to show the applicability of alpha power modified variable distribution,
Seema,
we have
it is
considered a
not
real life
movable.
data set.
Seema,
Yes, sir.
your presentation is not movable.
Sir, what I can't hear you.
Your slide is not moving.
Your slide is not movable.
Is it moving now?
Yes, now it is moving.
Okay, thank you. For introduction, the idea of developing new distribution by adding an extra parameter to the existing family of distribution or combining existing distribution became an important topic in the recent literature. There are various methods available in the literature that can be used to make the distribution richer and flexible to model the data. One of the methods available is alpha power transformation method, which was suggested by Mahadevi and Kundu. They applied the alpha power transformation method to exponential distribution and introduced the 2-parameter alpha power exponential distribution with various properties and application. Many generalization of the alpha power transformation methods have been attempted by various researchers, and it is found that the proposed method has been quite effectively used for data analysis purposes. As we know that the variable distribution is a very versatile distribution, which is capable of modeling monotonic failure rates, that is increasing, decreasing, and constant hazard rate function. However, the variable distribution does not provide a reasonable parametric fit for modeling phenomenon with non-monotonic failure rates, such as the bathtub shape, upside-down bathtub shape, and unimodal shape failure rates that are very common in biological and reliability studies. An example of the bathtub shape failure shape is the human mortality experience. With a high infant mortality rate, which reduces rapidly to reach a low level, it then remains at the same level for quite a few years before picking up. We can also consider an example for unimodal failure rates function. That is, it is mostly observed in a disease whose mortality reaches a peak after some finite point and then declines gradually. And one recent example for this is COVID-19 virus. Many generalization of the Weibull distributions were proposed to tackle with bathtub shape failure rates function. And one such method is adding of extra parameter, which was proposed by Mahadevi and Kundu, which is known as alpha power transformation method. The main motivation for studying and applying the alpha power transformation method on Weibull distribution is as follows. The alpha power transformation method is a very simple and efficient method for adding an extra parameter alpha to an existing family of distribution. The alpha power transformation method makes the distribution richer and flexible. Alpha power transformation methods enable us to introduce only one additional parameter rather than introducing two or more parameters. The alpha power transformation methods provide models capable of modeling both monotonic and non-monotonic hazard rate function. The alpha power transformation method provides us better fit than other modified models having the same or higher number of parameters. Here we have introduced the alpha power modified Weibull distribution by using the concept of alpha power transformation method, which was given by Mahadevi and Kundu. Mahadevi and Kundu has given the CDF of the alpha power transformation, which is defined in equation 1.1, and its corresponding PDF, which is given in equation 1.2. Now we have used the CDF of the modified Weibull distribution, and we have introduced the alpha power modified Weibull distribution, which is given in equation 1.3, and its corresponding PDF is given in equation 1.4 with scale parameter lambda and shape parameter alpha and gamma. These are the list of 7 special submodels of alpha power modified Weibull distribution. This is the graphical representations of probability density function and hazard rate function of alpha power modified Weibull distribution. Figure 1 shows the plots of alpha power modified Weibull distribution probability density function for different values of the parameters. Figure 2 shows the plots of alpha power modified Weibull hazard rate function, and it is representing increasing, decreasing, upside down bathtub, increasing, decreasing, increasing, and bathtub shape hazard rate function. From figure 1 and 2, we can say that the density function and hazard rate function of alpha power modified Weibull distribution is decreasing, positively skewed, and unimodal, and the hazard rate function is monotonically increasing, decreasing, bathtub, upside down bathtub, and increasing, decreasing, increasing for different values of the parameter. Here we have defined some statistical properties of the alpha power modified Weibull distribution. The quantile function is given in equation 4.1.1. The moments and moment generating function is given in equation 4.2.1 and 4.2.2. Table 2 shows the moment for different values of the scale parameters alpha, gamma, and fixed lambda equal to 2. From table 2, it is observed that as the value of the parameter increases, variance decreases. Equation 4.3.1 shows gives the Renyi entropy of alpha power modified Weibull distribution, and equation 4.3.2 shows the Shannon entropy of alpha power modified Weibull distribution. Equation 4.4.1 gives the order statistics of the ith order statistics, and the asset moment of is given in equation 4.4.2. We have used the method of maximum likelihood estimation for estimating the value of the parameters. The MLEs of the parameters alpha, gamma, and lambda can be obtained by solving the above equation 4.5.2, 4.5.3, 4.5.4 simultaneously. But solving these equations to get the estimates of the unknown parameter in explicit form is quite difficult. Therefore, a numerical technique may be used to solve this non-linear equation. A simulation study has been performed to illustrate the behavior of the MLEs in terms of the sample size n. We generate a random number for a sample size of n equal to 50 and n equal to 100 from alpha power modified Weibull distribution using equation 1.3. We consider the value, we consider different values for lambda, alpha, and beta. For each setting, we obtain the average values of maximum likelihood estimates and the corresponding empirical mean square error. The average values of maximum likelihood estimates and mean square errors are reported in table 3 respectively. It is clear from table 3 that the estimated values of the parameters are very close or almost equal to the fixed values of the parameters. And it is also observed that as the value of the sample size n increases, mean square error decreases, which shows the reliability of the estimated parameter. A comparative study has been made to observe the flexibility of the proposed distribution with other existing distribution. The alpha power modified Weibull distribution is compared with several existing family of alpha power method, namely alpha power exponential distribution, variable distribution, alpha power inverse variable distribution, and exponentiated inverse flexible variable distribution. To check the adequacy of all the statistical models, several goodness of fit measures are considered, along with its p-value to compare the fitted models. These statistics are widely used to determine how closely a specific distribution fits the associated empirical distribution for a given dataset. In general, if the values of all the above criteria are smaller and the p-value is greater, the model is considered as the best fit dataset. This is a 242-day COVID-19 dataset from Singapore, recorded between 20th November 2020 and 19th July 2021. This dataset is comprised of newly reported instances on a daily basis. The dataset is taken from Elmel Valley. The minimum, maximum, first quartile, median, third quartile, squeamish, and curtosis of the datasets are given respectively. It clearly indicates that the data are highly skewed and leptokurtic. Thus, the alpha power modified variable distribution can be used as a justifiable choice for fitting the COVID-19 dataset. The maximum likelihood estimates, along with its negative log likelihood, are presented in table 4, and the adequacy model for model selection are presented in table 5. Figure 3 displays the plots of estimated density and estimated CDF fitted to COVID-19 dataset. From table 4 and table 5, it can be seen that the alpha power modified variable distribution has the lowest negative log likelihood, AIC, CAIC, BIC, HQIC, W, AKS statistic, and highest p-value. Hence, we can say that the alpha power modified variable distribution provides the best fit as compared to other existing distribution. From figure 3, it is evident that the proposed alpha power modified variable distribution is suitable model for fitting the COVID-19 dataset. Conclusion. In this paper, we have proposed a new lifetime distribution, namely alpha power modified variable distribution. Various statistical properties of the proposed distribution has been given. The method of maximum likelihood estimation has been used for estimating the value of the parameters. A simulation study has been performed, and it's observed that as the value of the sample size n increases, mean square error decreases. To show the applicability of the proposed distribution in analyzing real-life dataset, we have considered COVID-19 dataset, and it is shown that the alpha power modified variable distribution provides the best fit for the COVID-19 dataset as compared to exponentiated inverse flexible variable, alpha power exponential, alpha power inverse variable, and variable distributions. These are my references. Thank you.
Okay. Any question? Any question? Okay, thank you.
Thank you.
Seema Chetri for your presentation. Next speaker is Shaktivel.
Hello, sir, Nandini.
Okay, Nandini. Okay, Shaktivel and Nandini. Nandini, your topic is records based on extreme value type 1 probability distribution. So
yes,
you have only 10 minutes. The time is very limited. Okay.
Okay, sir. My screen is visible, sir?
Yes, it is visible.
Okay, sir.
Let's start now.
Good evening to all. Myself, V. Nandini, PhD research scholar under the guidance of Dr. K.M. Shaktivel, sir, Department of Statistics, Bharatiya University. My title of my presentation is Records Based on Extreme Value Type 1 Probability Distribution. Abstract of my study. In this paper, we present a new 3-parameter transmitted version of extreme value type 1 probability distribution based on lower record values. We present some statistical properties of this distribution. The maximum likelihood method is used to estimate the parameters of the proposed distribution. The fitting ability of this distribution can be determined by using real data sets, and a simulation study is performed to examine the asymptotic behavior of the parameters of this distribution. Outline of my study. Introduction, genesis of record-based transmitter map, record-based extreme value distribution, statistical properties, maximum likelihood method, Monte Carlo simulation, applications, and finally conclusion. Introduction of my study. In statistics, record values and record statistics is the largest or smallest values obtained from a sequence of random variables. Theory of record statistics is closely related to order statistics. It was first coined by Chandler. Record values and associated statistics are most important in real-life applications. For example, in industries, many products fail under stress. but the precise breaking stress or failure point varies even among identical items. In such experiments, measurements may be made sequentially and only the record values can be observed. Thus, the number of measurements made is considerably smaller than their complete sample size. This method is also known as a measurement saving method. There are situations in which an observation is sorted only if it is a record values. It can be used in meteorology, hydrology, climatology, economics, athletic events, and life testing studies. The genesis of record-based transmitted map. Balakrishnan and he 2021 proposed a record-based transmitted map to generate a new probability models. Let x1, x2 be a sequence of IID random variables with the distribution function. Then let x u of 1 and x u of 2 be a first two records of this sequence. If it is an IID random variables, then we define y for two different conditions for x u1 with probability 1 minus theta and u2 with probability theta. Theta belongs to 0, 1. Then the record-based transmitter distribution is obtained in the equation 1, and then corresponding probability density function is given in equation 2 for x belongs to the real line. Then x L of 1 and L of 2 be a first two lower records for this sequence of independent and identically distributed random variables. Then we define a random variable y for two different conditions for L of 1 and L of 2, x L of 1 and L of 2. As the same theta belongs to 0, 1. And then the distribution function can be obtained by using the above conditions, and then it can be, that is the record-based transmitter distribution is obtained in the equation 3 and the corresponding probability density function in the equation 4. Then extreme value type 1 distribution. This distribution is also known as a Gumbel distribution. Here we are using Gumbel type 1 distribution, which as one of its special cases, that is it is an alternative to Weibull distribution and exponential distribution, as well as it is related to Gomet's distribution. The Gumbel type 1 distribution has a probability density function with its two support alpha and beta, which is greater than 0, is given in the equation 5, and its corresponding cumulative distribution function is represented in the equation 6. And then the record-based extreme value type 1 distribution. Here we consider the lower record type transmitted map to frame the record-based extreme value type 1 distribution. The Gumbel distribution is considered as a baseline distribution here. Then the probability density function of REV type 1 distribution based on lower records is described in equation 7, and its corresponding cumulative distribution function is obtained in the equation 8. And then theta belongs to 0, 1 with its support alpha and beta, which is greater than 0, which is scale and shape parameters. This is a figure of probability density function of record-based extreme value type 1 distribution. This figure, the figure 1 of A, which represents for different values of alpha and beta and fixing the values of theta equal to 0.5, which is a unimodal right, which is unimodal left skewed and reverse J-shaped. And the second figure, figure 1 of B, which represents for alpha and beta are fixed and theta values are varying. And then this is the reliability analysis. There is survival functions, hazard rate functions, and cumulative hazard rate functions plays a vital role in many real life scenarios represented in equation 9, 10, and 11. This is this figure 2 represents a survival plot of record-based extreme value type 1 distribution for different parameter values. And this is the hazard rate function which is increasing over time when x value increases for different values of parameters of the distribution. I have discussed some statistical properties here. The quantile function is most commonly used technique to generate a random samples of the distribution, which plays a vital role. The random samples can be generated by using the Monte Carlo simulation in my study by using the probability distribution function. The closed form expressions of the quantile functions has been obtained by using the Lambert function. Without using Lambert function, I'm not able to get the closed form expressions of this particular distribution. So I use the Lambert W function, which satisfies the conditions below. And then I'm using the negative branch of Lambert W functions in the above equations. I'm getting the equation 12. By simplifying these equations to get the closed form expressions of the quantile functions, from this to get the median of this distribution, and then method of moment. the moment of REV type 1 distributions on lower records are given in the equation 14, which can be used to find the mean skewness kurtosis of this distribution, and the first moments and mean are also expressed in the equation 15. And then the incomplete moment of REV type 1 distributions for the lower records are described in equation 16, and then first incomplete moment can also be described, which can be used to find out the Born-Funnell Lorentz and Zinga index curves, which can be used for income distributions and economic studies. And then the probability weighted moments of REV type 1 distributions are expressed in equation 18. And then incomplete probability weighted moments of REV type 1 distributions are in equation 19. And then order statistics, there is a let x1, x2 be a sequence of random samples of size n. Let xkn denotes that ith order statistic. The period of order statistics can be represented in the equation 20. And then really entropy. Entropy measure is most commonly used to measure the uncertainty of the sample, and then it can be obtained by using a prior information existing. Here I have used a Rini entropy for this record-based extreme value type 1 distribution, which is for nu greater than 0 in the equation 21. Then the mean residual lifetime. The mean residual lifetime or life expectancy at age t is the expected additional life length of the unit which is alive at age t, which can be expressed in the equation 22. And then mean inactivity time. Mean inactivity time is a waiting time elapsed since a failure of an item on the conditions that the failure may occur. It can be expressed in 23 equation. Then here I have used the maximum likelihood estimation methods to estimate the parameters of this particular distribution. Let x1 to xn be a sequence of random samples from the record-based extreme value type 1 distribution with unknown parameters alpha, beta, and lambda. Then the likelihood functions can be expressed below, and then the log likelihood functions of this distributions can be written as follows by taking log for the likelihood functions in the equation 24, and then by using that equation 24 we are getting the partial differential equations, that is partial differential equations of particular parameters alpha, beta, and theta, then equating them to 0 to get the estimated values of the parameters. And then in this case, I have used the Mount Carlo simulations to generating a sample and measure the accuracy and asymptotic behavior of this particular distribution. Here, I have discussed here two different cases. This is the first case. This table 1 shows the first case of this simulation study. I have taken alpha value equal to 1.5, beta equal to 2.6, and theta equal to 0.1 for 5 different sample sizes: 75, 100, 300, 500, and 700. On seeing the root mean squared value, when the sample size increases, the value converges towards 0. That is n tends to infinity. This root mean squared value which converges nearly towards 0. And then the table 2, which represents the second case: alpha equal to 3, beta equal to 5, and theta equal to 1. Here we have discussed the mean, average bias, root mean square, coverage in probability, and average width for 5 different sample sizes. And then from the above table, we should verify that when the sample size n increases, the root mean squared error value decays towards 0. The average bias of the parameter alpha is slightly large for small to moderate sample sizes, but tends to get smaller as the sample size n increases. We also observe that for all the parameter values, the bias decreases as the sample size increases. Hence, from this, maximum likelihood estimates of record-based extreme value type 1 distribution are consistent and more efficient. Then real-life applications, we consider a data set representing a survival time of... Hello? Yeah, just a minute, ma'am. COVID patients of China. Here is a data set. And then the parameter estimates...
Please conclude.
Okay, sir, okay. Parameter estimates, likelihood functions, and information criteria are used to explain that record-based extreme value type 1 distribution gives a better fit when compared to other distributions. Extreme value type 1 Fredshit and exponential Fredshit distribution. Then goodness of fit test can also be considered to show the accuracy of this particular distribution. Then this is the conclusion of my study. These are the references. Thank you. Thank you,
Okay,
sir.
thank you. Thank you, Nandini, for your nice presentation. Next, Bindu PP. Our topic is double X gamma distribution and its application. Teacher.
Hello, can you hear me?
Okay, teacher.
I will share my screen. Hello, my screen visible?
Not visible, teacher.
It may come. Now it is visible?
No. Okay, it is now. It is visible, teacher.
Okay. Good evening, one and all. Myself, Dr. Bindu PP, Assistant Professor, Department of Statistics, Government Arts and Science College. Today, I am going to present my recent work on double X gamma distribution and its applications. This distribution is a generalization of a Laplace distribution, and also it is an extension of the X gamma distribution introduced by Sen et al. 2016. There are several generalizations of exponential distributions were introduced, and you know that exponential and gamma distributions were well-known lifetime distributions. And also there are several generalizations are have many applications in real life data and also in survival modeling. And in the present study, I have considered the X gamma distribution introduced by Sen et al. 2016. And it is a finite mixture of exponential and gamma distribution. And actually, the structure of the density is obtained by mixing exponential with the parameter theta and gamma 3 theta. And the mixing proportion is pi 1 equal to theta by 1 plus theta, and pi 2 is 1 minus pi 1, that is 1 minus theta by 1 plus theta, where theta is the scale parameter. In this present study, I have extended X gamma distribution to the entire real line. Just I would like to give a quick review on what is X gamma distribution. The PDF of X gamma distribution is given by in equation number 3. This is the mixture of exponential and gamma 3 theta. Exponential theta and gamma 3 theta. And now I introduce a double X gamma distribution, and it is a single parameter distribution with the density function given as in equation number 2. And I have derived the expression for the CDF, and it is given in equation number 3. And I have plotted the graph of double X gamma distribution for various values of the parameters. We can see that for lower values of theta lies between 0 and 1. The distribution have flat tails and also slight bimodality. And for theta greater than 1, it is unimodal distribution. And this is the plot of the CDF. I have also derived the expression for the survival function. It is given in equation number 4. And also I have derived the expression for the hazard function. I have studied the reliability measures also. And I have plotted the graph of the hazard function. We can see that it is increasing as well as we have then decreasing and then increasing structure. And also I have derived the expression for reverse hazard rate function. It is given in equation 6. And also mean residual life also I have derived expression for that. And I have also studied the entropy measures also I have not included in this slide. And also computed the regarding the properties, structural properties, I have studied the moments also, derived the expression for the moments. Since the distribution is symmetric distribution, odd order moments 0. Even order moments are given by equation number 9. And these are the expression for the mu2 and mu4. And also I have computed the expression for the earth absolute moment. And also have computed the expression for the coefficient of skewness and kurtosis. And also I have derived the, so studied the expressions for distribution of earth order statistic, distribution function as well as density function of earth order statistic. And also have computed the means, partial moment, earth order moments also not included in this slide. And now I am moving on to the maximal likelihood estimation of parameters. I have also done the estimation of parameters using method of moments and other methods and compared, and I found that maximal likelihood method is provide better estimate regarding lesser MSE and bias. So I have, for my application, I have used maximal likelihood estimation procedure. And since it is only with one parameter, it is very easy to compute MLE. And I have computed the MLE by maximizing the, usually we solving the likelihood function score equation, but in my procedure, I have developed an algorithm by, to maximize the likelihood function directly using the optimum function of the BFGS, optimum function in the BFGS algorithm. And I have also done the simulation study to check the reliability of the my algorithm I have developed in R. And for this, I have considered sample size. Actually, I have different sample size also used, but I have only included as 250. I have considered sample size 50, 100, and 250. And these are the outputs of my simulation study. Here I consider sample size 50, 100, and 250. In my applications, my data set have more observations, so I didn't included the data regarding this lower sample size. And I can see that if I increase the sample size, my estimates are more close to the original value of the parameter. And now for application, my interest is to introduce a new error distribution for microarray gene expression data, and also to develop a new testing procedure based on this distribution. And for this, I am suggesting this distribution as an alternative for the Laplace distribution. Laplace and asymmetric Laplace distribution are commonly used for suggested as an error distribution for microarray gene expression data. And in this study, I have used a microarray data sets downloaded from the Stanford microarray. And I used the archaic information criteria and AIC and BIC to for remodel evaluation. And regarding the data set, the data set experiment ID is actually 51398. This data is almost symmetric data. Since in this study I have considered symmetric distribution, so I took data set almost symmetric. And actually, I have also considered the asymmetric extension of the double X gamma distribution, but not included in this presentation. So I have considered microarray gene expression data, which has have slight asymmetry. And this data consists of around 42,000 gene expression values. And also I have normalized this gene expression data using the Lowes regression method introduced by Cleveland and Delvin 1988. And these are the box plots of gene expression data. We have red and green intensity values, and before and after normalization. I have fitted the X gamma distribution to the normalized gene expression data. And this is the descriptive statistic regarding my data set. And I have, for comparison, in this study, I have introduced a double X gamma distribution as an alternative for the Laplace and normal distribution. So I compared X gamma distribution with the Laplace and normal distribution. And again, I have used these, I have mentioned earlier, BFGS algorithm. Hello. Hello.
Teacher, you please continue, teacher.
Okay. This is the plot of fitted X gamma distribution as well as the Laplace and Gaussian for the gene expression data. This is actually gene expression data means log ratio of red and green intensity values. This is called the gene expression data, and we can see that this X gamma distribution is slightly better than Laplace. Both are performing similar. From AIC and BAC value, there is slight improvement for the double X gamma distribution. And this table 3 gives the estimated value of the parameters of double X gamma, Laplace, and Gaussian distribution. Regarding this distribution, double X gamma, this is only one parameter family, very simple structure compared to the Laplace distribution. Estimation also very easy. In that case, it is double X gamma distributions have some advantages than Laplace distribution. And also, finally, regarding the goodness of it, AIC and BIC values are compared to normal. There is a high difference. We can see for the AIC value and BIC value is very high for the Gaussian distribution. Laplace is have a very lower value compared to this. Since we are more than 40,000 observations, AIC and BAC values are very high because here the number of observations are very high. Because of that, AIC values are like this. More than 40,000 observations we are considering. AIC values, larger values. And compared to Gaussian distribution, we can see that Laplace and X gamma distribution is very much good fit to the data. And X gamma have some more advantages. And,
teacher, please conclude, teacher.
Okay. Lower value of AIC, lower AIC value of double X gamma indicate that this is better than Laplace and almost similar performance maybe. And in this present study, I have introduced a new family of distribution called double X gamma distribution, and it is a mixture of Laplace and double gamma distribution, and also has simple structure and single parameter. And regarding the estimation of the parameters, it's very easy compared to Laplace distribution, and numerical results show that our distribution is better compared to Laplace and Gaussian distribution. These are my references. Thank you.
Okay, thank you, teacher. Any questions? Any questions? Okay, thank you, teacher, for your nice presentation. Next, next topic, type 2 sensed Pareto 2 model with inliers at 0 and 1. So the speaker is Bhava Gosai. Okay.
Yes, sir. Is my screen visible?
Visible. You have only 10 minutes. Okay. Within the stipulated time, you please stop your presentation. Okay.
Okay, sir.
Okay.
Good evening, Riyaz, sir. And one in all present in this meet. Here, Pratima Bhava from the Maharaja Sayajirao University of Baroda. My presentation is on topic type 2 censored Pareto 2 model with inliers at 0 and 1. This is my joint work with Professor K. Muralidharan, working at the MS University of Baroda. The presentation content is to introduce term inlier, to discuss the various practical situation of the model, studied model, model description, then to
discuss the parameter estimation methods, and last, real data application for the result and references is given at
Bhava
last.
Gosai,
Now, first I like to introduce.
Bhava
Yes,
Gosai,
yes, sir.
your slide is
Yes, sir.
not movable.
Sir, I am moving it. Is it now?
Your slide is not movable.
But sir, I am scrolling it. Let me do first unshare and share. Okay. Is my slide visible?
Yeah, now it is moving.
Now it
Okay,
is
now
moving.
it is movable.
But in presentation mode, it is not moving, sir. That is the problem.
Okay.
So is it okay in this mode?
Yes, okay.
Okay. So let me first introduce the term inlier. Inlier is nothing but a small observation present in the data set which remains in other observation of the data set. Here, instantaneous failure and early failure we treat as a inliers. So what is instantaneous failure? Item with the that fail instantly at the time of experiment having value 0 is called instantaneous failure, and premature failure items are called early failures. When inliers are present in the data set, then we need to tackle such inliers using the non-standard mixer distribution. But in literature, there are two types of mixer distribution: standard mixer and non-standard mixer. So suppose G is the mixer of two distribution function f1, f2 with the mixing proportion 1 minus p and p respectively, then f1, f2 both are corresponding to the continuous random variable and is called standard mixer. Otherwise, if f is discrete distribution degenerate at some point A and f2 is either continuous or discrete distribution, then we call non-standard mixer. For my study, our study, we have taken f1 as a discrete distribution degenerate at point 0 as well as at point 1, and f2 is considered as a Pareto distribution. Atchison 1955 was first to discuss the inference problem on instantaneous failure in live testing, whereas the Kale and Mullidharan 2000 have first introduced the term inlier in connection with the estimation of the parameter in early failure model with the exponential failure time distribution. Let me discuss the practical situation in which our model is applicable. First, to treat the hematologic malignancy patient. If lesion is absent, then lesion size is 0. And if lesion is present but at a baseline level, that is, it is not possible to measure in CT scan or X-ray or MRI, then we have taken 1. And otherwise, lesion size is considered as the longest diameter, which has some positive diameter distribution function. Second case is in the mass production of technology component of hardware. Suppose n component put on a test, and some component easily we found fail at a time of installation, considered as observation 0 as a lifetime, and some fail with a negligible life, we consider it as 1. Otherwise, component lifetime have some positive failure time distribution. Also, it can be applicable in genetic birth defect study. Any baby with a genetic defect born dead, then we consider observation as a survival time as 0. And if any baby born live but have a death within 28 days, then we take observation 1. Otherwise, survival time of the baby having the positive distribution function. Similarly, in the rainfall measurement, our model is also fit to there. The model is the CDF and PDF of the model is as given in 1. PDF shows that x observation is equal to 0. We have taken as a probability 1, and P2 is the probability of x is equal to 1, whereas last line of the model gives the probability of x greater than 1. Using the Pareto 2 model with the B equal to 1, we obtain the model density function as in 4, and we consider here live test in which n items are there, R1 having 0 observation, R2 having the 1 observation, and remaining n minus R1 minus R2 having the life observation greater than 1. Their ordered observation denoted as usual notation we follow. as well as we adopt the type 2 sensor. Censored experiment is censored when we observe n minus r1 minus r2 minus c censored failure item, and obviously c is 0, then no censoring scheme is adopted, otherwise censoring scheme is there. Now, first method adopted is the MLE, and vector parameter vector theta, which is of parameter P1, P2 theta, is estimated using the our likelihood function is, just a minute, likelihood function is given in 5, where here we have used two indicator function, one for the representing the x0 observation, another for x1 observation, and for 4 different case of the inlier situation obtain the MLE parameters. Fisher information is obtained, and also found that asymptotic distribution of MLE is 3-variate normal distribution, and using the variance covariance matrix, interval estimation is given for the parameter P1, P2 theta. Second method used is the maximum product spacing estimator. Here we need to maximize the product S, which is the product of difference of two distribution function xi and xi minus 1. Obviously, when data having the same value, then this S going to be 0. So the problem is tackled using the Singh et al. 2016 method, and S is maximized. The 4 situation of the inlier situation is considered, and in the last case, when R1, R2 less than n, then we need to solve the equation 7 iteratively using the R programming, solve it and to get the estimated value. Third method is the uniformly minimum variance unbiased estimator. Sir, our method is easy to get parameter. UMV is of the parametric function like density function, survival function, and other important parametric function. So here we observe that density belongs to the 3-parameter exponential family, and obtain that Cx vector is jointly complete sufficient for the parameter vector. And we have obtained the distribution property of the Cx. After that, using the type 2 sensor data, we have obtained the joint density of the complete sufficient statistics as is in the 10. Interestingly, we found our density according to the form suggested by the Roy and Mitra 1957. And that's why using the distribution property, we first suggested the UMV estimator for the parameter, and second, using the result of similar approach of the result of Jani and Singh, we able to suggest several unbiased uniformly minimum variance unbiased estimator psi, which is a ratio from alpha to b, and alpha choosing several different value, we obtain several results for the parametric function, UMV of the parametric function in result 7 by setting the K1, K2, K3 along with the variance expression. By setting the K1, K2, K3, we get several corollaries, which is important for getting the UMV estimation of the such parametric function. Also obtain another parametric function g theta by setting K is equal to 0. We are able to get the UMV of P1, P2 as well as theta. Also, we have obtained the UMV of the density of our model along with the variance expression. Also obtained the UMV of the survival function with the along with variance expression, and all these results are demonstrated through 4 data sets. First data set is the loss ratio of earthquake insurance in California during the 1971 to 93. Here observed some years no loss ratio, and in some year there is a loss less than 1 billion, which is considered as 1. In the second data set, NFHS 3 survey of the Gujarat is taken, in which woman questionnaire, from the woman questionnaire, we consider a observation age on death of a child, and observe 15 stillbirths and 37 neonatal death. Stillbirth is considered as a zero life, and 37 neonatal as a 1 observation and analyzed. Third data is the forest burn area in India during the February to May 2014. Consider the affected burn area, and it is observed that 6 states, including territory, have no fire, and that's why observation fire burn area is 0. Whereas in the 5 territory or state region, it is burn area is less than 1 square kilometer, considered as a 1. Last data of the 50 states of US during 1981 to 2010. Average snowfall is considered as a data, and in some state average snowfall is 0, considered as a value 0, and as well as average snowfall is less than 1 inch, considered as a 1, and analyze all the data. First, we have shown using the way goodness criteria. All these 4 data sets to model well, and after that density plot is given here, survival function plot is given, and all the results of the parameter estimation is obtained using the R programming that is here. Due to the less time, let me tell you, all the methods are comparable here. Parametric function are also estimated for our all 4 data set. The second table gives the PDF and survival function UMUE along with the variance expression, and also it is observed that as survival function decreases as time increases in all 4 data sets. So lastly, I like to conclude that here various estimations to deal with the type 2 sensor parameter 2 model involving inliers at 0 and 1, and flexibility of the model is shown by applying the result on 4 real data sets of the different field. It is found that inliers play actually a role in bias of the estimator when we take inliers at 0 and 1, and all the methods are comparable, but still we suggest use MLE for estimating individual parameter, whereas use the UMVE to estimate the parametric function. This is my references. Thank you.
Okay, thank you. Any questions? So thank you, Bhava Gosai, for your presentation. Next.
It's my pleasure, sir. Thank you.
Okay. Next, a new generalization of inverse exponential distribution and its application.
Sir, actually, he is not there, sir. He is not present in the paper.
Okay. Jabir B. He is not here.
Yes, sir.
Okay. He is the last participant. Okay. Anyway, thank you all the participants for your very nice presentation. Once again, I extend my gratitude to the organizers of Indian Society for Probability and Statistics for giving me an opportunity to chair this session. Okay, thank you all.
Thank you so much, Dr. Riyaz, sir.
Thank you.
Thank you so much, sir.
Okay, thank you.
For the kind sentence.
Okay, okay.
Thank you all the participants.
Okay.
Thank you, ma'am.
Thank you, sir. Again, the session will start from tomorrow at 9:30 a.m.
Okay, madam. Okay, madam.